on Optics and Photonics organized by PRL Optica Student Chapter. SCOPE 2021 is the 6th annual international conference in the series. This conference is aimed to provide a platform for PhD and postdoctoral students to share their research with peers and experts in their respective fields. This is the first conference in India that is organized by the student and for the student. We are all aware of the pandemic situation that has gripped the world. We had hoped that, unlike last year, at least this year, we would get to see you all in person. Sadly, that has not been turned out to be the case. However, we are scientists and our spirit do not dip. Due to the overwhelmingly positive response that we received last year, we have decided to continue this legacy and perform this year's conference online. We are happy to tell you that this year participants come from various parts of the world, including USA, Berlin, Spain, France, Finland, China, United Kingdom, Singapore, South Africa, and of course India. Like every year, this year too, SCOPE 2021 will be conducted as a 3-day conference. The conference addresses various fields in vast spectrum of optics, with a major focus on nonlinear optics, ultra-fast spectroscopy, quantum optics, and quantum information. In addition to this, SCOPE 2021 has been extended to include interdisciplinary fields using light. Consequently, more invited talks are including this year to cover this diverse field. As mentioned earlier, this is the only conference in India that is for the student and organized by the students. All of this would have not been possible without the contribution of our chapter volunteers, together with the support from conference advisors Dr. Gautam Samanta, Professor R.P. Singh, and Dr. Rajesh Kushwaha. I would like to welcome our Honorable Director, Dr. Anil Bhardwaj. Being the Director of Physical Research Laboratory, he has always been generous and helpful in organizing the annual edition of SCOPE of our chapter. I welcome all the invited speakers of different disciplines who agreed to deliver their talk in SCOPE 2021 and have joined us from various parts of the world. We fully acknowledge the difficulties you all might have faced due to the time differences. We sincerely hope that the trouble you have put in is going to help the young scientist community to make a better tomorrow. I also welcome all the participants who have very enthusiastically chosen to attend this year's SCOPE conference. I have been told that today we have an audience of more than 170 people. I hope we all would gain a lot from this endeavor and implement it in a way that contributes to scientific and general society. On that note, and on the behalf of the entire organizing team, I welcome each and every one of you to the 6th annual edition of Student Conference on Optics and Photonics, SCOPE 2021. Thank you and have a wonderful day ahead.
Thank you, Anju. So that was our first woman chair of SCOPE, Ms. Anju Rani. Now, it is my pleasure to introduce the chief guest of this inaugural session, Dr. Anil Bharadwaj, Director PRL. Dr. Bharadwaj initiated the research in planetary science at SPL and contributed to the development of planetary science program in ISRO Department of Space and planning of planetary missions of India. He was the principal investigator, PI, of SARA experiment on the first Indian lunar mission, Chandrayaan-1, which has revolutionized our understanding on the interaction of solar winds with the moon through several new findings. He is the PI of MENSA experiment on the Indian Mars Orbiter mission, MOM. Dr. Bharadwaj has received several awards and honors, including the most coveted Shanti Swarup Bhatnagar Prize and the Infosys Prize of Infosys Prize of Physical Sciences 2016. He has also held many prestigious positions, such as the elected president of Asia Oceania Geoscience Society Planetary Science from 2006 to 2010. Currently, he is the chairman of the Joint National Committee of INSA International Science Council for COSPAR, Committee on Space Research, URSI, International Union of Radio Science, and SEO STEP, Scientific Committee on Solar Terrestrial Physics. With this, I request Dr. Bharadwaj to address the participants of SCOPE 2021 and officially inaugurate this conference.
Thank you, Madhu, and namaskar, suprabhat. A very good morning to all of you, and hearty welcome to the 6th edition of SCOPE, or Students' Conference on Optics and Photonics. This series of conferences started in the year 2015 and currently has 40 active members of the scope in PRL. This conference this year is a very special one, particularly because PRL is celebrating its Platinum Jubilee. PRL, or Physical Research Laboratory, established in the year 1947 by Dr. Vikram Sarabhai, the father of Indian space program, is completing its 75 years. And hence, this year's scope is a very special one for all of us. To celebrate the Platinum Jubilee of PRL, PRL has launched a series of colloquium called PRL Ka Amrit Vyakhyan. And this is a 75 episodes series of Vyakhans being conducted by PRL online from 4th of August of this year. It is being held every Wednesday at 4 p.m. And today, being a Wednesday, we will have a PRL Ka Amrit Vyakhyan, which is the 17th in series of Vyakhans, being delivered by Professor Andrew Bowie of University of Tasmania. So you all are welcome to join this live on YouTube channel of PRL. I am also glad to say that this scope annual conference is the probably only conference in the world which is being organized by the students for the students. The participants are largely students and postdoctoral fellows or young faculties. And this is aimed at disseminating information and having scientific discussions on a 3-day meeting. It is also a unique opportunity for our PhD students for their professional development and network. Unlike Scope 2020, that is the last year's Scope meeting, which was fully in online mode, this year's Scope conference is being conducted in a hybrid mode, where participants of PRL are attending this conference from a conference room at PRL, and the participants from outside PRL are participating in an online. The major focus of this meeting is nonlinear optics, quantum information, ultra-fast science, and largely I can say the application of light in different fields. And this edition has 12 invited speakers from outside India, 7 speakers from within India, and 15 speakers with a total of about 170, as I'm just told now, spreading over more than about 10 countries. So this is a unique occasion for the students. And as we all know that PRL has a very active program in optics and photonics for several decades. And this provides an opportunity for the students of PRL to really interact with the scientific community in a big way. I wish all the success for this 3-day event of the students by the students called Scope, and which is also providing an opportunity or providing a scope for our students to not only interact but also participate in live discussions with the experts in the field. I hope this meeting would be a great success and would provide a new feast of knowledge in the areas and the development in the field. With this, I wish the Scope meeting of 3 days to be highly successful, and all the participants would certainly get something out of this meeting in terms of their gain in knowledge. Thank you. Dhanyavad.
Thank you, sir. Thank you for that warm inaugural speech. I'm sure with such a diverse audience of eminent scientists and research scholars joining from various time zones, the conference is going to be a rich mine of knowledge and a sensational success. Now, I have Sandeep delivering the vote of thanks for this inaugural session.
Thank you, Madhu. On behalf of the entire team of Student Conference on Optics and Photonics 2021, I express my sincere gratitude to one and all of you for being present here and making this conference a reality. This conference could not be possible without the unwavering support and constant guidance of Scope Advisory Committee, composed of Professor R.P. Singh, Dr. Gautam Kumar Samantha, Dr. Rajesh Kumar Kushwaha. I thank them all for their round-the-clock availability for any help required. I also offer my sincere thanks to PRL and especially our director, Professor Anil Bhardwaj, to give us note to organize the Scope 2021. I also acknowledge the support extended by the Computer Center of PRL towards the design and development of conference website in such a short span of time. Amid the still prevailing pandemic situation, this is the second version of Scope conference in virtual mode, and this could not be possible without the premium Zoom membership provided by Optica. I express my indebtedness to Optica for providing us the premium Zoom membership. I'm also grateful to all the volunteers who put their continuous efforts to organize this conference. I would also thank all the Indian and foreign speakers who have shown their keen interest to present their research work in SCOP 2021. I also thank all the student participants and the student speakers for whom this conference is tailored to. To summarize, I thank you all for your support and we request you to continue the same enthusiasm for the years to come.
Probably there was a network error. So thank you, Sandeep. I'm sure all of the volunteers and everybody are have put immense help for this conference, and you thanking all of them is a great thing for today. Now we have reached the end of the inaugural session. Our next session, ultra-fast spectroscopy and molecular dynamics, will begin at 9:30, which should have been 2 minutes before, but it will be beginning shortly. This session will be chaired by Pranav Bharadwaj. So thank you all for attending the inaugural session.
Begin. Thank you, Madhu. Hello and welcome to the first technical session of SCOPE 2021 conference. The title of this session is Ultra-Fast Spectroscopy and Molecular Dynamics, and I'm Pranav Bharadwaj, the session chair. Before we start, here are some ground rules. The presenters can share their live screen using the share screen button at the bottom right of the window. I request all the presenters to adhere to the clock. The audience can use the Q&A widget to type in your questions, while panelists may ask their questions in the chat. People attending on YouTube can type in their questions in the comment section. All these questions will be compiled and addressed at the end of the talk. On this note, let's start this session. Our first speaker for today is Dr. Varun Makhija. Dr. Varun completed his PhD from J.R. McDonald Lab in Kansas State University on the topic laser-induced rotational dynamics as a route to molecular frame measurements under the supervision of Professor Vinod Kumarappan. He is currently an assistant professor at the University of Mary Washington and an active member of the ultrafast community. His talk for today is titled A Lab Frame Density Matrix for Ultrafast Molecular Dynamics. With that, sir, I invite you to deliver your talk.
All right, I will try to share my screen. I seem to not be allowed to share my screen. It says host disabled participant screen sharing. Okay, that seems to work now. All right, I hope everyone can see and hear me. If there are any technical issues, please let me know. Okay, so I'm gonna give a talk on molecular dynamics. The title's a bit of a mouthful, but hopefully I will be able to explain everything that's in the title as we as we go through the talk. Before I start talking about physics, I just want to acknowledge everyone who's involved in the work that I'm about to present. Hopefully I will be able to present all the work I intend to, but we'll see how time goes. My collaborators at the National Research Council, Dr. Paul Hockett, Albert Stolo, Simon Neville, and Michael Skirman, they played a big part in the work you will hear about on excited state dynamics and photoionization. And I'll also present just a little bit of ongoing work with a couple of collaborators from the Pulse Institute, Dr. Ryan Coffey and a graduate student, Kareem Hekazi. All of the work here that I will present is based on the honors thesis of my research student, Margaret Gregory, who was a physics student at the University of Mary Washington. I'll say a little bit more about that in a moment. She graduated last year and now she's pursuing a PhD in physical oceanography at MIT. So I don't think many people in the audience would have really heard of this university. So I thought I'd say a little bit about it. All our students are undergraduate students like Margaret. So we offer a Bachelor of Science or a Bachelor of Arts degree. It's in a place called Fredericksburg, which is about 80 kilometers south of Washington, DC. And its philosophy is essentially that the students who come here have to get a well-rounded education. So they don't take just physics courses, they take literature courses and philosophy courses and all sorts of stuff like that. This is also to say that if anybody in the audience ever finds themselves in Washington, DC or nearby in the United States, when we are allowed to travel again, you're welcome to come. Anju at the beginning mentioned something about time differences. It's currently 11:05 p.m. here. I am at home. I have my cup of coffee and I am in my pajamas. This is not the first talk I've given in my pajamas. So I just want to say if anybody in the audience would like to visit one day, that'd be great. Please feel free to contact me. We like hearing seminars from speakers. We have excited students. We typically have 1 or 2 colloquiums every month. All right, so that's a little bit about the place I'm at. So the work that I'm about to present, the bulk of it was done by an undergraduate student during her bachelor's degree. All right, so I'll give you a brief outline, very brief outline. I'll start with an introduction, and this is like very basic molecular physics. Since the audience here is so broad, I don't really know how many people have delved into molecular physics. So it's a very fun, basic sort of introduction. If you're an expert in the field, that's the time to check your email, or I don't know, if you're somewhere in Europe, maybe you're eating dinner, you can mute me, that's fine. The motivation part is when you want to come back to the talk, if you're an expert, and that's where I will talk a little bit about what exactly I'm doing. And the main thing here is I will be considering rotation in molecular dynamics calculations. So molecular dynamics is typically thought of as vibrational and electronic dynamics. Does rotation matter? That's essentially the question I'm going to talk about. And adding rotation is going to give us something called a lab frame density matrix. And then I will talk about the consequences of adding rotation for actual measurements. I'll show you some data, and I'll talk about how we can use this formalism to analyze that data. And finally, if I have time, I will talk about constructing the molecular frame from measurement. And what exactly I mean by molecular frame, I'll present in a moment. And then I'll end with a brief outlook of what's happening next, essentially. All right, so let's get started with this very basic introduction to molecular dynamics. I want to start with essentially what I call a molecule. It's a clump of atoms glued together. The gluing together is done by the electrons, and I'll talk about that in a moment. And for me, and I think most molecular physicists, we don't go beyond just a few atoms. This is just 2 atoms. This is ethylene, which is just a few atoms. You might see some molecules that are a bit bigger than this, but we don't really think about anything like a biomolecule, nothing gigantic with thousands of atoms. That's not what I will be talking about. Okay, so let's talk about the atoms being glued together by the electrons. So the way we understand the structure of a molecule, why the atoms come together in the way they do, is using something called the Born-Oppenheimer approximation. This is where we take this molecular state and we assume, and there's no a priori reason to assume this, that it can be written as a separable state, or one state of the electron, the quantum state of the electrons, the collective quantum state of the electrons, and the state of the nuclei. This separation is an approximation. In general, the electrons and the nuclei interact, so you shouldn't be able to write the wave function, the quantum state this way. But when you do write it this way, you find that you can come up with a Hamiltonian for just the electrons, and the electronic state is an eigenstate of that Hamiltonian, and it spits out an electronic energy times the eigenstate back. This should not be here. That's a mistake. I'm sorry about that. This electronic energy here turns out to be a function of, if it's a diatomic molecule, the distance between the nuclei. And here I've drawn that, and you can see very clearly there's a minimum, and then it starts to go back up again. So the molecular geometry is this minimum in the electronic energy. So when I said the electrons glue the atoms together, that's really what I meant. There's a minimum in the electronic energy. And for a polyatomic molecule, this is going to be a surface because there's more than one bond distance to consider. The minimum in that surface is what we think of as the molecular structure. Now, on top of this electronic energy, we can add vibrational energy and rotational energy, right? And the general structure of those energy levels kind of looks like a fine structure, kind of just like, you know, the fine structure of an atomic level, right? The green lines here represent the vibrational fine structure. On top of every vibrational level, there's an even finer structure. That's the rotational levels, right? So that's kind of like the vibrational and rotational motion, if you want to think of it that way, of the molecule on top of the electronic energy. We sort of break up the wave function too. I'll get to the picture in a second. The nuclear state into a vibrational state and a rotational state. And the details of those states I will talk about in a moment. Now with modern light sources like attosecond pulses, they have a very broad bandwidth, right? Since the pulses are very short. So you could imagine that such a pulse that's resonant with some excited state in the molecule the bandwidth would cover more than one electronic state. So this is what I've shown here. This is a very broad band, let's say attosecond pulse, and is going to excite a pair of electronic states. Inside each electronic state, there is a vibrational fine structure, just like I showed on the previous slide. And then if you zoom in on a single vibrational level, you get a rotational fine structure, right? And here I have labeled these rotational states with J and K. J is the total angular momentum of the molecule. K is the projection of that angular momentum onto the molecular axis. Right? M, the M in this state, is the projection onto a lab fixed axis, and we'll talk more about that in a bit. So there's this total energy, which is a sum of these three, and then there's the total angular momentum and the projection on the molecular axis. The total energy is a conserved quantity because I'm assuming this is an isolated system. It is a molecule hanging in the vacuum somehow, right? So then the total angular momentum is also a conserved quantity. But in general, there's no reason to think of these three things as being separately conserved. That is kind of what is happening in the Born-Oppenheimer approximation, because since we've assumed that the molecular state is written this way, these states in the Born-Oppenheimer approximation are the stationary states of the molecule. So population from one state won't hop to another one, right? That does happen though when the Born-Oppenheimer approximation breaks. So we'll talk about that just briefly, right? Now I've extended the situation to a polyatomic molecule, let's say a triatomic. This is just a model molecule. Don't worry about all the stuff on this. These surfaces here represent the electronic energy surfaces. This is just a pair of them. You can think of both of them as excited states, and down here is a ground state, right? This intersection here of the two electronic energy surfaces, this is where the Born-Oppenheimer approximation breaks down in the worst possible way. And in this vicinity is when it also breaks down very strongly, right? So you can imagine that if one of these states is excited and we're somewhere in the vicinity of this conical intersection, population can hop from one state to another. In other words, the electronic energy can be exchanged for nuclear energy, right? So these things are not individually conserved. One can change to another, but the total energy must be conserved, right? Similarly, the total angular momentum must be conserved, but the projection on the molecular axis need not be. All right. So what I'm going to do now is pretend like we excite a superposition of these two with an attosecond pulse, kind of like the picture I showed you previously, but I'm going to ignore everything but the electronic states just to simplify life a little. And I'm going to switch from kets to wave functions. So let's say I've excited coherently a pair of electronic states, and I get a superposition of the wave functions this way. Now we know these electronic states are not eigenstates, so the amplitudes of each are going to be time dependent. The time dependent probability distribution is the absolute value squared of this thing. So it works out this way, right? The absolute value squared C1 is the population of one of the electronic states, let's say upper one, if I call that state one. The absolute value of C2 squared is the population of the second electronic state, let's call that C2. And this additional term, the interference term, we call that a coherence, right? In general, the dynamics of this system are determined by all these things together. You need the populations and you need the coherences. All of that stuff together tells us what happens as a function of time after I excite the molecule with some kind of pulse, right? Okay, so that's essentially all I wanted to do as a brief introduction. I'll just briefly review it. And when I review it, I'm going to add a little bit of information. Instead of thinking of these as amplitudes of wave functions, we can just use a density matrix. The diagonal elements of the density matrix are the populations. The off-diagonal elements are the coherences. And you need the whole density matrix as a function of time to determine the dynamics of the molecule, right? All right. So the things we need to remember is that total energy and angular momentum are conserved, other things mix, and the dynamics can be characterized entirely by the density matrix, the populations and the coherences. Okay, so that's the end of the introduction. Now the experts can start listening to, stop checking your email. Let me talk about my motivation. That picture that I just showed you of those two surfaces, that's not actually of the water molecule. It is of a theoretical molecule, a made up system. And it was invented by the folks who wrote this paper here. And they have this very interesting idea where they say, all right, let's start in the ground state and let's pretend we excite only one of these. So they show a little wave packet here. That wave packet represents a superposition of vibrational states on this electronic surface. And then they show you a trajectory that this wave packet may take on the electronic surface, somewhat semi-classically here, right? And then when it gets in the vicinity of this conical intersection, remember that's where the Born-Oppenheimer approximation breaks down really badly. So population can hop onto the other surface, right? Total energy is still conserved, but population can hop onto the other surface. So at this point, population from state one is falling and it's going into state two. But look, you can also see a coherence show up, right? So the point the folks who wrote this paper were making, if we can measure this coherence, it's kind of like a direct measurement of the system going through this conical intersection, right? And they come up with a way to measure it. These two follow-up arrows here represent two pulses that are intended to measure what is called the reduced electronic density matrix. They're just interested in a coherence between the electronic states, nothing else, right? All right, that's really interesting, right? The question I want to ask is, well, what about rotation? That sounds like a really silly question because if you can see the time axis here, all of this happens in 140 femtoseconds. Molecules don't really rotate in 140 femtoseconds. That's too short a time. But what I mean by rotation is not really rotational dynamics. It'll become maybe slightly clearer if I show you a different demonstration. It's a different experimental proposal. So this is a proposal. The experiment has not been performed. This is another proposal for measuring just electronic dynamics now. There's no vibration occurring here. This is a molecule, amino-nitrostilbene. You'll see it later in the talk. It's been excited by an attosecond pulse. And these blobs here represent the charge density, essentially, of this excited molecule. As a function of time, you can see the charge density spreads across the entire molecule. This is a very interesting thing as far as chemistry goes, the transport of charge across a molecule. People are very interested in measuring things like this. The paper is also, in this case, proposing a way to measure this charge transfer, right? And in this, they decide to use X-ray diffraction to do so. The issue here is that this is a fixed molecule. Now you've probably heard about the fact that we can align or orient molecules with femtosecond pulses, but that is not what we cannot do this. This, in fact, is not allowed by quantum mechanics. Quantum mechanics doesn't allow you to fix a molecule, right? We may be able to get a very tight distribution of molecules, but we will never get here, right? So this is an approximation. It's the fixed molecule approximation. Experimental reality is something else. What's happening in the experiment is let's say, typically, we start with randomly oriented molecules, and then we excite them resonantly, right? So what we'll have there will be a charge density in the laboratory frame, right? It will look like something. I've just drawn, this is a L=2 spherical harmonic here. And that thing on the right there is going to do its own kind of oscillation. And that's what the X-rays will scatter off, right? So this is what we're going to see in an actual experiment. So I want to know, from here, can we somehow get this stuff? Basically, essentially, that's the question I want to ask, because experimentally, we're not going to be able to achieve this. All right, so now, how do we add the lab frame to this situation? In the molecular frame, it's what we talked about just a moment ago. We've made a superposition of electronic and vibrational states somehow. We don't consider rotational states at all. Right? This is a fairly drastic approximation because we're removing a conserved quantity. We're removing total angular momentum. It is advantageous in the fact that there are fewer degrees of freedom, of course, because you don't have to consider the orientation of the molecules in this case. When you tack on the total angular momentum states, you do. Okay. So what we're going to do is stack those states on in some sort of tenable way and try to see what happens. And the second thing is I don't want to deal with quantum states. I want to deal with the density matrix because it's very difficult to produce a quantum state. So I will deal with the density matrix. All right. So how do we do this? Warning, the next slide has a giant equation on it. Don't worry about it. And we're going to try to work through it one piece at a time. All right. So here's the giant equation. This is essentially an operator we invented. It's not entirely out of the blue. It is very much based on a previous operator invented to investigate the orientation of electrons in atomic excitation. So it's essentially stolen from Fano. But the important parts of this giant equation are here, these two pieces, this pair of Bra and Ket, or Ket and Bra, is a pair of angular momentum states, right? So now we've kicked the molecule with an attosecond pulse, and we've excited a whole bunch of angular momentum states. We're looking at every pair, J prime J, and these are also on different electronic states, N prime and N. So every pair of coherences between different angular momentum states, so because we're summing over both of these, are included in this operator, right? And also coherences between different vibronic states. So I've collapsed the electronic and vibrational states into a single letter N there. Right? So this piece is just all the coherences happening in the system, including those between angular momentum states. And these guys here are Wigner 3J symbols. You've hopefully seen them in quantum mechanics class. All they do is they take every pair of J and J prime that's in the wave packet and add them up to get a total angular momentum K. This K is also labeling our operator on the left-hand side here. Forget about Q and S for now. Actually, I won't talk much about Q and S in the rest of the talk, so let's forget about Q and S. But K, we can kind of think of as a total angular momentum of the wave packet. It's all of the pairs of angular momenta summed together, right? Summed in the way you add angular momentum, right? All right, so keep this operator in mind, right? we're going to use this to get the lab frame part of the problem. Let's just go back to the molecular frame part of the problem for just a moment. This was our quantum state. Now I can write the wave function squared, which is the probability of locating the electrons. R represents the coordinates of all the electrons at a set of coordinates labeled small r, for a set of nuclei at coordinates labeled by Q. Okay, so there's no orientation here because this is all in the molecular frame. And this is the same kind of equation that you saw before. There's the populations. Now I've written them as the density matrix. This is the population of a single electronic state and a single vibrational state in that electronic state, and we sum over everything. Here are this interference piece, right? It's the overlap between pairs of electronic wave functions and pairs of vibrational wave functions, and here are the coherences, okay? So this is in the molecular frame. It's essentially the same thing as I had in the introduction, but I have now also tacked on vibration, right? And it's not just two states, it's any number of states. Now let's look at what the lab frame version looks like. I won't derive this for you, but this is the lab frame version. This is the probability that I will find first a molecule oriented at angle omega. On that molecule, the set of electrons will be at a set of coordinates small r, and the nuclei will be at a set of coordinates capital Q. Right? On the right-hand side, everything looks very similar. Right? There's this overlap term, there's this population term. The only additional piece is that the density matrix elements, the populations and the coherences, are each dependent on the orientation angles, this omega. This omega is all the necessary orientation angles, the Euler angles, if you're familiar with those, right? Okay. So now let's take a closer look at these new density matrix elements, right? The ones in the lab frame. We look at those and we see that inside them are those operators, the angular momentum coherence operators, right? Here's our K, that's the total wave packet angular momentum. And there are several values of K, right? Remember, when you add two quantum mechanic angular momenta, you get several possible values. So all of those are summed over, right? I said we'll forget about Q and S. This guy, this D here, which is a function of the orientation angles, it's just a basis function. It's a basis function on all the sets of orientations. It's very similar to the spherical harmonics. Excuse me. Similar equation for the coherences, right? These A's, right? Notice that all the time dependence is in these A's. All the dynamical information is just in these A's, right? There's no time dependence on these basis functions. It turns out that these guys tell us about the population, because they're the diagonal elements, and also the molecular orientation. So it's the population and the molecular orientation of a particular vibronic state. Okay? This guy, these are now coherences between different electronic and vibrational states. And this actually tells us about the orientation of the coherences. Now that's a weird thing, and I'll talk a little bit more about that. These two functions, the A's as a function of time, they've actually shown up before, specifically in photoionization measurements. And I will talk more about photoionization measurements as well. So let's now think about these two statements a little bit. Essentially, if you look at this, I said this thing here is like a spherical harmonic, right? So this expansion is essentially like a multipole expansion. So these A's should tell you something about the shape of the molecular axis distribution. And these guys should tell you something about the shape of the coherence in the lab frame. What I mean by shape, let's take a closer look. So I said these are kind of like multipole moments. We name them molecular angular distribution moments, whatever, MADMs. You'll see this MADMs show up a few times, that acronym, right? If K is equal to 0, that's like a monopole. What that means is, let's think about just a single electronic state. This is just the population of that electronic state. So if the K is equal to 0, MADM is large, that electronic state has a large population. If the K is equal to 1, MADM is large for a particular electronic state. That's not population, that's just telling you that the population in that state is oriented like a dipole. there are more molecules oriented along the z-axis this way, right, than let's say perpendicular to the z-axis. So this tells you about the orientation in a particular state. K equals 2, if K equals 2 is large, the molecular distribution in that state is aligned. There's no difference between the head and the tail, but the molecular axis is very close to the z-axis. Similarly, there's the octupole and higher moments if we want to consider them. We'll only be looking at 0, 1, and 2 for the rest of the talk. Right? What about coherences? What does it mean for a coherence to be oriented? What that means is, in the lab frame, molecules that happen to be along the z-axis with their head pointed up and their tail pointed down, the coherence will be large for those molecules, which means the electronic dynamics for those molecules will have a large contribution from the coherence, whereas for one oriented perpendicular, that coherence will not be present at all. So in other words, when we start in an isotropic distribution and we resonantly excite a molecule, molecules at different orientations will experience different dynamics. And in a sense, the orientation of the coherence is the lab frame orientation of the electrons. Because these electrons here that are on this molecule, the one that's sitting here, they have the coherence is large and they're sort of zipping around up and down like that. So there's this time varying dipole that's created, right, in the lab frame. Okay, so that's how we can think about this, the multipole moments of both the populations and the coherences. The population case, it's just the orientation of the molecules themselves. The case of the coherence, it's the orientation of the electronic dynamics. Right? All right. A few more things to say about these MADMs. There are selection rules for them. If you excite resonantly the system with a single photon, the K equals 1 is only allowed for coherences between the ground state and the excited state. K equals 0 and K equals 2 are only allowed for coherences between pairs of excited states. Okay, so in other words, the coherences between excited states and excited states, between all the excited states, are only ever going to be aligned, whereas the coherence between the ground and the excited state is going to be oriented. That's going to be a dipole. In fact, this is the dipole that's responsible for resonant absorption, right? It's also the dipole that's responsible for the time-resolved measurements of absorption with XUV and IR pulses, if you're familiar with those. Right? So that's the selection rules, right? K equals 1 and K equals 0 or 2. Another thing to point out is that if we reduce this density matrix over the orientations, meaning we basically integrate over all orientations, we get the vibronic density matrix. The reason I'm pointing it out is because this is the thing that the very first theoretical proposal that I mentioned intended to measure, right? It intended to measure coherences between electronic states reduced over all other degrees of freedom. Right? This turns out to be just the K equals 0, just K equals 0 MADM. In other words, this guy completely rejects ground state, excited state coherences. That dipole that's created, the reduced vibronic density matrix does not see it in the experiment. Right? So if you design an experiment that targets this, you are going to miss any dynamics that come from these kinds of coherences. Right? That's a sort of side effect here, but an important one. All right, so that's all I want to say about these guys, right? Now I want to show you a quick numerical example that illustrates some of these things. And I'm going to use the same molecule that was used in the first, in my motivation. I won't talk a lot about how we do this. I'll just say that I need some raw materials. I need energies of states. I need dipoles. All of those are calculated by my collaborators at the NRC, Simon Neville and Michael Skirman. And so we can use these to calculate some coherences in the lab frame. All right, so here I've shown you for just a particular coherence between the ground state and the first state in my table over there, right? As a function of angle here. These two angles are this angle here, and then the spinning angle of the entire molecule around its own body. As a function of those two angles, you can see how the coherence varies, right? And then as a function of time, so the one that looks oriented is at time equal to 0. The one that looks flat here is at 0.32 femtoseconds later. So let's imagine just the molecule oriented at theta equals 0, chi equals 0. Initially, the coherence is large. In 0.32 femtoseconds, it goes to 0. Then later on, it will go negative and then come back again and then go back up, right? So I can plot all the coherences at one particular angle. So I'm going to do it at this angle, and then in between. And I'm going to keep chi set to 0 just to make life easier, right? All right, so that's on the next slide. There we go. So here is a picture of the coherences. This is the one that I showed you on the previous slide. It starts off high, goes to 0, continues negative, and comes back up. Here's another one that's opposite to it. And here's yet another one that's in between. These guys all together are what's going to give you the final electronic dynamics. Now, if I go to theta equals pi, the exact opposite happens, right? You can see the phase of the dynamics here is delayed, right? This guy starts off high, ends low. This guy starts off low, ends high. So the molecule oriented this way versus the molecule oriented exactly opposite to it, they're going to see different dynamics, but the difference there is just going to be a time delay, right? Whereas one oriented at pi over 2 is going to see something totally different because the three coherences are completely differently phased and have different values. So we can, okay, so this was just these are just coherences between the ground state and the excited state. And you can see that it's oriented, right? It's not aligned, it's oriented. There's more here, there's less there. 0 and pi are different. I have just shown you one coherence between a pair of excited states, and clearly these are aligned, right? 0 and pi are not different now, right? So this is just to demonstrate the concept, right? Now I have some pictures here. This is a molecule at theta equals 0. This is a molecule at theta equals pi. And these blobs that you're seeing are the difference in the charge density between the excited and ground state. And you can see that these two are exactly pi out of phase if you watch for a while. So this is a molecule aligned at theta equals 0. This is a molecule aligned at theta equals pi, and they're just delayed with respect to each other. Then on the right-hand side, if I switch this one to a molecule at theta equals pi over 2, looks totally different. Something else is happening here, right? So this may just seem like something that's really complicated, something that's a bug, right? Because we like to orient the molecule to simplify things, but this looks more complicated. There are different dynamics at every orientation. Actually, it turns out not to be a bug. It turns out to be a feature, provided that we can extract all of this information. Because in fact, if we leave the molecules unoriented, we are exciting a larger set of dynamics, and each set of dynamics is essentially a different initial condition. So if we can figure out a way to pull that information out of the experiment, we're actually getting more from an experiment on unoriented molecules than one on oriented molecules. So we're going to think about how one might do this using a measurement. So I might go a bit quickly now. This is just an example measurement, and this is real data. This is the ammonia molecule. We pump it 160 nanometers resonantly to a particular resonance state. As a function of time, it does what it does. And we probe it by removing an electron. And we go above the ionization threshold, we kick out an electron, and we measure as a function of time delay between the two pulses, the probability that the electron will come out in a certain direction with a certain energy. So here, more electrons come out here, fewer here, more here, right? I can actually unfurl this and just plot it as a function of angle and time. So at 0 degrees, at time equals 0, there are a lot of electrons. At 180 degrees, also there are a lot of electrons. And then this peak as a function of time sort of wobbles around. It does something, so there's something happening, right? This is usually analyzed by doing another multipole expansion. We expand now with spherical harmonics that are functions of the ejection angles. And now, again, the time dynamics of the data are all inside these parameters that are called beta parameters. Let's take a look at those. These are the beta parameters for the experiment. M is equal to 0. I don't want to go into too much about why, but there are only 3 beta parameters that are non-zero. That's with L equals 0, L equals 2, L equals 4, L equals 6, you can see is flat. There's a reason for that, but don't have the time to talk about it. But you can see clearly all three are different. So why are they different? To understand that, we need to do a lot of algebra and a little bit of perturbation theory. And what happens is we see that the beta parameters, in fact, are also built just like the density matrix from these MADMs. That's an interesting thing, because now this provides a connection to the density matrix. So we can perhaps think maybe from the beta parameters, we can pull out these MADMs. And if we can do that, we can get the density matrix as a function of orientation angle, which means we can get all of that information I was talking about. We can figure out for any orientation what the molecular dynamics are, right? I believe if you're in quantum information, you may have heard the word quantum tomography. I believe this is what a quantum tomography is. Okay, so can we do this? Let's go back to the experiment. Let's look at the beta parameters. We first need to be able to connect the L here to K, because these are the things we measure. We want to connect them to this. I'm going to skip this because I'm running short on time. How we connect L to K, it's a slightly long story. But essentially what we see is the beta parameters sort of separate out. The beta parameter with L equal 2 has these frequency components. I just took its Fourier transform, right? And I can calculate using a model of the excited state of ammonia, what frequencies there should be in the K equals 2 MADM for an excited state labeled 1 here. So what this 1 label is the following. Initially, we thought, all right, we're hitting a single resonance state called the B state of ammonia. This actually turns out to be doubly degenerate. It's 2 electronic states sitting on top of each other, but that degeneracy is actually broken. It's split. So this lambda equals +1 and -1 components, they're 2 electronic states. They split into 2. So this is 1 electronic state with a rotational ladder on top. This is another electronic state with a rotational ladder on top. So the electronic states are +1 and -1. So I can have coherences between these. Each of them have a population, and then there's an orientation of molecules in each of them as well. So these frequencies here turn out to be just the rotational dynamics. So the change of the orientation of the molecules as a function of time in one of the states. So here in the state labeled 1, right? And these frequency components match one of the beta parameters, whereas the other beta parameter turns out to have frequency components that match the coherence between the two states 1 and -1, right? So these beta parameters seem to be separating the orientation dynamics and the coherence between the two states. And these are the only relevant MADMs in this case. So it simplifies significantly, right? So essentially what the experiment is telling me is it looks like beta 2.0 is proportional to this guy and beta 4.0 is proportional to the other one. And these are the only two I need here. So I've measured this. I want to get this. I need this piece. This piece is really complicated. This piece contains all the photoionization dynamics. For the experts in the audience, it's built from the ionization dipole matrix elements. Those are very hard to calculate, and they're even harder to measure. But as luck would have it, someone has measured them for exactly this state and for exactly this continuum channel. This is this paper right here. It was Paul Hockett during his PhD, measured all the relevant, a large number of relevant dipole matrix elements that can be used to build these coefficients that sit in front of the MADMs. So if we can build that, we can divide them by the beta parameters, and we can pull out the relevant MADMs. And then this is a theoretical calculation, but we can get experimental versions of the electronic dynamics at any orientation angle. So this is a work in progress. So I can't say much more about it. It's just that going from the ionization dipole matrix elements to these coefficients is a very non-trivial exercise. It's going to take a while, but I believe we can make it work. Okay, so this molecular frame quantum tomography is sort of one result here. The other result I wanted to talk about is going in the opposite direction in a sense.
Dr. Varun,
yes.
Sorry to interrupt you. You have 5 minutes left.
Okay, that's not a problem. So I will skip through this relatively quickly. This is already published, so you can look at the papers if you wish. The idea here is now, suppose we stay in the ground state. We don't excite to upper states, but in the ground state, we kick the molecule and we make a rotational wave packet. What that means is we just produce a superposition of rotational states in the electronic ground state. If we do that, I can actually very accurately compute these guys. And then I'm going to measure these guys. So maybe I can get these guys. What does that tell us? Well, we managed to figure out that there is a connection between the molecular frame beta parameters, which are down here, and the laboratory frame beta parameters, which are the ones we measure. That connection is a matrix equation. So in other words, if I can measure the set of these, I can potentially retrieve the set of these. And this is something we demonstrated in a paper recently. Here at the bottom is a retrieved situation. And this is simulated data. So we didn't actually do the experiment, we simulated the data. And this is the calculated sort of from first principles photoelectron angular. So what these pictures are, this is an ethylene molecule. If we align the laser polarization along the carbon-carbon bond, this tells you the probability of ionization of an electron at a particular relative angle. So if the blob is very large, it's a large probability. If there's a node there, it's a very small probability. So this is doable for molecules with enough symmetry, is really what we learned here. We can get back the molecular frame result. We're going to try to do a similar thing. This is with the collaborators at the Pulse Institute at Stanford. We figured out that the electron or X-ray diffraction intensity also turns out to have the ground state MADMs in there. Now here, this is a very complicated equation. We won't worry about many things. These are scattering angles. So the electron comes in and scatters off the molecule, or the X-ray comes in and scatters off the molecule. Those are measured, right? Those are measured. These I can calculate. So we can get the molecular geometry. Right? In fact, here, this is these states here are vibrational states, and we've assumed they're time independent. But we could also imagine exciting a vibrational wave packet so that there's some vibrational motion. And then we can pull out, the molecular geometry as a function of time. Okay, so that's about all I want to say. So I just want to remind you of the things I said. There are two things that considering rotation really gives us insight into. One is that maybe from measurements, we can get back a density matrix. And this is, I believe, what is called a quantum tomography. The second thing is that we can do the opposite. If we can calculate the MADMs nicely, and we know how they connect to a measurement, we can then pull out information about that particular measurement in the molecular frame. Right, that's essentially all I have to say. So thank you very much for inviting me. It's very nice to be here. I've never been to Ahmedabad. Well, that's not true. I would like to come to Ahmedabad again. I've only been once. And that was actually when I was in school to play music at a wedding. So I didn't really see the city. I just came and I left. But anyway, I'm done. Thank you.
Thank you so much, Dr. Varun, for the wonderful talk. Now I'll take up a few questions. So I begin with the first question, which is that the difference in coherence for different molecular structures, such as linear or symmetric or asymmetric, like, has it been inherently considered? And if so, where? How do they affect the coherence and population?
That's a good question. And it's a complicated issue. So when you say coherence here, I'm assuming you mean the electronic or vibrational coherences. In the case of vibrational coherences, the geometry of the molecule is going to change as a function of time because you've excited a pair of vibrational states or a bunch of vibrational states, right? So it's a little bit difficult to consider what you mean by symmetry or asymmetry there, right? You may have a symmetric molecule and then excite a pair of vibrational states, which breaks that symmetry, right? This is something called Jahn-Teller distortion. And one of the things I'm doing is trying to understand how coherent, what role coherences play in Jahn-Teller distortion. I'm not sure how well studied this is, to be honest. Mostly people think about population transfer when they think about things like this. So that's probably the best answer I can give you. But in general, it's complicated. That's you really have to think about a specific case. Yeah.
Okay. Next, we have a short question. The difference between pi and 0 in the images that you've shown,
Yes.
is it unique for lab frame or molecular frame as well?
So what I've shown you there is the molecular frame, right? This is, so the molecule here is fixed, right? So we're in the molecular frame, but this molecule is at an angle of 0 with respect to the polarization of the pulse that excited the states. Whereas the molecule on the other side is at an angle of pi with respect to the polarization of the pulse that excited the states, right? So this is in the molecular frame. The dynamics in the molecular frame depend on the orientation of the molecule. That's one of the essential things that come out of this considering rotation. Because if you change the orientation of the molecule, it's essentially because if you change the orientation of the molecule, you excite a different set of states completely, right? You have a different initial condition, you'll have different dynamics. I hope that answered the question.
Right. Okay. Okay. It's sort of a different question. So conical intersections sound very similar to Rabi oscillations. Could you comment about the similarity or differences?
That's a slightly hard question. So yes, Rabi oscillations also involve population transfer between a pair of states that are no longer eigenstates of the system because you've put a field on it, right? So in that general sense, I suppose it's the same thing, except here there's no external field on the system, right? The reason this stuff is happening is because for us to understand the geometry of a molecule, we make this approximation. We make this Born-Oppenheimer approximation, right? We separate the electronic state from the state of the nuclei. This is not a thing we should be doing a priori, right? Because those are interacting particles, so they should have a combined quantum state. We are separating them. And then we are using this basis for all our calculations. This is really what's leading to this conical intersection thing, right? That conical intersection is a natural part of the system. There is no external field here.
Okay. Actually, two more questions. So beta 20 and beta 40, are these the only betas that have been measured, or are they, you've just presented the two?
No, that's a good question. Actually, so I skipped, this is the part I skipped. The reason that there is only those two, there's also beta 00. The reason that there are only those three is because of conservation of angular momentum. Remember K, right? For a pair of excited states, which is what we have here, we have two excited states. For a pair of excited states, K, the selection rule for K is it can only be 0 or 2, right? So we've got a wave packet sitting there. It has a 0 or 2 units of angular momentum. And then we ionize it with a photon, right? Photons have 1 unit of angular momentum, but we're squaring it here, right? So you get 0 or 2 for P as well, which is the angular momentum associated with the photon. It's not the photon angular momentum. You have to add these two to get L, right? So if you take 2 plus 2, right, the angular momentum can be 0, 1, 2, 3, or 4, right? That's how quantum angular momentum works, right? You can't have 1 or 3 because our interaction is inversion symmetric. Up and down are the same. 1 and 3 are odd spherical harmonics. So for them, up and down is different. So we can only have 0, 2, or 4 by conservation of momentum. And so you can see 6 is essentially 0, right? That's the reason we extract 6 from the data is a double check that we're not doing any multi-photon excitation.
Okay, now I have one last question for you. So you showed a coherence curve in the beginning, varying as a function of time delay, right? And later you went on to show that the coherence is angle dependent. right? So since the molecules are randomly oriented, you're talking in the most general sense of things.
Yeah.
How do you decouple the two? Would you sort of do some cold trims sort of experiment where you're looking at
Yeah,
essentially that is what I want to ask.
Yeah, I think I understand the question. That's very hard. You could try to do a cold trims experiment. So if you the way I've thought about this is any measurement I do, I want to be able to figure out how to express what I'm measuring in terms of the MADMs. In my mind, that's how I decouple it, right? Because the MADMs are just the time dependent part, right? And then the angle dependent part is just this analytical function. So I know it, right? So if I can do this much theoretical work, legwork, I can separate it. But a cold trims measurement is another way one might think of this, because then you can determine the orientation using the fragments, and you can independently measure the electron as well and do all that as a function of time delay. Hopefully the orientation doesn't change much. You're only considering a small time window. And that would also decouple them in a sense. But then how one would get the density matrix back from that kind of measurement, one has to think more about that.
So when you talked about this, when you showed this coherence curve where it sort of revives and then lies down again, in that particular
that was the motivation paper. Is that what you mean?
Later also you had mentioned in your slide there was like it sharply rises. No, not this one. Later in your slide you had mentioned one particular graph where it rises and then
yeah. I see this guy.
This one.
This guy down here is the electronic coherence. Yes.
Right. Okay.
Yeah.
So is this for a particular theta?
No, this is a lab frame measurement.
Okay.
This is a complete. This is here. This is this beta parameter. So this is a lab frame measurement. We started with an isotropic ensemble, put it in an excited state, right? This excited state, and as a function of time delay, we measured the photoelectron distribution, and we pull out the beta parameters, right? The beta parameters themselves turn out to be superpositions of the MADMs. That's the key bit. The measured beta parameters, there's no orientation. These are measured beta parameters in the lab frame. Because these are superpositions of the MADMs, the concept is so I measure this piece, if I know this piece, I can get this piece. Right? That's the general idea. And once I get that piece, I can get the density matrix.
Okay.
And that's actually a really hard problem, and it involves a lot of work. but basically knowing these coefficients that sit in front here is very difficult. But people who do high resolution photoelectron spectroscopy spend a lot of time figuring out the information needed to construct things like this. And for the particular state that we excited, it happens to have been done already.
Okay. Thank you so much, Dr. Varun. You answered all the questions. That brings us to the end of the first talk. Okay, so now we move on to the next talk, which is by Dr. Anindya Banerjee. Dr. Anindya completed his PhD from Jadavpur University in 2018, wherein he studied the properties of a class of non-Gaussian states. Subsequently, he joined PRL as a postdoctoral fellow in the Quantum Technology Lab under Professor R.P. Singh. He is currently a postdoctoral fellow at the Center for Quantum Technology in National University of Singapore, working in Alexander Link's group. Today, he will be delivering a talk on entanglement distribution through telecom fibers. Over to you, Dr. Anindya. You may now share your slide.
Right. Thank you for that nice introduction. It's always good to come back here. Right. So what I'll be talking about is entanglement distribution through telecom fibers. Sorry to the audience for kind of digressing from the declared theme of this session because of some timing issues. But all right. So I'm Anindya. I'm a postdoc working in CQT under NUS. I'm working with Alexander Ling, who is like an expert in entanglement distribution and satellite missions. The work that I'm talking about here is being performed in collaboration with Wang Wei, who is a CQT PhD student, and Alex, who is the PI of the group. Right, so a very brief outline. I'm going to talk about like what scenario we are trying to address, in which scenario we are talking about this particular distribution of entanglement, and then very shortly on the electromagnetic spectrum and the communication bands which we can use. Then I'm going to talk something about the intermodal dispersion, which comes up whenever you're talking about transmission of light through fibers. There would be some intermodal issues which we need to tackle, and then the experimental setup and the results. Also, disclaimer: I'm a theoretician. I was involved in the theory part. The experiment was done by Wang Wei. So please bear with me if I'm not too good with experimental setups. Please do excuse me for that. Right. So what are the scenario that we try to address in this particular situation? It's very simple. So we're looking at, say, a campus-wide or an establishment-wide network. You have a campus, and today, most of the campuses, at least like even in, mostly I'm concerned with Singapore right now. Here they have existing excellent fiber optic network architecture, which is what we want to use. But in any case, whenever like you're talking about a campus-wide situation, you will have some optical fiber network topology which is there. And one advantage of using these network is that these are relatively short point-to-point connections. Now, there are multiple ways in which you can distribute entangled photons for various purposes. Like if you're talking about secure communication for quantum key distribution, and there's also the quantum internet that's coming up. So like there are various situations where you need to distribute entangled photons. And so it could be free space in which you can have like a free space network, you can have telescopes and all that. You can have, if you want to do it for very long distances, you have to resort to satellite-based communications. And if it's for a short network, we can use the existing fiber network. So this is kind of the situation what we are trying to address. So suppose you have a central facility which houses your source, and then all these buildings in your campus are connected through telecom fibers. Now, why telecom fibers? Because these are the most popular fibers that you find. Most of our data are carried by the fibers, and the specification is probably G562D as per ITU specifications, which are single mode fibers for telecom wavelengths. And then you can have a central source that sends the photons between these buildings, whoever wants to communicate with each other. And this is what we are trying to do. Now, let's briefly talk about the spectrum. So the electromagnetic spectrum, there are various bands of communication. The original band was the O band. It's the oldest one to start with. And there are various bands. You have the O band, E band, S band, but the most conventional band right now is the C band over here, which is between 1530 to 1565, which is most commonly used. One of the reasons for common use of this band is that the losses are very less. The fiber losses in this band is quite less. So that's one of the reasons why this is used. So if you look at the fiber loss, then this is how it goes with wavelength. This is in dB per kilometers. So your O band has lesser loss compared to the bands over here, or the 850 nanometer band, which is marked over here. And then the C bands are even better for long distance transmission. So why not do it for telecom bands, right? So the obvious point can be that, okay, we can generate the entangled photons in these particular bands, say 1310 or 1550 nanometers, and then use them for your communication. But there's a problem. And the problem is, sorry, before I go to the problem, so essentially we get like 3 windows for, when we talk about fiber communication, we get essentially 3 windows. One is at the 850 nanometers, below which you will have scattering, which is not usable. And then there's a window at 1.3 or the 1310 nanometer window. And there's also the 1550 nanometer window, which can be used. Now, the problem is, if you go to these higher wavelengths, the detectors, like the in-gas APD detectors, they are not very efficient. They have like around 15% efficiency around the central wavelengths, which is a problem. Now, compared to the 850 nanometer, this is much easier in the sense that you have quite efficient silicon APDs in this range of wavelength. So the point is, all right, if we want to, because we're talking about quite short distances here, and if you look at the losses, 850 nanometer, it has a loss around 3 dB per kilometer for the telecom fibers. And the 1550 nanometer, it suffers a loss of about 0.22 decibels per kilometer. So the 850 nanometer suffers quite a higher loss. But when you look at the detectors with which you detect these photons, you would see that generally for around 2 to 3 kilometer length of fibers, the 850 nanometer actually outperforms when compared to the 1550 nanometer photons. So that's one of the reasons why we're trying to distribute entanglement using wavelengths around 800 nanometers through telecom fibers. So that's one of the reasons. Obviously, you can go to SNSPDs, which are nanowire detectors, which are quite efficient, but the problem is they're super bulky, they're very expensive, and they also have to be cryogenically cooled, which just drives up your cost. So if you're looking at a cost-effective way of distributing entangled photons in a campus-wide situation, one option could be using the 850 nanometer window, which would be better when compared to the 1550 window. So that's like, with that, we come to the problem statement, which is we want to distribute near IR entangled photons through telecom fibers. Now, it's easier said than done. And the reason is there's a big problem. The problem is that telecom fibers are not really single mode in these wavelengths. Because when we talk about these fibers in the telecom wavelength, there's something called a V number for fibers. And this V number actually tells you whether a fiber is single mode or a multi-mode. It tells you how many modes the fiber can support. Now, for the 1550 wavelength, these fibers that we aim to use, these are single mode, so you have pretty good transmission. But it's not that for the 800 nanometer bandwidth. And so what happens is, what does it mean when I say that it's not a single mode? Now, when I say it's not a single mode, that means that these fibers, when you try to put in these 800 nanometer photons through these fibers, multiple modes are excited. So for our case, for the G562D fiber, if you use around 810 nanometer photons, it comes around, the V number comes to something around 4. So around 4 modes are supported by these fibers. Now, the graph on the left that you see here, it tells you the normalized propagation constant. Now, each of these modes will have different propagation constants, which means that they will experience different root delays. And that means that each of these modes will be separated when they are passing through the fiber. And the delay between modes, when calculated, comes to something around, so for the LP01 is the fundamental. The first excited mode is the LP11, and the delay between them is about 2 nanoseconds per kilometer. For the LP21 and LP01, it comes to something around 3.4 nanoseconds per kilometer. And for this is about 0.8 nanoseconds per kilometer. So what this means that when you inject these photons into your telecom fiber, different modes, like these 4 modes, can be excited. And what will happen is, when you collect these photons out at the end of your transmission length, you don't exactly know when these photons will arrive. There would be these photons, these modes would be distinctly separated, which means that you need a lot of filtering to actually collect these photons. And because there are higher modes present now, they will also affect the quality of entanglement. It will distort the entanglement. Why does that happen? Because when each of these modes travel through the length of your fiber, they will experience some rotation of their polarization vector. Now, each of these modes will experience different rotation of the polarization. Now, there are devices called polarization controllers with which you can bring the polarization state back to the initial state that was there before the transmission started. But the polarization controllers cannot work equally well for all the modes. So you can correct for the fundamental mode, but you cannot correct exactly for the higher modes. So since the LP01 is the fundamental mode, using polarization controller, you can correct the rotation for LP01, but your signal for LP11, 02, and 21 will be scattered. What that means is that the polarization that you detect at the end of transmission would be different, which will lead to higher quantum bit error rate, scrambling your information, and it wouldn't be much useful. So how does this manifest? So this is essentially the setup that we had. So it's an asymmetric distribution of entangled photons. What do I mean by asymmetric distribution? I essentially mean that there could be two situations, right? So either you have your source close to you, and you just want to transfer one of the photons to some other party, right? So what happens is you can have like this signal arm. You can have it with, in your lab, so you can couple it through the 810 nanometer, which is a single mode for this wavelength, and you can transfer the other one through a telecom fiber, which is the network which is already there. So this is an asymmetric situation, or rather one of the asymmetric situations. The other asymmetric situation is you have telecom fibers on both the arms, but in this case, you have different lengths of the fibers. So they could be like, this one could be shorter, this one could be longer, or vice versa. So these could be the two asymmetric situations, very practical. And this is the source that we had. So this source has been developed here, and so they have very interesting names for this. This is called a PAPA, or the PAPA. So it's like a parallel axis. So you pump with your laser 405, and then you rotate it to diagonal polarization. You have a nonlinear crystal for phase compensation. And in this first crystal, because of birefringence, these separates into the orthogonal polarizations H and V. And then you can have a half-wave plate. So the H is again transformed back to V. So you have two vertically polarized photons entering your PPKTP crystal. And then both of these, it's a type 0 phase match crystal. So V will produce two signal idler, again in V polarization or vertically polarized. On the lower arm, you put another half-wave plate, you rotate it back to horizontal, and then the vertical comes from here, the horizontal goes there, they're matched along the same path. You use another crystal to compensate for the phase delays. The dichroic mirror here is used to separate the pump, and then the signal and idler are brought here, and then there's wavelength division multiplexing, and then you send them over here. So this is the basic setup that we had, and these are the results. So so when I talk about the asymmetric situation, so when we send just one of the arms has a telecom fiber, the other one has a 810 nanometer fiber, what happens is when you have a very short distance transmission, say of the order of 1 kilometer, this is the cross correlation measurement or the temporal correlation. So you see that there's already kind of a spread over here. So when you increase your timing resolution from 1 nanosecond, you go to about 0.5 nanoseconds, you can see these peaks slowly appearing. So this is the sense of the fundamental mode. In 1 kilometer and 1 nanosecond window, the higher order modes are not that evident, but you can see these peaks over here, which slowly start separating from the principal when you look at it with a better timing resolution. Now, when the distance increases, when you're transmitting through 5 kilometers, you can see this difference very clearly. You have this is for the LP01, and then with delays, you have around one, this is the LP11 mode, and this is the LP21 mode, and they are completely separated. What this means is that you can collect from here, but it is these photons that will drive up your tuber, that in turn will affect your entanglement visibility, right? So, and what's the delay? The delay is like as we calculated. So this is like we thought that it would be around 2 nanoseconds per kilometer. So over 5 kilometers, we get around 10 nanosecond delay between the LP11 and LP01. For the LP21 and 01, it was about 3 nanoseconds per kilometer. So it was like around 15 to 18 is what we get. So like each of these modes separate out. When you increase the timing resolution, the reason for looking at it with a better timing resolution was to see that, okay, can we get the higher modes? Are they there? But for these delays, we didn't see the higher modes appearing. It was mostly these three modes, the 0, 1, 1, 1, and 2, 1 modes that we had. So now we wanted to see that because of the separation on passing through the fiber, what happens to the entanglement, right? Sorry, before I go there, so this was for the asymmetric condition where we had like one telecom fiber in one arm and the other arm was coupled to a 810 nanometer fiber. And then we can also have another condition where we had different lengths of telecom fibers in each of these arms. Now with 1 nanosecond coincidence window, you can see that this is fairly broad. So this was for the signal. It had on one arm we had a 2 kilometer fiber, on the other arm we had a 1 kilometer fiber. It was fairly broad, and these are symmetric. It doesn't really change if you just interchange a signal either. And then when you increase the timing resolution, you can see these peaks slowly appearing over here. So you have to collect over a very long time, and if you have a very narrow temporal window, you can still collect these photons. But the problem is you will miss a lot of the photons. So your rates are going to go down, right? So now what happens to the entanglement? All right. So when we have again, for this, we have 1 kilometer on one arm, 2 kilometer on one arm, and the other has an 810 nanometer. So I'll keep coming back and forth. It's still the asymmetric situation. So without filtering, we get about, when I say without filtering, I mean that there is no spatial filtering, there is no temporal filtering. Without that, after 1 kilometer, we have about 82% visibility. After 2 kilometers, the visibility reduces, it's about 78%. Now, these visibilities can be increased a bit by using spatial and temporal filtering. So for temporal filtering, what you do is you use a shorter coincidence window, you make your coincidence window much narrower. So maybe of the order of, say, picoseconds, you make it that narrow, and then you collect your photons. It does give you better entanglement. And we can also do spatial filtering. What that means is that after you transmit, when you collect these APDs, you connect 810 nanometer fibers, so this is a fiber coupled. And what this does is that it will filter out only the 810 nano, only the principal or the fundamental mode, the LP01 modes, and then you look at the entanglement between these two. So using spatial filtering, we have better visibility, about 83%. The temporal filtering, it's about 82%. So so this is after 2 kilometers, right? So after 2 kilometers without filtering, we had about 78. And when you do the spatial and the temporal filtering, you can increase your visibility to about 83 and 82%. But these are still not that good, right? We can do it better, probably, but let's just wait for that. So that's a question that we'll be addressing, that can these visibilities be increased? But before that, let's look at the symmetric distribution. Now, when I say symmetric distribution, we have equal lengths of fibers on both the arms, right? So as you see, when you do that, so when you have a 1 kilometer long fiber on both arms, and you have 1 nanosecond, it's really wide, and you cannot really separate out the fundamental from the higher modes. They're pretty much mixed. It's pretty much the same. With a better temporal resolution of 100 picoseconds, you can slowly see these peaks appearing, but still they're pretty much overlapped, and you cannot really separate them out. You can use better temporal resolution, but then you're losing a lot of the photons over here and here, and that is going to keep your rates really low. When you increase your distance of transmission about 2 kilometers, then a lot of the photons end up in your higher modes, and now they are fairly separated. But the problem is when you look at the distribution between the fundamental and the higher order modes, they're pretty high. So this ratio is pretty high, which you don't want it to be that way. You want most of your photons to be in the fundamental mode if you're going to use some kind of a spatial filtering. Now, the effect of this overlap on entanglement is drastic. The visibility goes down to 52%, which is completely unusable. Again, this is without filtering, but visibility is really low and it cannot be used. So the degenerate photons under the symmetric condition, they perform really bad, and this simply does not work. Okay, so what could be the saving grace? Is there a way out of this? Probably yes. So what we can do is we can move to non-degenerate photons under, again, the same symmetric and asymmetric distribution. Now, if you remember the previous graphs, at least we can just look at this. So this is on the left, where you see this cross-correlation graphs. This is for symmetric distribution of degenerate photons. And when you look here, which is the symmetric distribution of the non-degenerate photons, we see something really interesting. We see that it's most of the fundamental that is being excited over here, and very little of some other mode that comes in. But this ratio, it's really nice because most of the photons are now here in the fundamental and very little over there. So if we use very nice coincidence window, like a very short one, we will still end up getting quite a lot of the signal out of it with very little losses, which is really nice, and which was kind of counterintuitive at first. And on the left, this is for the asymmetric situation where we had telecom fibers in one arm and telecom fibers of different lengths in each of the arms. But when you look at all of them, the good thing that we see is that the higher order modes are almost absent in these cases. So the non-degenerate photons perform much better in these situations. Now, why is that? The reason is the wavelengths that we had was about 850 nanometers for the signal and about 784 for the idler. And in these, because these wavelengths are different and they're traveling through different fibers, the modes that they excite are quite different. And the intermodal dispersion, what it does is it completely destroys the higher order correlation. So you almost none of these, the higher order photons or the higher modes reach the end of the fiber. They are dispersed within the fibers itself, and we end up getting much better signal at the end of these fibers. Now, obviously, as you can guess from here, we will end up having better entanglement. So we actually see that without any filtering, after 1 kilometer, we had a visibility of around 90%. After 2 kilometers, it was 89%. But after 6 kilometers, we had fantastic visibility of 85%. Again, all of these are without any filtering. We have also checked, which is not included in the slides here, but we have also checked for 6 kilometer fiber. So this is for the asymmetric, where we have only one 6 kilometer fiber in one arm. The other one has an 810 nanometer fiber. So with that, we get around 85%. And when we tried doing it with 6 kilometer fibers on either side, so over a total distance of 12 kilometers, we still ended up getting fairly high entanglement. And with filtering, we had more than 90% visibility, which was really nice. And it's kind of what we're trying to show is that that when you use non-degenerate photons, they perform much better in these kind of situations. So as you move from degenerate to non-degenerate, your visibility increases from 52% to around 85%. So this is for 2 kilometers. This is also for 2 kilometers. There's a difference. Yeah, so this is also for 2 kilometers, but the visibilities are pretty high. So the non-degenerate photons, they hardly excite any of the higher order modes. And even if they excite some higher order modes, it is because these are different fibers, they do not end up, they are dispersed within the fiber itself, and they do not end up reaching the detectors. So, which means that we end up having way better entanglement than we really expected. So that is all that I had actually. The reason was this was prepared for a 20 minutes talk, and then I was asked for 30 minutes. But I'll just continue saying a few more points, right? So the question is, can we further increase the visibility? Now, probably we can, and that is what we are currently working on. It's something very interesting. It's called a fiber piano. And what it does is that we can actually control the geometry of the fibers itself. And when I say that we can control the geometry, we have a feedback loop. And with this feedback loop, we can actually control the geometry, and we can control which of the modes are actually excited within the fiber. And that is what we will be using later on, because one thing that we want to check is that when we look at these plots actually, so when these appear here, it's because like so three modes were excited, right? LP01, LP11, and LP21. So the central maxima that we have that arrives with 0 delay, it is the LP01 on both the arms, but it also contains the LP11 and LP21 from both the arms within this, right? And this peak appears because of LP11 and LP21, and this is for the other case. So you can like, it's a mix and match, right? So that's why we have like one peak over here, the other peak over here. But in this one itself, we have the fundamental modes. We also have the excited modes and from each of the fibers. So LP11 and LP21 from both fibers will also arrive at the same point with 0 delay. This also affects the entanglement. The reason for using this fancy thing called fiber piano is that we want to control the modes in a way that we can convert this LP11 and LP21 as well to the LP01 mode itself. If we can do that with the polarization controllers at the output, we can get much better entanglement visibility. That is something that we expect, and that is something we are still kind of working on. But right, so I guess I'll stop over there. Thank you.
Oh, sorry. Sorry, my mic was on mute. So I'm going to take a few questions for you.
Sure.
What was the coupling efficiency of these experiments? Is your first question.
Right. Coupling efficiency for the system overall, it was around, I think the total it came out to 20 to 30%, not more than that.
Okay. The next question is, using a QQH setup at the fiber output, can't we improve the visibility further?
You can, yes, but then it works, like I said, if you're using a single mode fiber. If you're using a multi-mode fiber, or like in this case, for 810 nanometer, the telecom fibers are few mode fibers. They have a fiber core of around 10 microns. And with that, what happens is you also end up exciting some of the higher order modes. So using QHQ, you can control the polarization, or you can rotate it back for the fundamental, but it's almost impossible to find a setup that works for all the modes. So that's why it's not going to work when you are just using when it's a few mode fiber and you end up having the excited modes.
Right. So what's the coincidence window here?
For these plots on the screen right now, they were all 1 nanosecond.
Okay. Okay. The next question is, can we model this setup and compare with experimental results?
These all are experimental results.
Oh, right. Okay. Okay, so that was the last question. Dr. Anindya, thank you so much for joining us. Thank you for the wonderful talk.
You're welcome.
Okay, so with this, we move on to the first student talk of this session by Mr. Sunil Dahiya. He's a PhD student at ISER Mohali, working under the supervision of Professor Kamal Singh. The title of his talk today is Ultra-Thin Delay Line for Attosecond Delay Control and High Harmonic Generation. Over to you, Sunil. You may now share your slides.
Okay, thank you, Pranav. Just wait for.
Yes, Sunil, we can see your slides.
Just a minute. My slide. Just a minute, sorry for the delay.
No problem.
Cannot see my. Okay. Okay. Can you see my presentation right now? And
Yes, we can. You can try going full screen.
okay, it's the slides are moving, right?
Not right now.
Okay, let me do it once again.
Okay.
Now you can see the slides moving.
Yes, yes. Now it's fine.
Yes.
Now it's working
That's
perfectly.
fine. Okay, okay,
You can begin.
okay. I can start now. So, good morning, all. I thank the organizers for giving me an opportunity for this student's talk. Actually, I work as a senior research fellow in femtosecond laser lab, NICER Mohali, under the supervision of Dr. Kamal P. Singh. The title of my talk is Ultra Thin Delay Line for Attosecond Delay Control in High Harmonic Generation. In the outline, I'll systematically talk about the various ultra-fast phenomena and their timescales. I'll give the introduction to high harmonic generation. Then I'll talk about the details of attosecond pulse generation setup at ICER Mohali. Then I'll talk about our attosecond ultra-thin delay line, its design and working principle, its calibration and resolution and stability. And then we used this delay line for IR delay control in high harmonic generation. And last, I'll talk about the future perspective for this delay line. So starting with various ultra-fast phenomena and their timescales, molecular dynamics phenomena such as chemical reaction, dissociation, vibration, rotation, they occur at a timescale of femtosecond. While the electron dynamics phenomena such as excitation, electronic transition, tunneling annihilation, HHG, etc., they occur at a timescale of attosecond. Further going, nuclear dynamics phenomena such as collision, fusion, they occur at femtosecond timescale. Now the main question arises, why do we need these attosecond pulses? So the answer is to observe, understand, and control the ultra-fast electron dynamics in atoms, molecules, and solids. There are various methods of generation of these attosecond pulses, such as high harmonic generation, X-ray field emission laser, etc. The most common method is high harmonic generation, and I'll talk about it more in detail in my PPT. So starting with, again, the high harmonic generation is a non-linear light matter interaction phenomena, which gives or which provides us a coherent light source in XUV or soft X-ray regime for attosecond pulses. So in this phenomena, the highly intense femtosecond pulses interact with the gaseous atoms. That leads to the generation of odd order harmonics such as 3 omega, 5 omega. Then these XUV pulses generated from each atom superimposed with each other, that leads to generation of a coherent XUV attosecond radiation that acts as a laser light. So microscopically, this phenomena can be understood via three-step model. In the first step, the annihilation of the electron occur. This is shown below in this figure. In the first step, the annihilation of the electron occurs via tunneling phenomena. This occurs due to high magnitude electric field of the femtosecond laser tilts the Coulomb potential of the atom in one direction. The second step is the acceleration of the electron, and it gains kinetic energy in the medium. And the third step is when the electric field sign changes, this electron comes back to the parent ion, recombine, and then generate the higher energetic photon that leads to this generates the higher energetic photon Then the incident one. So here in the graph, in the graph B, high harmonic generation spectrum is shown, which is our experimental observable. These harmonics are separated by 2 omega frequency. This is because that XUV, each XUV pulse is generated at a half the period of optical pulse of the IR pulse. Then the Fourier transform of these windowed harmonics, assuming that they are in phase, that leads to the attosecond pulse train envelope. Here, the high harmonic generation phenomena helps us in broadening the spectrum of the coherent pulses that actually leads to attosecond pulses in time domain. So this is the brief description of high harmonic generation. So then to realize this phenomena, we have developed a attosecond pulse generation setup at IISER Mohali. In the top left corner, we can see the 3D design of our custom built setup, which is comprised of 3 main components. One is HHG chamber, second is sample chamber, and the last is the detection part. In the HHG chamber, we can see the figure below. Here, these highly intense focused femtosecond pulses drilled a hole through a stainless steel containing argon gas, and here the high harmonic generation occurs. Then, as you can see on the right top corner, the schematic of this setup. These generated harmonics then again focus to the sample chamber via toroidal mirror. These harmonics can be spectrally resolved via spherical grating on a multi-channel plate detector. Then in the figure B below, we can see the spectrally resolved harmonics on a phosphorus screen, and the line profile of them gives us the figure C. Here we can calibrate these harmonics using aluminum filter transmission curve. Using this aluminum filter, or by this aluminum filter, the lower order of harmonics less than harmonic 11 are cut off. So for this purpose, for getting these harmonics up to order of 29, we use, or we have the parameters of our femtosecond pulse of about central wavelength 800 nanometer. Its pulse width was 25 femtosecond, and we used an input power of femtosecond pulses of about 2.9 watt only. So with this successful generation of high harmonics, we had the objectives. The objectives are the temporal measurement of attosecond pulses and attosecond pump probe spectroscopy. So for these objectives, we require optical delay lines with attosecond resolution and attosecond stability. Already there are a number of delay lines exist, and they can be categorized into 2. The first one is amplitude split, and the another is wavefront split. Michelson interferometer, Mach-Zehnder interferometer, they're on these interferometer based, these amplitude split delay lines are, these amplitude split delay lines exist. They offers good resolution. However, they lack of stability. For that, they need active stabilization. So below, there is an example of Mach-Zehnder interferometer based delay line here. So then, in order to get rid of active stabilization, people come up with the wavefront split delay lines. For example, annular hole mirror based or split mirror based delay line. They offer good stability with passive stabilization. However, they're complex setup, and they need specialized optics and fabrication for that. Below in the figure, it is an example of annular hole mirror based delay line. Then with these limitations, we had a motivation of designing a new delay line, which should be simple, compact, with attosecond delay step resolution. It should be highly stable without any active stabilization, and it would be beneficial that if this delay line will give us absolute time zero reference. So with these motivation in our mind, we come up with a design which is wavefront split based phenomena. So we used ultra thin glass plates of 140 micrometer thickness for this purpose, as shown below. So optical delay between the two arms here can be precisely controlled using the rotation of the lower glass plate via motorized stage. The corresponding femtosecond fringes are shown below, which shows the minima and the maxima position. So this delay line have a number of features. One of them is common path configuration, which helps us in getting higher stability. Another is it is a dispersion balance as the both arms passes through the identical glass plates. It shows a number of characteristics. Some of them are that it provides us around 2.5 attosecond time delay resolution. It gives us around 2 attosecond stability. It provides us attosecond absolute time zero delay reference. And it also offers negligible pulse width broadening. So next part is the calibration, resolution, and stability of a delay line are the important aspects. At the graph in the top left corner, so in this graph, the evolution of femtosecond fringes with the angular rotation of the glass are shown. In this graph, the maximum intensity point of the nonlinear fringe evolution and the invergence symmetry at parallel configuration of glass plates gives us the absolute zero delay reference here. Then this angular rotation axis is changed into the time delay axis in the graph below. This can be done via the equation on the top right corner. Here, I should emphasize that our delay line is self-calibrated, as these femtosecond fringes follows 2 femtosecond periodicity automatically, corresponding to 800 nanometer of the central wavelength. So on the right-hand side, the graphical representation of this equation is shown below, and the time delay curve follows the theta square dependence. Here, the nonlinear feature of this curve helps us in attaining higher resolution in time delay step of about 2.5 attosecond at 1 degree. However, this time delay step will increase as we go on higher order or as we go on higher angle. Also, one can increase this resolution with more thinner glasses. Then talking about our stability, we have analyzed the difference between fringe intensity and the laser intensity. And we found out it was to be around 2 attosecond. And this high stability was due to our common path configuration. So we have calibrated, we have found out it's a highly resolved in time delay step, and it provides us a very high stability regarding path fluctuation. So with all these things, we used our ultra-thin delay line for IR delay control in high harmonic generation. As shown in the schematic, we have put our delay line in front of femtosecond beam without deviating its direction. So with this delay line, we have observed the variation of harmonics and with the IR delay. Then the intensity of the harmonic 17 is tracked as shown in the graph below. This intensity of the harmonic 17 follows the periodicity of 2.7 femtosecond. That is similar to the fundamental pulse actually. And from this graph also, we can also see that there are attosecond periodic oscillations, which shows that our attosecond, or which shows that our ultra-thin delay line is capable of showing attosecond resolve measurement. At last, in conclusion, I will talk. I will say that we have designed and realized an ultra-thin optical delay line, which can give us delay step of up to 2.5 attosecond. It provides us absolute time zero convenience. It is highly stable regarding path fluctuation. And to perform or to check its performance, we used it in double IR pulse delay experiment, showing attosecond resolve measurements. In the future perspective, we envision our delay line for the application in XV IR attosecond delay experiments. At last, I would like to thank my supervisor and my colleagues for guidance and support. I also acknowledge ISER Mohali for research facilities and DST Max Plan for research funding. Thank you all. Thank you all for listening.
Thank you, Sunil, for your talk. I'll take now a few questions for you. Okay, so what was your per pulse energy for a particular harmonic? Let's say for the 17th harmonic, what was the per pulse energy?
Per pulse energy, as shown in the slide before, it was we took around, you can say, 0.9 millijoule. Yeah.
Right. So
yeah,
that is
0.9 millijoule. This is the incident femtosecond pulses energy.
Right.
So
and
our system
what was the output energy?
So output energy, actually high harmonic generation phenomena is a highly non-efficient in that sense, and we can say that about 10 to the power minus 6 order of efficiency decreases as we capture these harmonics. So we assume that it should be in nanojoule energy. These harmonics should be in a nanojoule.
You talked about attosecond pulses, but have you done some sort of characterization, or is this simply a Fourier transform of the frequency spectrum that you see?
So actually that was a theoretical slide which gives us that if these harmonics are all in phase, that gives the Fourier transform of them that can give us attosecond pulses, the train of pulses. However, in experimentally, actually we are yet to characterize these pulses. We are at a stage we are making to make it possible. So the phases of these harmonics, determining these phases of the harmonics is a challenge, and for this challenge or for this measurement, we need with these attosecond resolved delay lines. So we are working on that right now.
Okay, Sunil, my final question would be targeted towards a slide that you show, in which the fringes that you showed, you told us that it sort of acts like a self-calibrating system.
Okay.
But let's say, for example, when we typically do our two-color experiments, we usually pay a great deal of attention to ensure that the phase matching between the two beams, let's say 800 and 400, is zero, for which one of the processes that we use is a third harmonic crystal or a third harmonic generation process.
Okay.
In this particular setup, when you say, what do you call your absolute zero? How do you know the two beams that are passing through the upper and the lower sections of your glass plate, they are aligned?
So these fringes in the as you see in the graph, these femtosecond fringes evolution. So they follows the inversion symmetry at the position when these two glasses are parallel in configuration. So that inversion symmetry and the maximum intensity point, that gives us exact position where is my absolute zero delay reference. So it is one of the way that we can say that this delay line can provide us that absolute zero delay convenience in that sense.
Sunil, actually, I have two more questions from you.
Okay.
For you. So the first question is, how are you measuring the time delay versus intensity graph?
Time delay versus intensity graph. So in this slide, as this femtosecond pulses goes through this ultra thin delay line, we have put up a screen and we captured these fringes through a camera. By intensity tracking of that video, we have this evolution of the femtosecond fringes. It is a direct method mostly. We can use a photodiode too.
Okay. The next question is, please explain how phase matching here in gas jet is different from phase matching in bulk crystal experiments.
Okay. Here the phase matching is an important phenomenon that gives us how much order of harmonics you can get. So it is an important phenomena here macroscopically. These XUV pulses generated from each atoms, they superimpose in that sense that if they highly matched in phase, that we can have a shortest, you can say the shortest pulse in attosecond regime. However, in the bulk part, I'm actually not sure about. I'm working in the gaseous phase only. Sorry for that. I'm not sure about the solid part.
That's quite all right, Sunil. Thank you so much for your talk.
Yeah, welcome.
Okay, so now we move on to our next student speaker, who is Miss Diksha. She's a PhD student at IIT Kanpur, working under the supervision of Professor R. Vijaya. The title of her talk is Optical Bistability, its Mechanism and Control in Erbium-Doped Fiber Ring Laser. Over to you, Diksha. You may now share your slides.
Thank you, sir. Is the slides visible?
Yes, they're visible.
Okay, so hello everyone. I will be talking about optical bistability, its mechanism, and control in erbium-doped fiber ring laser. This will be the outline of my talk. I will first give a brief introduction of erbium-doped fiber ring laser. Then I will introduce the optical bistability, its mechanism, its control, and then I will try to summarize. So erbium-doped fiber ring laser is a fiber laser which utilizes erbium-doped fiber as its gain medium. Its length can vary up to a few meters to several of tens of meters. And then we use a 980 nanometer laser diode to pump the EDFRL, and the feedback mechanism is provided with the help of wavelength division multiplexer and a 99:1 coupler. And then there is an isolator also in the cavity to make it unidirectional. And then we have an optical spectrum analyzer to record the output. So erbium-doped fiber makes this laser to be a tunable laser and the wavelengths lie in the range of C in the L bands. This is because its emission has a very broad spectrum as shown here by its amplified spontaneous emission spectrum. This is recorded for a 36-meter long ETF, which ranges from around 1530 to 1600 nanometers. And it is shown at various levels of pump power at the 980 nanometer. And when we give the feedback mechanism, make the laser out of this EDF, we get the lasing at around 1590 nanometers for a 36-meter long EDF in the cavity. So basically, what is optical bistability? When we have a range of input and when we get two stable output states for the same range of input, that is basically bistability. And we can get this bistability out of our erbium-doped fiber ring laser ETFRL under suitable conditions. For example, we need to have some optimum length for it. What is the lasing wavelength? What is the concentration of the erbium-doped fiber which has been used? And what is the feedback ratio, etc., which we will be discussing later on. And how do we characterize or obtain this bistability in the output of our fiber laser? So what do? We record the output power while increasing the pump, and then again record the power while decreasing the pump power. And then when we combine these two, we get a hysteresis kind of characteristics in its output versus pump power plot. So this is basically optical bistability. For the pump power range between A to B, we have two stable output states depending on the initial condition, that whether we are increasing the pump or decreasing the pump. Now, what is the basic mechanism behind achieving this bistability in an EDFRL? So the first requirement for this is the long length of gain medium. Why? Because when we have a long length of EDF in our fiber laser cavity, then when we pump it, the end section does not receive the adequate pump power which is required to do the pumping process and do the population inversion. So what happens, this end section of our gain medium or the EDF becomes absorptive in nature rather than being emissive. So what happens, it starts absorbing the emissions from the front section of the gain medium. So by nature of EDF, it starts acting as a saturable absorber. What is saturable absorber? The absorber of the gain medium or the active medium will reduce as the input power increases. And what is input power here? The emission from the front section, which is at the lasing wavelengths. So this creates two initial conditions. One is different while increasing the pump from lower value to a higher value. The another is while decreasing the pump from a higher value to the lower value. While increasing the pump, what is happening? The population inversion is taking place in the front side. With the increase in the pump, the emission is also increasing. But here there is an absence of pump, and the emission which is increasing at this stage, it is spontaneous emission, but with the help of a cavity and the round trips, it is converting into the stimulated emission, which is growing with the pump power. As a result, the emission is somewhat absorbed over here, and we get some output threshold, after which we will start getting the laser output out of our fiber laser. This is while increasing the pump. Now, from this high value of the pump, when we decrease it again back to a smaller value, the laser cavity already has the high or large power which is circulating inside the cavity. The absorption in this section is already almost saturated because there is a lot of power. So this absorption is saturated and already we have a large power. So while decreasing the pump, even below the threshold, we still get the lasing because there is already large power in the cavity. And at some point, when we continue decreasing the pump, the gain of the laser will cross below the cavity losses and we will get another down threshold. So there will be two thresholds in this bistable laser. One while increasing the pump, there will be an up threshold, and the other will be while decreasing. So this difference between the two thresholds creates a region of bistability. Now we have carried out some experiments also. So we have constructed this EDFRL. The additional component which we have added here is a tunable filter so as to control the feedback wavelength which we are providing. And this is the output spectrum of this laser when we have kept the pump power to be constant at 60 milliwatts. So setting the tunable filter at different central wavelengths, this is the output spectrum ranging from 1540 to 1560 nanometers. So first we have kept the central wavelength of this tunable filter to be fixed at 1545 nanometers and change the length of the gain medium which we are using. So when we used 11 meters of EDF, we are getting the output while increasing and decreasing the magenta and the blue to overlap with each other. So both the thresholds are overlapping. So in this case, there is no bistability. And then when we increase the length to 15.6 meter, again, there is no bistability. But when we increase the length up to 25 meters, we are getting two different thresholds. The magenta one while increasing and the blue one while decreasing. So there is this down threshold, up threshold, and the difference is around 3.5 milliwatts. So we say that the bistable region is around 3.5 milliwatts for the length of 25 meter EDF at the wavelength of 1545 nanometers. Now, next, we have kept the length to be constant and changed the central wavelength of this tunable filter. So at the central wavelength of 1545 for the length of 25 meters, this is same as this, we are getting some bistability. And then when we change the central wavelength of this filter to be 1550 nanometers, we see that there is a decrease in the width of the bistability. It is reduced from 3.5 to 2.6, and then changing it to 1560, the bistability becomes even narrower. So we conclude that while increasing the length of the EDF, we get the bistability, and as we further increase the length, the bistability becomes broader, which will be shown in the next slide. And when we change the tunable filter central wavelength, so bistability is broader at the shorter wavelength side than at the longer wavelength side. So we carried out the same experiment for the length of 36 meter also, ranging from the wavelength to 40 1540 to 1560 nanometers. The in-between values have been presented by this table. And we see that for an increased length of 36 meters, we also get a broader bistability as compared to 25 meters. Now, all these experiments or the results were recorded with the help of a spectrum analyzer. We can also use a power meter so as to have the linear relation between the output and the pump power. So we see that while increasing the pump, this is the magenta line, after a threshold, we see a rise and then the linear increase of the output with respect to pump. And then while reducing, while reducing the pump, there is another path which is followed, and then we create another threshold. So like this, in this also, we can view the bistability in the linear range also. So this is at the case for 36 meter. This is also 36, this is also 36, the same wavelength and the same wavelength. But this is recorded with spectrum analyzer, this is recorded with power meter. Why we recorded with power meter also? Because we wanted to see the characteristic, the laser output characteristics. So what the noble thing we observed over here, for example, if we have a shorter length of the EDF in our cavity, then and we have already seen that there is no bistability in that. So it follows the standard output characteristics of the laser curve, which is when we increase the pump, there is one threshold and then the power gradually increases. But as we have sufficiently increased the length of the EDF of the gain medium to be 36 meters, then what do we see? After the threshold, it has a sudden hike in the output, and then the linear increment of the output takes place with the pump power. So this sudden hike just after the threshold is because of the long lengths of gain medium in the cavity. And this happens because of the saturable absorption property of the EDF. And we think that because of this sudden hike in the output, we are able to obtain this bistability out of our EDF parallel. Now, how do we control the parameters of bistability in the EDF parallel? So there are many methods. As we have seen, the length of the gain medium affects the bistability. Whether we are able to achieve it or not, it highly depends on the length of the gain medium. Its doping also, the doping of the EDF also plays the important role, that if the absorption, because it overall depends on the absorption by the EDF, and if the doping will be high, absorption will differ, and accordingly the bistability will differ. Now, and we have also seen the feedback wavelength, the role of the feedback wavelength, which plays an important role also. So we talked about shorter wavelength side, that around 1540 it is broader, around 1560 it is narrower. This is because the absorption cross section of the EDF, which is shown over here. So at shorter wavelength the absorption is higher, while at longer wavelengths the absorption is comparatively lower. So this creates the difference in the absorption by the EDF, which creates the difference in the bistability width. Another factor, which is the cavity loss. So we can incorporate another variable optical attenuator to control it, and then see what happens or how it affects the bistability. So we observe that if we increase the cavity loss, then the width becomes broader. So like that, with these three parameters, we are able to control the width of the bistable region, which has been obtained. One paper also showed another method to control this width of the bistability region by incorporating or utilizing another laser at the signal wavelengths around 1550 or so to control the width of the bistability. And another factor, which is the wavelength filter, which we have incorporated. So earlier we thought that it is just controlling the feedback wavelength. So what do we do is we remove the filter, and we had the same 36 meters of EDF in our cavity, and then tested it for the bistability. So we obtained no bistability. But as soon as we inserted the filter and selected some particular wavelength for the feedback, then we obtained the bistability. So here is the graph which shows the output of an EDFRL with 11 meters of EDF without the filter, with the filter and without the filter. So we see that as soon as we insert the filter, the output has very much increased with respect to the pump. So what is happening when we insert the filter? It quickly enhances the output in the cavity, which will affect the absorption property of the EDF, which ultimately relates to the optical bistability. And this is the curve which has been recorded for an 11-meter EDF. So this is absorption versus input power. So what we have done is we have provided some input power at different wavelengths and recorded the output. From that output, we have calculated the value of absorption coefficient and then plotted it with respect to input power. So this shows the characteristics of saturable absorption of EDF, that at the lower input power, the absorption is high, and as we increase the power, the absorption saturates. So this is a saturable absorption in EDF, which ultimately leads us to optical bistability out of the EDF current. So I would like to summarize. So with the help of the saturable absorption property of EDF, we can use this nonlinear property to exploit the optical bistability out of that EDF current, which will ultimately leads us to perform some all optical processing methods, such as optical transistors or all optical logical operations, which can be implemented with the help of optical bistability. And optical bistability can be achieved in the EDFRL under suitable conditions, and it is highly dependent on the length of the EDF and the feedback wavelength. And we saw that absorption is higher at the shorter wavelength side, and hence the bistability width is broader at these shorter wavelengths. And we also saw that the standard laser output characteristics gets modified when we increase the length of the gain medium up to sufficiently long length. Thank you.
Thank you, Diksha, for the nice talk. I have a few questions for you. The first question is, from your graphs, can you use optical bistability as an optical filter?
Actually, optical bistability is a phenomena which I'm getting at the output, in the output power of my laser. So, and it happens while increasing and decreasing the pump. So as a filter, I do not think so, because it's not a component which can be used as a filter, which will filter the wavelengths. No.
Right. Okay.
It's a phenomena which is happening.
Okay. So the next question is that you showed a very interesting graph with and without filter, and we saw there was a huge change in that.
Yes.
So the reason for that change, is it because some property of the laser has changed, or is it because of some change in the property of the EDF?
No, so the change in the property of the cavity has been changed, not the EDF. EDF is our active medium, but the construction of the laser, so the construction of the laser has been modified. So we have inserted this filter. Now, when I set it at say 1550 nanometers, then the feedback wavelength will only be 1550 nanometers out of this, the spectrum which I showed in the beginning, this. So out of this entire broad emission, I am now selecting one particular wavelength for the feedback, which will very much enhance the absorption at that particular wavelength and bleach the absorption at all other wavelengths. So that is why the output has been so much increased.
I see. Okay. So is that the reason that at 1540 nanometers, you see a very broader stability?
Yeah, the reason for broader bistability at the shorter wavelengths is related to its absorption cross section, which is higher at shorter wavelengths.
Okay.
Yeah, this graph. So at 1540, the absorption is higher as compared to 1560. So that is the major reason of having a broader bistability. Because the absorption is higher, the emission will also be higher at that wavelength, and hence we will have a more small signal gain of the cavity.
Okay. Okay, that's all, Diksha. Thank you so much for your talk.
Thank you.
Okay, so we now move on to the third invited talk of this session by Dr. Alan Johnson. Dr. Allen completed his PhD from the Imperial College of London on the topic long and short wavelength optical sources for attosecond science. He was then a visiting researcher at the University of Frankfurt, followed by the University of Ottawa. He was awarded the prestigious Marie Curie early stage researcher position at the Imperial College of London, where he carried out HHG spectroscopy experiments and built a water window X-ray attosecond laser. He is currently a Probis postdoc fellow at ICFO, examining ultrafast dynamics of quantum materials. In addition to this, he also has a beautifully written introduction section to his thesis. On that note, I invite Dr. Allen to deliver his talk on ultrafast soft X-ray science from tabletop sources to resonant imaging. Over to you, Dr. Allen.
Right. Thank you, Pranav. Lovely introduction. I'm glad that you find the beginning of my thesis useful. It'd take a while. So yes, my name is Alan. I'm actually just currently changing to be a Lacacia Fellow at ICFO. I have my own lab starting next month. And today I'm going to talk to you about ultrafast soft X-ray science from tabletop sources to resonant imaging. So to begin with, let me just say, why are soft X-rays a great place to do ultrafast X-ray ultrafast science? Well, it's basically because soft X-rays give you access to localized electronic and nuclear structural information. And the reasons for this are threefold. One is that you can, let me talk about the localized part. The great advantage of working in the X-ray is that you have absorption elements from different atoms are incredibly well spaced in energy. They're hundreds to even thousands of electron volts apart. So by tuning your photon energy, you can really look at just one atomic species inside your sample. So for instance, you can look at just what's going on around the coppers or just around the vanadiums or just the oxygens. So in that sense, it's a localized probe with angstrom resolution. The other important thing is that it is sensitive to both electronic and nuclear structure. In particular, the X-ray absorption process looks something like this. Your X-rays come in, take an electron from a very deeply bound core level, and put it up into a vacancy around your valence or conduction band. Because this state barely gets perturbed by anything, it's a very, very clean probe. And it is, in fact, the premier way to probe unoccupied states inside a material. So photoelectron spectroscopy is the best way to look at occupied states. This is the best way to look at the unoccupied states. The other thing is if you look at even further out at slightly higher energies, just beyond the absorption edge, you can actually get nuclear structure back through a process called XSAFs, which is basically the scattering of emitted electrons from adjacent atoms gives you interference and you get these slow oscillations. So with soft X-rays, you can get this localized electronic and structural part well separated in energy. It's a very nice clean probe of a lot of things. And it's so important that this has really been one of the big goals in attosecond science for ages, is to build soft X-ray sources at the laboratory scale with attosecond time resolution. So the first demonstration of this was done way back in 1997. Where you can see that they managed to generate radiation out past the carbon edge at 280 eV. At this point, there were almost no photons, but it was still so exciting that people have pushed on with it, and we've made huge progress over the last 2 decades. Sorry, I hope you can see my cursor. Huge progress over the last 2 decades, and now we can generate and people have started to use X-ray absorption at the carbon edge to really do some dynamics measurements inside small organic systems and medium-sized organic systems. So we've made a huge amount of progress, and it's largely driven by the development of longer wavelength driving lasers for a reason that I'll tell you about right now. So just a brief recap of high harmonic generation. I know that you've had a couple of talks on this already today, but just some points are more important in the infrared. So the basic idea of high harmonic generation is given by the 3-step model, where at the beginning you have a strong laser field. It ionizes an electron. That electron can then propagate freely under the influence of the laser field, getting driven away. At some point, the field, because it's an oscillating laser field, right? A radiation field oscillates. The electric field will switch direction. That electron will slow down and get accelerated back towards the atom. If it hits the ion it came from, it can release all its kinetic energy as a big high energy photon. Now, the important thing is that this photon energy scales with the intensity and the wavelength squared. the intensity, because that controls how fast this electron accelerates out in the continuum, and the wavelength, because that tells you how long it spends out in the continuum before this field switches direction. So it has longer to accelerate away and then come back. So those are the important scaling rules. But actually, the real secret sauce to high harmonic generation is perhaps in the phase matching. The real challenge is to try and get all of these different atoms inside your gas jet to emit their high harmonics at the same time, right? And this can prove very, very tricky in the soft X-ray because you have your wavelengths are so different that your normal phase velocity in the materials is completely different. And the other thing is that you're generating a lot of plasma, which will further distort this phase matching quite a lot. But it is possible, but it's probably the trickier part, let's say. Sorry, my setup is quite annoying here. So this is why people have gone to long wavelengths, right? It has the advantage of giving you a high emission energy at a fixed intensity. So this is better than just turning up the intensity, because if you turn up the intensity, you increase the amount of plasma that you generate, you make more and more ionization, and that can make it impossible to achieve phase matching. But with the long wavelengths, it is possible, right? So this is why this has been the huge driver of getting the high photon energies. The other thing, however, there are a couple of cons. One is wave packet spreading. So as I said, the electron spends longer out here in the continuum. That unfortunately also means it has longer to go in the wrong direction and miss the atom completely when it comes back. The other thing is that there's a stronger intensity dependent phase. This is basically the fact that these trajectories, depending on the amount of time you take to come back, you pick up a different energy. And that means for any given photon energy, there's an intensity dependence to the actual phase of emission. And this gets stronger with longer wavelengths, the more time it spends out in the continuum. So it can become quite tricky to do. You become very sensitive to intensity fluctuations. But despite that, it does work. So let me present some of the results we got during my PhD at Imperial College. So the actual setup is very simple. It's not significantly different from normal high harmonic generation. You have a few cycle driving laser. The only big difference is that it's at 1800 nanometers instead of 800 nanometers. You focus it down into a gas cell and you get harmonics out. This gas cell is filled with very high pressure gas compared to what you'd normally expect. All this has to be done in vacuum, but this is filled with between 4 and 10 bar of gas pressure, which obviously is not something you ideally want to put into your vacuum. So you need to construct this special apparatus. But at any rate, we filter out the fundamental radiation, and we can just look at the harmonics on a soft X-ray CCD. And these are the kind of results that we get. So you can see this is the generation in neon up at the top left. I hope you can see my cursor. It's not entirely clear to me that you can. But yeah, this is the radiation emission from neon, and this is the radiation emission from helium. And you can see that it really spans deep into the hundreds of photon energy and that we can tune it with the backing pressure. If I take a line out, you can see that we're well past the oxygen edge, going out to almost 600 eV. And we actually get enough flux out here at these really high photon energies to do some basic X-ray spectroscopy. So this is, I think, Mylar. And we can see a couple of absorption features measured with the high harmonic sources, even though these fluxes are, for people who do lasers, these are obviously tiny fluxes, but for soft X-rays and ultra-fast X-rays, this is actually pretty good. The other thing is that we can see carrier envelope phase dependence. For those of you who aren't attosecond people, this is basically a signature that you're generating an isolated attosecond pulse, right? And as we tune this with pressure, we can put this isolated attosecond pulse anywhere inside the spectrum that we want to. So here it is. This is the signature of an isolated attosecond pulse at the carbon edge, and this is one at the oxygen edge. I should briefly say that the oxygen edge is probably the single most important absorption edge there is, because oxygen's in all of the organics, it's in all of the transition metal oxides, almost everything has oxygen in it. So it's one of the great peaks to reach. Okay, so we can do this, right? We can generate soft X-rays all the way across the water window up to the oxygen edge. It's very nice, but we'd really like to understand what's actually going on, right? How is this generation working? Is it the same at 800 nanometers? And how can we make it even better? So to do that, we've simulated our driving conditions, really simulated our experiment, I think, probably to a higher degree of agreement between experiment and theory than people usually bother with. So we really went and got all of the parameters so that we could do a full 3D calculation and really make it match up as well as possible. And what we found is we are in fact very different from the normal phase matching region, right? In particular, we are going in with intensities many times higher than people would usually use. And what you can see here in this plot in the top left is the fundamental laser intensity. This dashed line is what it would be in vacuum, and this red line is what actually happens. So there's a huge amount of loss. Well, actually, defocusing is the real thing that's happening here, right at the edge of the gas jet. So we never attain that peak intensity. And if we look here, we've plotted the ionization fraction electron density. And you can see it spikes, the electron density goes up very, very high. In particular, this ionization fraction of 6% is hundreds of times higher than people usually consider. Very, very high density plasma, which is what I earlier told you didn't want to do. And if we look at a time and space resolve plot, this is the profile in time of our fundamental driving laser just at this generation region. And you can see actually there's only significant on-axis intensity, sorry, right at the beginning of the pulse. And then there's so much plasma buildup already that it actually defocuses, and all these trailing ones are going off at a funny axis. Right? So this is really, we're whacking this thing hard. How does this affect the generation process? Well, if we look at the buildup of these harmonics in the time domain, first of all, we can see even though there's many cycles to our laser pulse in the last one, we only get 2 bursts of harmonic radiation. One corresponding to this nice, well-behaved thing at -5, and one corresponding to the one next to it. So actually there's only 2 harmonic pulses, and they build up very rapidly. This is just the spectral version of the same plot on the right. And if we just take a line out for them, if we just look at the buildup of each one separately, we can see that they build up in space inside that gas jet very, very quickly, right? All of the intensity one builds up within, say, 100 microns, and roughly the same for the second one. And then we have some oscillations. These are Maker fringes because the phase matching isn't perfect beyond that point. So what we see is we have a big long gas jet, we have a big long focal range, but in the end, the harmonic radiation is only building up over about 100 microns. And this is quite surprising because we actually get fluxes comparable to or better than people have achieved with these conventional schemes. Not all sources, but certainly conversion efficiencies are not very different. So what's going on, and why should we care about this regime, which we've dubbed the overdriven regime for high harmonic generation, where you go in much, much harder than you would ever expect you should, and still somehow get out radiation of comparable brightness. Well, let's do a quick heuristic argument. You can calculate the rough phase matching conditions for a Gaussian beam at focus using this expression, right? All this does is take into account matching the Gouy phase, basically. Sorry, there's no Gouy phase at focus. What am I saying? All it does is calculate the point where the phase contribution, the phase dispersion from the plasma, and the neutral gas remaining cancel out, right? And you get good phase matching, basically. This is kind of a standard little argument for high harmonic generation phase matching. And from this, you get a phase matching pressure for a given plasma fraction. But if you look carefully, you can see that the plasma fraction actually scales inversely with the wavelength. Or sorry, I skipped something there. So you have this phase matching, and from this phase matching pressure, you can find the critical plasma fraction that will give you optimal phase matching, high phase matching pressures, the most emitters. But what you can actually see is that this critical phase matching scales inversely with the wavelength squared, right? So as you go to longer wavelengths, to achieve good phase matching in the traditional picture, you need lower and lower and lower ionization fractions. And then if you really consider this phase matching fraction, pressure, to first order, the total number of emitters is just the critical plasma density times the phase matching pressure. That becomes not a function of wavelength. Basically, you go to longer and longer wavelengths. People have said that you can use higher and higher pressures, so you get more and more emitters, but you actually don't get more emitters. You get the same number of emitters, roughly. Okay, so there's no actual gain in the traditional picture of going to high pressures and things. However, you do lose something. And what you lose is this plasma contribution. So this is the plasma refractive index here at the top. It scales with the wavelength, right? The impact of the plasma that you're generating back on your driving laser gets worse and worse. So you should go to longer and longer driving lasers. The amount, for the same given amount of plasma density, the back reaction on your driving field gets worse and worse, and you're gonna have more and more defocusing. So you're not gonna be able to maintain nice, smooth laser beams over any given length. It's gonna defocus faster and faster. The other thing is that the single atom phase, this intensity dependent refractive index that I talked about earlier, which is unique to high harmonic generation, scales as the wavelength squared. So not only is your intensity going to change faster due to this defocusing, it's going to affect your high harmonic generation worse and worse as you go to long wavelength sources. So that's why we think this regime, the overdriven regime, where you kind of forget about achieving classic phase matching, and you just go in and hit it hard, and you get this very rapid buildup in one area where the phase matching is achieved transiently, but at super high densities. This will be more and more valuable as we go to longer and longer driving wavelengths and higher photon energies. Okay.
Dr. Allen, sorry to interrupt you. There's something perhaps wrong with your mic. Could you say the last few sentences again? Yeah, sorry, still can't hear you. Perhaps you can try turning it off and on again.
Really nothing.
Yeah, it's fine now. It's fine now.
Oh, very weird. Okay. All right. It was just to say that we think other works have actually been done in this overdriven limit in the past without realizing, essentially, and that as we go to higher and higher photon energies, it will be more and more important. Your other option is to just build bigger lasers and looser focusing so that you don't get this defocusing. But as we're approaching the point where lasers are already dedicated facilities, like you see at the Eli facility, for instance, that doesn't really seem like a sustainable approach. Okay, let me just show you quickly something we can do with this source. So we can do X-ray spectroscopy. That was the whole point. This is the X-ray absorption spectrum in P3HT, which is an organic solar cell component, one of the two big important organic solar cell components. And you can see we get very nice absorption spectrum at the oxygen edge and at the carbon edge. Right, and we can probe different things depending on which spectral regions we look at. So this will be very quick, but just to say that the time resolved version of this experiment has now been done. Right, so this is the transient change in the carbon edge spectrum after photoexcitation, after really looking at this light harvesting process. And you can see there's two features, one a very short-lived one, and another a long-lived one. This is a shift, which is why it looks like there's two things. But it's actually one. We can see one feature is short-lived and the other feature is long-lived. And I won't have too much to say about this, but we took this to our theory colleagues and they did some calculations. And what we can see is that at short times, in the first 10 to 30 femtoseconds over here, this excitation is consistent with a delocalized interchain excitation. So the initial absorption process is really a delocalized one across several chains of P3HT. But quickly, within about 40 to 100 femtoseconds, this changes, and it really has the characteristic of a localized excitation. So from this, we can really look at the dynamics inside the system. We can see that though there's an initial delocalization, the system localizes very quickly, and this could be important for the function of organic solar cells. But I am not an expert on this. If you're interested more in this, I am on this paper, but it's not my work primarily. So I advise you to check it out on the ChemGrive. Okay, so I'm sorry, I'm running a little bit late because I guess technical problems. But I want to switch gears completely now and talk about something I'm doing here at ICFO, which I think could be a big application for these sources in the future. Right. So this is these are coherent imaging inside quantum materials, and these are experiments that are actually done at facilities. So I'm mostly going to prevent things that were done at the X-ray free electron laser in Korea at PAL. But basically, this is leveraging the fact that X-rays, because of their short wavelength, can give you very high spatial resolution, right? They have 2 nanometer wavelengths at the oxygen edge, for instance. So you can really get very nice high resolution, higher than you can do with optics, combined with this spectroscopy information. And we use what's called lensless imaging techniques, where we take diffraction patterns and invert them. This is because optics in the X-ray are just terrible. So if you can do lensless,
Dr. Allen, sorry to interrupt you again. There again seems to be an issue with your microphone. So it's kind of a bit muffled up.
Sorry, that might be because I have some rather powerful noise canceling on, because I have a baby in the other room. But let me just see.
Now it's totally fine. Now you're audible.
Okay, I will just try and speak very clearly then, and hopefully. But anyway, just wave if it's a problem, and I'll try again. Sorry about this. Okay, so we've shown in the last few years that you can, by tuning to particular resonances, measure phase transitions at the nanoscale, right? So this is the work done with X-ray holography and with coherent diffractive imaging, where these different colors correspond to different phases of vanadium dioxide through its phase transition, right? And in fact, using coherent diffractive imaging, you can return the entire complex refractive index in the X-ray for every single part of your sample, just by scanning the photon energy and doing these complex reconstructions. They give you back the real and imaginary parts of the refractive index. Now, our real goal here was always to study the time-resolved version of this, because VO2 shows an ultra-fast phase transition in about under 30 femtoseconds, maybe very, very fast. This phase transition can occur. But in all real systems, you will have a coexistence of both phases, of the low temperature and the high temperature phase. This is natural for all quantum materials because of a competition between short range and long range order. So we wanted to do the time resolved version of this measurement and hopefully answer some long-standing questions. And earlier this year, we were able to achieve this. So you can see some of these features in this. This is a single color image, just that one peak that shows contrast in the metal insulator. And you can see we've picked out a couple of regions, and we can really, with nanoscale resolution across these lineouts,
Alan, it's happening again.
Is that better? Or is that worse? Should switch to a different microphone. Can you hear me now?
Yes, yes.
Okay. Figures while I was doing that. So anyway, okay, great. All right, so we can look at the actual full images at each of these time slots. We can see that there's some big changes starting at around, well, when we pump at 0 femtoseconds. And that the spatial structures are actually quite consistent. And if we compare them to the static domain structure measured with multiple colors before pumping, we can see they actually match. So we were quite surprised to see this, but it looks like we're switching all of the domains, all of the insulator to metal on the ultra-fast timescale, which was definitely not what we expected and what nobody expects in the literature. So this was quite surprising. And in fact, using principal component analysis, we could see that every single point in this sample undergoes the same dynamics at short time scales. At long time scales, you start to really get some spatial motion, like 250 picoseconds, certainly. Some domains have moved, but at short times, they all switch and they all switch the same. And in fact, there's two time constants, one a very, very fast one that we expected, but then there's this slower 5 picosecond component that was unexpected because people had previously attributed this secondary time scale to nucleation and growth, so really spatial dynamics. we can say that that is definitely not spatial dynamics. There's no spatial dynamics at this point. Something interesting is happening, but we're not sure what it is. So we're still working on that. To help answer the question, we could go a little bit further, and sitting at 20 picosecond delay, we can scan the photon energy and actually reconstruct the spectrum of this sample, right? So this is the absorption and the phase shift of the X-rays across the oxygen edge. I won't get into the interpretation of the spectrum. I'm already slightly over time. This is my second last slide. But just to say that this is actually spectral quality comparable to dedicated X-ray beam lines. So with this coherent imaging, you can actually reconstruct spatially resolved spectra with comparable spectral quality to special dedicated XFEL beam lines like the ones they constructed at EuroXFEL. So it's going to be a very powerful technique. And I just wanted to end with the potential for doing this with high harmonic generation. So this paper that I've thrown up here, I think is published last week. It's the first demonstration of time-resolved imaging with high harmonic generation. It's from Klaus Roper's group. Very nice work. It's looking at magnetization dynamics, which I think are particularly easy to look at. They're a great place to start, as opposed to this phase imaging, which is a little bit trickier. But it demonstrates some of the real advantages of trying to do imaging with high harmonics. High harmonics have very high spatial resolution, much better than synchrotrons, for instance. It obviously gives you high time resolution, and it lets you do these experiments in the lab where you can really play around a lot more. Our PAL experiments had to be done in 5 days, right? Which didn't give us a lot of time to troubleshoot some things that we would have really loved to. But anyway, it worked, we're very happy, but this would be great in the future. The challenges with high harmonic generation are obviously the low flux. That's always a problem. But it turns out that in the end, we didn't need that much radiation at the XFEL. Damage thresholds run into a problem first. So these experiments could well be done better with high harmonic generations. And the other one is the broad bandwidths, which blur out these diffraction patterns. For that, I would say spectrofiltering is the way to go. It just affects the flux a little bit more. But this is, I think, a big growth direction for high harmonics and something that should be pursued even more than it already is. With that, thank you for your attention. And are there any questions?
Thank you, Alan, for the nice talk. Yes, we do have some questions for you. So our first question is, can we use, instead of a Gaussian beam, some other beam like a Bessel beam? Because in that case, the divergent effects can be minimized.
Right. Yeah, there has been, not in the soft X-ray specifically, but quite a lot of work on shaped beams for this. I'm not sure, the usual idea of a Bessel beam, of course, is it doesn't diffract, right? I presume that's what the author is referring to. That won't be the case here because this is a nonlinear phenomenon. Okay? This is like putting a Bessel beam through a very strong lens. And of course, once you put that new phase profile onto it, it will diffract. But it might help. I don't know. This hasn't been explored at all, as far as I'm aware. So it's an interesting thought. Maybe it would really help get that long range buildup.
Right. So the next question is, what is the lowest resolution one can image? I think is geared towards the end of your talk.
Right. So these diffractive imaging techniques are in principle diffraction limited. So it just depends on capturing the really high Q components in this scattering. But yeah, it depends on the wavelength. So you could, in our experiment, I think we get down to about 20 nanometers, but the actual limit would be 2 nanometers. So I guess like most X-ray things, ultimately you're going to be damage limited. So not everything you'll be able to get 2 nanometer resolution before the sample is destroyed.
Okay, I now have a couple of experimental questions for you. So in the initial section of your talk, you had mentioned that you can't just keep on increasing the pressure. That point I found quite interesting because there is a trade-off between the pulse energy that you can use and the pressures that you can use for efficient phase matching. So based upon the observation and on the experiment that you had performed, what happens when you keep on increasing the pressure? I'd expect the phase matching to go bad, and then after a while, the intensity should go down. But I think you observed, on the contrary, that it remains constant.
No, I mean, if you look at our pressure plots here, you can see that the overall flux does peak at some finite pressure. And as you go really, really high to even higher pressures, it drops off. I think maybe I misspoke. What you can't do is keep ramping up the intensity would be the usual thing that breaks it down. That'll cause the pulse to break up and the phase matching to go. But the pressure won't cause quite such dramatic problems in the same way. You'll get buildup somewhere in your jet. You'll probably just walk off the best phase matching condition. So you can see in the helium data, we went all the way up to 12 bar, and we're still getting high harmonics. They're just getting less and less bright. It's quite a slow drop off as you do, but I think it's all from because the reabsorption is totally negligible. I think it's all from this phase matching destruction.
My next question is actually related to the previous one. So the gas cell that you're using, it's quite narrow. If you so typically you would expect that if you increase the width of that gas cell, it essentially is equivalent to saying that you're increasing the length of your gain medium.
Yes. So this relates back to phase matching again. So originally we did start with thicker targets, and we thought this was the way to go. But then we started doing these phase matching calculations, and what we found was, in the end, the harmonics only build up over a tiny range, right? If I go back to this one, you can see that the defocusing occurs right at the beginning of the gas cell, right? And if I look at the harmonic buildup in space, the buildup is completely done basically before the center of the gas cell. So I haven't drawn it here, but the wall of the gas cell is right around this point here. So basically all the rest of the gas cell is doing, even when it's only a few hundred microns thick, is just giving us maker fringes and ruining our beam. So if I could make the target even thinner, I would. Most of the length just doesn't contribute. This is not the case at 800 nanometers and lower photon energies. There you can get quite long buildup lengths. But at these long wavelength sources, I think thinner is better.
Okay. So I see that you're essentially using a chamber within a chamber geometry, right? And then you're also focusing beams. So typically, what is the thickness of the window? Which so there are two chambers, right? Yeah, this one. So this window that you use here, I see that there is no filamentation or nothing happening here, even though you'd be pretty close to the focusing point.
These are actually not windows. Well, they are windows, but if you look carefully, there's actually holes drilled through them. So the laser does not pass through the material. This is a differential pumping jacket just designed to capture as much of the gas in that inner volume as it can. But yes, there's two tiny holes for the laser and the radiation propagate through.
Right. I also see that you're using an X-ray CCD camera.
Mm-hmm.
And it's one of the issues that even we have been facing. We are flooded with the background light. Did you face a similar issue?
Yes, background light was quite a problem. Well, okay. Let me say, if you're working at 800 nanometers, it's a much bigger problem there, because the 1800 nanometers is not absorbed by the X-ray CCD, right? So our big problem was actually third harmonic contamination, because I mean, we're making 500th order harmonics, but we also generate a lot of third harmonic in here. So that needed to be filtered out. So one thing that I would strongly recommend is, if you can, they're not cheap, but there's multiple companies that sell these metallic filters you use to remove the background. One company can sell, if you don't have that, then that's the single most important thing you need, is one of these metallic filters, these freestanding 100 nanometer thick aluminum filters. Without that, it's going to be extremely difficult. And I would recommend not using an X-ray CCD. I would recommend using an MCP configuration. But these filters, you can buy them pinhole-less, they call them. And those work extremely well. And I think are really essential pieces of technology, unfortunately.
Okay, so my last question is related to something you said. I want to particularly talk about the difference between filamentation and HHG. And you might argue that filamentation happens only in the initial, only on the initial particular starting harmonics. So it's more of a perturbative process. But experimentally, have you noticed a point where, let's say, the generation is still happening, but the HHG has stopped, but the initial harmonics are still being generated? So do you come across some?
When you say the initial harmonics, do you mean like lower order harmonics?
Lower order harmonics.
So unfortunately, we don't detect the lower order harmonics in this experiment. So I can't say what's going on with those. certainly I think people have shown regimes of filamentation where there's no high harmonics, right? The intensities required to obtain a filament are much lower than those necessary to get HHG. So in the usual way that you kind of partition this in your mind, where there's the IR field does one thing, and then you take that and you calculate the harmonic buildup in a separate calculation. I think that works for filamentation as well. I would view filamentation as basically a process happening to the fundamental, and then you get a filament, and then you can go calculate what the harmonics emitted from that filament would be. But I don't view them as such a directly connected, like the harmonics have no impact on the filament in general, would be what I would claim.
Okay. If I may elaborate on that. So basically, if you go away from the phase matching condition in the sense that, let's say you do something with the pressure of the gas. So now you're offsetting your phase matching condition, but you still see white light generation where the filament is being focused. So my question was, in that regard.
Well, I mean, yes, we've seen that for sure. I mean, I'm not sure that it's a filament in the strictest sense of the word, because I mean, our distances are so small, I can't tell you if it's really a filament, but certainly we can generate a lot of white light without generating any high harmonics at all.
Right. Okay, so the last question is it better to use cylindrical gas cell over gas cell in cuvettes? Because in that case, you can improve the interaction length constant.
Sorry, I don't quite understand the question. The gas cell in what geometry was the second one?
Yeah, so I'll repeat the question. It says, is it better to use cylindrical gas cell over gas cells in cuvette? So cuvettes are essentially quartz cuvettes in which you can hold some sample, right? So in that case, you can improve the interaction length constant. So essentially saying, is there a particular advantage to use cylindrical?
This is asking about if you go down the down the glass capillary.
Yes.
That's the geometry they're asking.
Yes.
Right. So I guess the glass capillaries are harder to get to work, I would say, is one downside for sure. They're prone to things like damage. So yes, there's quite a lot of controversy about this in the field in general, I would say. Some people swear by these capillaries, other people won't touch them. What I will say is people have claimed that with the gas capillaries, you can get the buildup over very, very long lengths. And they claim that these lead to very, very high fluxes. I'm not sure this claim is really borne out in the literature. Because for instance, they haven't really been used for better imaging or better spectroscopy or really like all of the metrics you'd use to really tell if a source works better. I don't think they've necessarily panned out for. But that said, in the sense, this over-driven thing should be a problem there as well, right? In that case, you don't get defocusing in the same way. What you get is defocusing the point and then coupling to higher order modes, which will then cause large-scale intensity beating down the fiber. I think Captain Remain have one paper, a theory paper that looks at this multi-mode beating, but that should be a problem. So these pictures people have where there's a nice smooth intensity profile along the whole thing, because you've coupled into the fundamental mode and that gives you nice harmonics. That should not happen, right? Because it ignores the fact that you're generating plasma and then you're going to couple into higher order modes. And even if that mode dies out faster, you're going to be continually putting power into those higher order modes. So I don't think that's as well understood as some people claim. Certainly in my case, we went with the gas cells because it's much easier experimentally. But I think there's a lot of work to be done exploring this multi-mode beating in the capillary sources.
Okay, thank you, Alan. That was it. Thank you so much. Nice stuff.
All right, thank you very much for the invitation. Thanks again.
Thank you. Our last invited talk of this session is by Dr. Rajesh Kushwaha. Dr. Rajesh completed his PhD from Physical Research Laboratory on fragmentation dynamics of polyatomic molecules. He then joined the J.R. McDonald Lab at the Kansas State University and is currently an associate professor at PRL and heads the ultra-fast molecular dynamics group in femtosecond laser lab. Today, he will be speaking on ultra-fast laser matter interaction from strong field ionization of molecules to plasma chemistry. Over to you, sir. You may now share your slides.
My slide is visible. I'm audible.
Yes, sir. Yes, sir.
And my slide is visible.
Yes, sir. It's visible.
Yes, I'd like to thank our organizer for giving me opportunity to share research activities of my lab. So thanks host team and invite team and then all the team members. So I have chosen this topic, which is very broad in nature, ultra fast laser matter interaction. This is so many things it can cover, and uh, even I am covering from the strong field ionization of molecules to the plasma chemistry. So I have opted, I have chosen this topic so that in this student conference, many students are using now ultra-fast laser, and they are performing experiment of atom or molecules to ionize as well as filament or plasma chemistry. So as well as I would like to advertise my lab so that many students can at least familiar that what kind of facility is available in PRL, and they can write me, they can propose some things, and we can work together. So with this motive, I have broadened my kind of title or presentation today. Uh, so let me just start the very general motivation. So when I say a light matter interaction in the gas phase, we use atoms or molecules that we are interested to investigate and understand the physics. And in experimentally, we use some kind of projectile, like Alan talked about the X-ray. So we can choose a different kind of photon, and energy you can choose, or you can use electron or ion, and then we interact them with matter, and finally we measure by some detector. So this is a scheme that widely used in the light matter interaction and gas phase and all the process through which we investigate the atoms or molecules. This is a scheme that we use. What we notice here is there is some interaction time, and after that only if some process happen that we try to measure indirect way, means our detector don't know what happened. Sorry, just a minute. So detector don't know what happened in the interaction region, so it may just detect some ions or electrons, depend on your spectrometer design. And this process is in nanosecond or microsecond domain. It's a asymptotic domain, means after a very long time. So what happened in the shortest interaction time, that is a black box to us, and that's why we try to understand the process of light matter interaction by plotting the counts that either electron or ion or scattering, whatever the process happen here. We try to plot as a function of energy or angle or some other parameters, and then we try to interpret that particular phenomena happen. So this is a way the conventional atomic, molecular, and optical physics, particularly collision physics research is going on. On other hand, in the chemistry, I am just giving a one example where this is the Miller-Urey experiment, famous experiment that tell us that how the amino acid was formed in the primitive condition. So in this experiment, it is like mixing the few chemicals, or let's say NH3, CH4, S2, and H2O, and created the primitive condition by a spark, spark lightning here, and then after a few days of the process, we measure, they confirm that the amino acid has been formed. So this is one scheme. Here we have a black box in a certain region. Here it is like so many process happening. For example, you know that now the interaction time. So interaction time, if we estimate how much photon pass by time, let's say, that will be in kind of attosecond time. Means if you know the 1 angstrom and the speed of light, if you divide, then it will come like 1/3 attosecond. The electron response in the molecules should be attosecond, nuclear dynamics picosecond to femtosecond, and dissociation process may happen. So many process happen, but we don't have a clear kind of in time domain. We don't know what process happened first, and then we how the next step started. It happened in the attosecond or a picosecond. Finally, we are getting the amino acid, which is the big molecules, and then we are using start with a very small molecules. And in this process, what are the mechanism which process dominate or what happen? That is what information is not known to us. So what I mean that either in the first example I have shared, there is some information is missing to us. We are not able to see that. We are trying to see by indirect method, or in the chemistry also some of the mechanism. It is we are trying to interpret or understand the mechanism in the indirect way, and there is no way to see the directly that what happened means how the geometry change or how the motion happen. So if you try to understand this mechanism, what mechanism happen or what process really happen, then we can develop different kind of technique. And some of the technique when you try to develop, for example, X-ray diffraction, like previous speaker has discussed, then when you are using the diffraction to know the geometry, then the dynamics it is not known to us. So, and if you try to measure the dynamics of the molecules, when I say dynamics means in the boundary state, how the nuclear dynamics there or electron dynamics there under the interaction, then the geometry we may miss. So this is a kind of limitation or experimental challenges we have, and because of that, people are trying to develop schemes so that we can measure both dynamics and geometry at the same time. And they have name, I mean, these days it's called the molecular movie. And there are various schemes are there so that we can know uh, all the information. So to just demonstrate that this is a general motive, that we can know all the details of the light matter interaction, basically the either dynamics or the geometry of the atomic and molecular system. We have developed this lab. Okay, so this lab uh, we have developed where you can see there are femtosecond laser which is installed on the optical table, which is floor isolated. Means floor is isolated, means vibration cannot transfer here. Now there's a different technique we have used. In addition, the various setup we have developed, you can see the velocity map imaging spectrometer. I'm going to show a few results on that. This recoil ion momentum spectrometer, as well as the higher harmonic generation setup. This is under development. Few more results I'm going to show, that is showing, I mean, the setup is the other side, that is for filamentation and the plasma chemistry. So this is a general lab, and this facility is open. I mean, any student just write to me, and then we can arrange beam a time, and they can conduct experiment. So what kind of experiment can be done here? So let me just show some results, some kind of experiment that we have performed. So by the way, this lab established just before the lockdown, and so whatever the results we have, it is in elementary in nature, but it is at least giving kind of activities, a reflection of the lab activities. So let me just share what I'm going to discuss today. Okay, so if you see here that we are using the femtosecond laser, and you can use either atoms, molecules, or diatom, triatom molecule, or even hydrocarbons, or even solid. And then first question that we are asking, that can we control the unimolecular reaction? Unimolecular reaction means when you interact molecules, let's say either CO2 or this molecules, methanol, then some process happen here, and then we may get a dissociative ionization. So means so it may dissociate, molecules may get a dissociative ionized, and then it will fragment. So it will produce molecular, I mean, ionic fragments and neutral fragments. So we can know the yield. We can have a various technique to know the yield. Now, how to control the yield? So there are two schemes are there. One scheme is like this molecules has various potential energy curve, and we can populate to some state, and before that state which is repulsive, means it's dissociative in nature, and once it's dissociative, it will produce the some fragments. So but if you use another probe beam, so kind of pump and probe scheme, then you can change the population, and in that way we can alter the dissociative reaction yield. This is one scheme and had been demonstrated earlier also. The another scheme is like change the laser parameters so that the interaction nature change. So if you stress the pulse or use the pulse duration or many other parameters, if you change polarization, then the interaction with molecules will change, and it's possible that the yield of a particular dissociative reaction may also change. So these are the two schemes widely used, and we are going to demonstrate that one of the scheme where we can use the laser parameters to control or alter the yield of the particular dissociative reaction. So what I'm going to discuss today is basically the H atom migration. So basically in this molecule CH3OH and CH3Cl, how we can alter the yield of HN plus ion formation. HN and ion formation means H2, H3 and H plus ion formation, which is basically due to the kind of migration, H atom migration and association process happen. This phenomena is known hydrocarbons. This happen, and this process is even in ultra fast nature. But we are just showing or demonstrating the quantum control or the how we can control the yield of HN formation. I'm going to show some results on the strong field ionization of CO2 in this. So this is the first part that I'm going to show. The next I will just discuss that how we can create a filament which is very useful for atmospheric sensing and many things, and how we can means the lifetime of the filament and other phenomena we can measure it. And finally I will discuss with the plasma current. So many topics I'm covering and just giving a kind of information or update that these are the activities that we are doing, and it will, if you are interested, you are welcome, you can join me. So let me start one of the experiment. So we first investigated the control of quantum control of H atom migration and S3 formation from CH3OS methanol, and this is use a velocity map imaging spectrometer. It has multiplates velocity map imaging spectrometer, so it's also called a thick lens. So basically we are setting the electric field in such a way that velocity vectors of the fragments that is generated due to the interaction of laser is image at the detector. Okay, and we are using NCP phosphodetector. The velocity map imaging spectrometer, which is here, it's linked with gas chamber, supersonic gas chamber. So here the gas is coming in this way, and the interaction happen in this chamber. And this can be operated in two modes. So even for ions, we can have a time of flight measurement. So we can know all the fragments that are generated due to the interaction of laser, as well as you can select the particular ions, and then you can see how their what the velocity distribution are. So this is the kind of capability we have. We can also switch to the velocity map imaging VMI mode of electron, so we can get a different ATI and other things that I have not planned to discuss today. So this is the experimental setup, and now I'm going to show the results that if you're using the methanol and laser, and then we're detecting the kind of ion yield, then how we can change the yield of let's say this H2 and H3 as a function of various laser parameters. So this is with aim that we can demonstrate or we can so that this scheme may be suitable for changing the yield of the yield of the unimolecular reaction. So here I'm just so this result we are not using the detail of velocity map imaging spectrometer. I'm just showing the results in the first phase only on the TOF based measurements. So we see that once you have a three intensity, we can clearly see there's a change of the H and yield. So H plus yield is very less here, but it's going increasing. And at this 5.7 into 10 power 13 watt per centimeter, you can see the huge doubly ionization phenomena is also happening. Means the fragment C2 plus or O double plus, it is coming from the precursor or doubly or triply ionized. So what happening that once we are increasing the intensity, we are basically perturbing the Coulomb potential, and then many phenomena start happening, even the non-sequential double ionization, and as a result, so the phenomena will be means the fragmentation process will be different. So whatever we see, particularly the ions, these ions, that will be sorry. So that will be the results of the phenomena, or that is the results of light matter interaction. So what happening that once we increasing the intensity, the interaction process or the is kind of populating the dissociative state, uh, that is changing. So you are populating to the more dissociative state. So we have more channels for HN plus formation, and that's a way that we can demonstrate. Okay, so it's playing a role. In a strong field, there are some theory that tell us that how the strong field ionization took place, and we have performed ADK and P50 theory that I'm not showing here, but that theory requires the ion yield as a function of laser intensity. Since here we are focusing on HN plus H2 and H3 yield, how it is changing as a function of intensity, we have plotted, and you can clearly see there is a enhancement. Means once you increase the intensity, the HN plus formation is increasing as a function of laser intensity. And here LP is linear polarized and CP is circular polarized, and you can see there's also a dependence on this. When we switch to the wavelength, let's say here at 800 and 1300, so this is at 800 and other one is the 1300, we can see there's a huge variation in the yield of H2 plus formation. And this is certainly exciting to us, that why this happened. Means once we are keeping all the parameters same, pulse duration, peak power, everything is same, just we are changing the wavelength, and still we are in MPI region. Still we can see that the fragmentation process is changing. It means that the higher wavelength is decreasing the ionization. I mean the population state, which are getting populated various excited state in this case at 800, that is less in case of 1300. So this is just demonstrating that these are the parameters can be used to alter the yield of association process that we have focused in this. Let me show you the some more results that we have changed the pulse duration. So once you are changing the pulse duration, let's say 29 femtosecond, your molecules is present within the 29 femtosecond. So there is a less coupling. Once we stress the pulses, there is a huge coupling between the pulse and the atoms. So not only the excitation process happen, there is a coupling between the laser beam, laser presence of laser pulse, which is 195 femtosecond, with your molecules, what process happening. So that will certainly influence. And what we see that the influence is in the enhancement in nature. Means we are populating more repulsive state, and as a result we have more yield of HN plus H2 plus on this. So this is a kind of demonstration that we can also use pulse duration to enhance the dissociative process, particularly the unimolecular dissociative process, where the coupling will be strong, particularly in the longer pulse duration. On the other hand, it has been known that by changing the circular polarization, you can see that recollision, the electrons which are recollide and then excite further or ionize the further the molecules, that is non-sequential double ionization. That kind of cross section reduce. So this is again a demonstration that we can use the circular polarization to reduce the some unimolecular dissociative process. Basically, we are diverting the electron recollision or reducing the cross section of electron recollision cross section. So with this, now I will switch to the another topic. So in this, what I have seen shown here is the only the time of flight based measurement. Here I have not talked about the any reaction, but all these fragments are coming from the various reactions. So now we are going to demonstrate that how particular dissociative channel. So we can select the particular dissociative channel and then see that how we can control it. So for that, to select the dissociative channel, we have used another setup that is not a cold trims, VMI. It is a kind of cold trims, or since we are using the effusive in this case, we are saying the RIMS, recoil and momentum spectrometer. It is basically the combination of coincidence technique and the time of flight. So what techniques here is that once the let's say the male due to interaction is on the, let's say, some ion species is formed, AB plus 2 plus, and it is fragmenting, then we record their time of flight in the in the sequence. So it is like in correlated manner. So when you record in this manner, means that is like to do this we should have a single collision condition. So it's like one molecules, let's say CH3Cl double plus, that single molecules has to fragment here, and then our detector is waiting. So first it detect the first hit, whatever the ions detected first, that naturally depend on the mass by charge ratio. Lighter one detect first, then the window is still open, and then second ions hit will be recorded, and like this third hit or fourth we record. So once we plot the hit one versus hit two, you may get a dissociative reaction channel. So this is a scheme that we have used in this RIMS setup. And here that is we are just demonstrating the time of flight spectrum, where you can just clearly see what are the ions are formed even in this molecules. We can see H plus, H2 and H3 plus formation took place. Sorry, I'm getting another call. Okay. So this is what we get in the first hand, and then we go for further analysis, and then we try to get dissociative channels. So once we plot hit one versus hit two time of flight, we can get the coincidence plot, and there we can, depending on the islands, we can find out which are the dissociative channels. So based on this coincidence plot, we can find out which channels this H plus is formed, H2 plus, H3 plus are formed. It's possible that there are some neutral fragments are there, or three body fragments are there. The neutral fragments we are not able to detect. So that if it is more than one fragments, then we may not able to investigate that dissociative channel. But if it is a one neutral fragment, then by momentum conservation, we can try to find out the detail of that. I mean the momentum of that neutral fragment, and then we can investigate the detail of that particular dissociative channel. So in this study, just to demonstrate that how the particular dissociative channels, like this are the fragmentation channel, how that is influenced by the various laser parameters. So we have selected only few channels, and these are the two body breakup. So we analyze ionization took place, and then fragmented in the these are the channels. So we have selected this channel, and then investigated that how this four channel the yield is changing. So basically the this is from the time of flight, how when you're changing the laser yield, how H2 H plus and other yield are changing as a function of laser intensity. And then we shortlisted the ion. So 1 2 3 4 is basically the this dissociative channel. Sorry, how to go back? Okay, so this 1 2 3 4 is basically these are the channels, and from this channel we can know what are the H plus, H2, H3 all are formed, and that we can select, and that we can estimate from the channel wise, and you can see that based on the intensity, even the channels are decreasing. So if you remember in the previous case where or even here, once we increasing the intensity, we see that this yield are increasing. But in a dissociative channel, this is, if you select a particular dissociative channel, it is not true. Means it possible that these are forming from the various channel, which are, so it is each data points is belongs to the, all the possible channels. But in particular channels, it's not true that it is decreasing increasing all the time. So we can see that once you're increasing the intensity, so dissociative channel wise contribution from the H2 H plus, S3 plus, that is decreasing. So this is one way to to demonstrate or go in detail that how the particular dissociative channel yield is basically change, or their yield is change as a function of intensity. Now, we have further extended that in particular dissociative channel. Once we see that, so here we are going in detail that how we singly ionize and doubly ionize is contributing. So this is total, and this is a just we have selected a particular case. I mean the particular like H plus only. We have H2, H3 plus that data results I'm not showing here, but just showing that how as a function of pulse duration the singly ionized and doubly ionized. So singly ionized case we have a more compared to the doubly ionized case. Okay, just as a function of double as a pulse duration. But when we go to the reaction wise or dissociative channel wise, you can see the many channels, at least Hn plus, except S2, SCl, where the migration took place. All cross section is decreasing. On the other hand, the SCl, which is the basically the migration, hydrogen migration to the fluorine site is needed, that yield is increasing. And that is interesting because we clearly see that if there's a more pulse duration, means more coupling between the pulse to the molecules. I mean, it's like pulse duration is more than the vibrational. I mean, time. So in that case, we clearly see that all other yields are means fragmentation is happening a lot. I mean, the other yields of the channel are decreasing, but migration as well as association yield is increasing. So with this, we have further analyzed that even the kinetic energy release for this channel, it is also depend on the pulse duration. So that is we're trying to understand. We are trying to understand in theoretically how why this happens. So our theory team is working on this. That how by changing the pulse duration, why this kinetic energy peak is shifting towards the higher energy side. Further, we can see that even the momentum, here we have plotted Px and Py. So for the top panel here, all the H plus, H2 and H3 plus at 29 femtosecond. And then the bottom one is the 64 femtosecond. You can clearly see there is some slight change. But that change is not noticeable at this case. But when you switch to the HCl, where 29 and let's say 510, then you can clearly see there's a huge asymmetry. So certainly the process through which this SCL process happen, particularly at as a function of pulse duration, that process is different, and that is reflected in this momentum map. So with this, now I will switch to the another topics. It's like extension of what we have done in strong field ionization, and we clearly see that ionization yield, let's say plot as a function of intensity, you can see it is different from singly ionized and doubly ionized in case of CO2. In fact, if you try to see that how the fragment yield is changing, I mean, in general, we can see that there is a increasing trend. I mean, here this is demonstrating the fragmentation process. In fact, so we can see that how at one point, 0.1 petawatt, we can see that CO2 yield is certainly going up. So it means the fragmentation process of C plus O plus and CO plus of CO2 is going up, and this is we have further investigated that as a function of polarization, it is also influenced. So this is just to demonstrate that how the fragmentation process are also influenced by the laser parameter. So let me move to the another topic, that is femtosecond filamentation and film dynamics. And here we are focusing on the how the filament lifetime and the film dynamics is basically we can measure, and how what are the parameters that influence. So basically the this is the experiment. So once you focus the laser in air, if it is gigawatt, then due to the modulation of refractive index, the filamentation you can generate, and this is very easy. But this scheme has been used I mean investigate the kind of atmospheric sensing. So some reaction we can use it. So for that we should have a clear knowledge that what is the lifetime of this. Okay, so we thought that let us investigate the lifetime by changing the various parameters. So basically, once you change the various parameter, we wavelength or density or power or many things. you can see the filament length and the width are increasing. So once you investigate in detail, then we find that how the lifetime is dependent on the various parameters. So in this kind of project, we try to investigate the filamentation and their lifetime. And at this point, if you even investigate how the filamentation are there, basically the supercontinuum generation is there, you can see that this is also influenced by the pulsed what is the wavelength, and even the focusing length also, it is highly influenced by this. Okay, so let me just show you that at this four wavelength, you can see the lifetime is basically dependence on the what are the focal length we are using. So once we are changing this focal length, we can see that lifetime. So once you, let's say here, if it is lifetime is shorter, I mean, we can clearly see that there is a dependence, and that we can summarize how this dependent here. So if you is LT is a lifetime length and width. So at the various wavelength, the depending on the length, if length is large, let's say, then lifetime is short. This is what conclusion we are getting out of this. So we and that all are dependent on the wavelength. So we can clearly see that this kind of investigation is needed. So now I will move to the another project. So now we have discussed that filament, and this filament is interacting with air. So some chemistry may also happen. So now in this, I'm going to show that what chemistry may happen. So let's say if you're using or ablating the material, so plasma film is created, and then the filament has certain lifetime. So during that lifetime, like we have estimated in the previous section, that that lifetime is it is in nanosecond. You see, it is coming in the nanosecond kind of. It is in nanosecond lifetime. So because of the nanosecond, and the film evolution is also in nanosecond, then the presence of filament may influence the process. I mean, process in the plasma film, and that may alter, or that may change, or that may create a different kind of mechanism for the plasma chemistry. So this is the aim. So first hand, we have investigated the, let's say, the lifetime of the filament, the same scheme that we have used before, and then we found that from 0 to, let's say, 8 nanosecond, we have a filament is still there, and once this filament is interact with the material, and then it means that there's a coupling between the filament and the plasma film that generated from the laser light matter interaction, the film. So let's here we have used the three different material, this acrylic sheet, PMMA, Teflon, and graphite. And depending on the filament, here is the, if you see clearly, depending on the beginning of the filament, center or end point, either end or beginning or center, we can see the this CN, that formation happen due to the carbon from the your target, and the nitrogen from the atmosphere. So that's why we are using the plasma chemistry term here. So we clearly see that there is a change and their I mean the yield as a function of the filament position, and this is clearly saying that the filament and plume interaction also playing a role in this case. So we further investigated, and then we focus on the center, because at center we see the highest intensity. So we focus on the center, and then we investigated further to find out what are the channels. For example, here we have investigated the CN and C2 formation, and we can clearly see that all this formation took place, and that is also depend on the material. So the is basically the physical or chemical properties now we have investigated, and then because the properties of this material are different, so that also influence the CTN and the C2 formation in the plasma, in the filament and film interaction. Further, you investigate the lifetime, and we can see here that the lifetime of this ionic lines in this case is going almost like a 2 microsecond, but in case of C2 and CN, that is even more. So this is certainly interesting that This is from the atmospheric contribution, and this is from your target. And we can see that because of the interaction, because of the flume and the filament interaction, we have a longer lifetime, means up to even the 8 or 9 microsecond the CN formation took place. So with this, we switch to the again to see that how the intensity is influencing on this. And in general, in the plasma flume, we say it is a properties of plasma. It's not influenced by the other parameters. But the plasma properties like electron density, temperature, other things is influenced by the laser intensity. So with keeping in this mind, we have investigated that how the plasma CN, let's say plasma chemistry, the base CN formation, C2 from the target, and then atomic species, how their yield are increasing. So we have clearly observed that there is a dependence on the laser intensity. It means the plasma properties. So with this, now I will reach to the conclusion that we have demonstrated that how the unimolecular reaction can be controlled or alter the ion yield by the laser parameter. The lifetime of filament is inversely proportional to the length of the filament. So if you increase the length or decrease the length, we have to know that how the filament life is changing, and then the filament plasma influences the CN formation. So I'll end here. Thanks. You may ask question.
Thank you, sir. We'll take up a few questions now. So the first question is that the plume evolution that you talked about, that is happening in nanoseconds, but you are using femtosecond laser. Why cannot we use nanosecond or picosecond laser for the same?
Yes, yes. This nanosecond laser has been used, and this is studied a lot. I mean, people has used the nanosecond laser, and there's an advantage of using a nanosecond laser, particularly when you are doing elemental analysis, because we assume that the plasma is at a LTE condition, so local thermodynamic condition. So here we are considering that when you are using the femtosecond pulses, okay, then we have created the kind of filament. So inherently there is a filament and flume interaction, which is not a case in case of nanosecond. And it has been found that because of this, there is an enhancement in the signal. So because of the filament, we also saw that if there is a filament, the yield, emission yield different. So there is an advantage of using femtosecond laser over the nanosecond laser.
Okay. So, okay, how does cell phase modulation affect your results, especially when you're using different wavelengths? So since you're trying to compare different wavelengths, how does that play a role?
Yes, yes. So the critical, let's say, so what happened here that the refractive index is modulated by the intensity of the laser. So refractive index n equal to n0 plus n2i. Okay, and if you estimate the critical intensity, it will come like wavelength. It's proportional to wavelength. So once you there will be p square. There's a terms that is coming. So it is inversely proportional to n2, and then proportional to frequency. Frequency is the wavelength inverse is reverse. I mean the inversely proportional to wavelength. Okay. So based on that derivation, we can see that if you're going the higher wavelength, then we need a lower. I mean, you can go to the peak intensity. The critical intensity will be lower in that case. So there is inversely proportional with the minimum intensity or critical intensity is needed as a function of intensity and function of wavelength.
Okay.
So by that derivation, you can know.
Fine. So now there's a general question. If somebody is interested in your work and they want to ask you, how can they reach out to you? So perhaps you can say something in that regard.
Yeah. So that's why with that motive only I share all the activities of lab, and it can be expanded. Although I share in the beginning that we want to go to probe atomic and molecular dynamics up to attosecond time scale. But since this lab is just started and we have some elementary results only, so any student can just write to me or interact to the students in my lab, and then they can directly plan. I mean, there is no such a restriction. We will provide a beam time as well as what equipment we have, working equipments. We can help in all prospects.
Sir, another question has popped up. They're saying, are you probing nanostructures as well?
Nano particles we have used in signal enhancement purpose, and we got a signal enhancement up to 4 times. But nano structure we have not proved it. Means we have used commercial nanosecond, nanoparticles, silver and gold nanoparticles, and aluminum nanoparticles on that our target, and then we got the signal enhancement, and that is due to the what we understand is due to the plasmonic coupling. Plasmonic oscillation. So we are trying to probe by pump probe scheme how this signal enhancement took place when the femtosecond or nanosecond laser interact with in presence of nanoparticle. But nanostructure dependence we can do. Now, probing the nanostructure that may be a different region that I am not expert, so I cannot comment how we can uh, probe that nanostructure. Yes, different nano size, I mean nanoparticle size, different size we can use and investigate how that is uh, influencing the optical emission.
Okay. Thank you, sir. Okay, with that, we come to the end of our first session. The next session on quantum optics and quantum communication will be chaired by Ms. Tanya Sharma, and we'll meet again at 2 p.m. after lunch break. Thank you all. Thank you for joining us.
may ask their questions in the chat, and people attending on YouTube can type their questions in the comment section. All the questions will be addressed at the end of the talk. At this note, let us start the session. It's a great pleasure for me to introduce Dr. Eleni. Dr. Eleni Diamante is Senior Director at Lib 6, Sorbonne University, Paris. She received her PhD in Electrical Engineering from Stanford University in 2006. Pardon me, one second. She then worked as a Marie Curie postdoctoral scholar at the Institute of Optics Graduate School in Palaisio, France, before joining CNRS in 2009. She is a recipient of European Research Council Starting Grant. Her research interests are quantum cryptography, including continuous variable quantum key distribution and protocols beyond QKD. Today, she'll be delivering her talk on secure communications in quantum networks. Thank you, Dr. Eleni, for being here with us. Now I leave the stage for you to talk.
Hello.
Hello.
I hope you can hear me. Hello, good afternoon. Thank you very much for the introduction, Tanya. Thank you very much for inviting me to your nice conference. I wish I would be there in person, but unfortunately, under the present circumstances, we can only handle virtual events. So let me share my screen so that we can start. Can you see my presentation?
Yes.
Yeah, is this okay? It's in presentation mode?
Yes, it is.
Fantastic. Okay, thank you very much. So I'm going to be talking today about secure communications in quantum networks. So we'll be touching upon a number of topics on the field of. I saw that you have very nice talks in the field of quantum technologies, among other exciting topics as well, scientific topics. So I'm going to go through a little bit some basic information about quantum communications and the way that we conceive quantum networks, and then I'll be focusing a little bit more in the general results, some results that we have in my group on quantum key distribution in particular, and then more extended applications of quantum networks. So let me see a little bit how I'm going to be describe quantum communication networks. So essentially, these networks are quantum systems linked with photonic channels and photonic resources. So the way that we work with quantum communication networks, yes, is that we encode our information, the quantum information, in properties of quantum states of light, and then we propagate them in optical fiber or free space channels, so which can be, as we're going to see a little bit later, even satellite links. And the information processing is happening in the network nodes, and the network nodes can be all sorts of different devices. Okay, you can have in this client-server model that we're using often in quantum information, you can have quantum memory storage devices, you can have, of course, quantum processors at the very end of the scale, or simple cryptographic devices, which is going to be the main focus here in my talk today. It can be quantum sensors as well, leading to applications, for example, like distributed quantum sensing. So this is where the processing is happening. And what do we care about in this type of networks? We care about security. Again, this is going to be the focus today. So the idea is that you can have some agnostic, malevolent network devices or nodes. And we also care about the efficiency, how we can optimally use the communication resources. I'm going to, a lot of focus here is not going to be more at the component level, but at the application level, at the system level, how you can actually use these systems to demonstrate rigorously and in a provable way the quantum advantage in security and efficiency, so corresponding to these attributes that we just discussed, for a number of protocols: communication, delegated, distributed computing tasks. So this is the way that I'm going to conceive quantum communication communication networks. And I think it's important to understand that quantum communication networks are not perceived as something that is going to come and replace classical information networks that we all know today. The idea is that they are going to share resources. So there is going to come to enhance these classical resources and add some tasks, enhance some tasks that are already present in classical networks, or create some new ones that are entirely due to the fact that we're exploiting here quantum resources, that they have some properties that you cannot possibly use in classical systems. So let us look a little bit at these applications of quantum communication networks. I like this figure that shows to you a kind of a roadmap for quantum networks. This should be read, that has been put forward by our colleagues here in Europe at Delft in the Netherlands. So it's nice to read this from bottom to top and see on the left the stages of the quantum network. So essentially what you do is that you start, as we're going to see in even more detail a bit later, with trusted repeater networks, because if you want to extend distance, we're going to talk about it, you're going to have to add intermediate nodes. And the technology that we have today allows us to do this, but the quantum information has to go in the classical domain. So these have to be trusted repeater nodes. And then we increase in complexity, we start adding entanglement, which is the source of quantum advantage for many more applications. Then we start adding memories as well, then fault tolerant few qubit processors until quantum computers. And as long as you start adding more and more complex devices like this, you see on the right of this figure that you have access to more and more complex functionalities. So at the bottom of the figure, you see quantum key distribution. This is how we know how to do this today. So I'm going to focus quite a bit on this application. And then as you see, while we go up these layers, we have access to more and more protocols that go even up to blind quantum computing, clock synchronization, or distributed quantum computing, that are applications that we cannot yet fully do in quantum networks. But I'm going to show you some versions of protocols towards the end of my talk, where you can actually start looking at things that are more complex than two-party protocols like quantum key distribution. So technologically today, I would say that we are about at this on an experimental and pretty advanced point of view, we are at this level of development, these three bottom layers, and we are heading towards being able to slowly start adding quantum memories and quantum repeaters. And I'm going to give you an outlook a bit in this direction today with some nice results that have come up recently. So let's go then to what you would like to do in a quantum network. I'm going to spend some time in quantum key distribution, whose goal is to secure network links. Okay, the idea is that you want to secure communication inside your network, and typically this protocol has been designed to be point-to-point between two trusted parties. So why quantum communication is interesting, quantum key distribution is interesting. Why do we even need quantum cryptography? Remember here that modern cryptography, so the classical cryptographic tools that we're using, all of us every day today, rely on assumptions on the computational power of an eavesdropper. So there is several variations and flavors of cryptography. There is not a single one. We have in particular symmetric and asymmetric algorithms. So asymmetric algorithms are the ones that are used on the internet. Okay, that are used when we use passwords, etc., for our credit cards. When we're buying something on the internet, we communicate with our bank. These are typically all of these on the internet as asymmetric protocols. The problem with asymmetric protocols is that they are vulnerable, that have been shown to be vulnerable to future computational advances, and in particular quantum computers. And so this has led to a whole new area of research that's called post-quantum cryptography, which is still classical cryptography, but whose goal is to be resistant, to come up with cryptographic algorithms, new ones, that are resistant against attacks by a quantum computer. So these are not yet chosen. There is no actual functional operational algorithm for post-quantum cryptography, but this is the landscape, let's say, in the classical cryptography today, the fields that are advanced. So what does quantum key distribution do? than in this picture. So what it does in practice, it allows for this exchange of sensitive data between two trusted parties. Okay, this is the point-to-point aspect that I talked to you about, with two attributes of security that are extremely important. And they are not present in all these classical algorithms. So first of all, the security is information theoretic. So meaning that, or maybe you may have heard of it as unconditional security in the sense that you do not have to make any more computational assumptions on the eavesdropper. And it offers again also long-term security, which means that if the key that you want to exchange has not been compromised at the time of the execution of the protocol, then it will never be. Okay, so this protects its in-depth security that protects in the long-term data for which we need security for a long time. And this is of course guaranteed against a null-power eavesdropper, even an eavesdropper that holds a quantum computer. It's important from a cryptographic point of view to clarify that the QKD key distribution does not solve entirely the cryptographic problem, the cryptographic sequence. It needs to be combined with authentication algorithms, first of all, so that the two parties need to authenticate themselves before actually doing the key establishment. And at the end, when the key is generated, they need to use also encryption algorithms to actually exchange the secret key. So a very common one that you may have heard is one-time pad. So one-time pad offers an information theoretic encryption technique, but there is all sorts of practical considerations there. One-time pad is not very much used because it gives slow rates. So it totally depends on what you want your keys for, or otherwise you can combine with symmetric algorithms for encryption. So how does it look? Typically, this is, let's say, a little bit the textbook description of quantum key distribution. We have our two parties, Alice and Bob. They are connected with two channels, the quantum channel. So as we said, this can be an optical fiber or a free space link. They also, as we said, need to be connected with a classical authenticated channel, which is public. It means that it can be listened to by Eve, but because it's authenticated, it means that Eve cannot actually perform attacks on it, but she can perform attacks on the quantum channel. So Eve is the eavesdropper, and the main idea here, the underlying idea of security, is because of the quantum properties of light, in particular, depending on the protocol of superposition or non-locality, and because of the non-cloning theorem of quantum mechanics, we know that any information that Eve is going to try to obtain by performing some sort of attack on the quantum channel and by listening the public classical channel will lead to errors in what Bob receives, in the sequences that Alice and Bob receive, and therefore by comparing a subset of their data after the communication, after they have exchanged their quantum states via classical communication, they will be able to calculate their errors and bound the information that the eavesdropper may have obtained on the key. And if this bound is in accordance with the security proof, then they are able to extract the secret key with absolute security. So this is the main idea, the underlying idea of this protocol. So let us go and look a little bit at the state of the art in point-to-point fiber optic QKD. So this is a graph that we did with some colleagues a few years ago, and it's already a little bit obsolete. We should do a new one. So this is a field that is advancing really, really very fast. But there are some attributes here, some characteristics in this graph, some features that are relevant, that will always be relevant. So what did I want to show you here? First of all, what you see is that the performance of a QKD system is typically benchmarked by the secret key generation rate, so how fast you can generate your keys, as a function of channel loss or of fiber distance, depending on your channel loss allows you to make the link with other types of channels as well. If you want to see it in the fiber distance, then you can make some assumption about what is your loss per dB, how many dB are per kilometer, for example, and then you can make this equivalence between fiber distance and channel loss. So what you see here is that there is a number of protocols. There is not a single QKD protocol. There is many of them. So I'm going to highlight here the decoy state, the so-called decoy state BB84 protocol, which has led to record implementations. I'm going to focus a bit later in the continuous variable protocol, CV protocol, that is something that we're working on here in Paris. These two protocols that you see here, they are called coherent one-way and differential phase shift QKD. They're a little bit left aside for the moment because the security proofs are not as advanced as for the others. And then there is a few emerging protocols. This particular one is extremely popular. Now it has jumped in the last few years since this review was written to be a mature protocol. Is a measurement device independent protocol. And then there is the high dimensional protocols and the round robin differential phase shift protocol. So you see there is all sorts of different protocols with different characteristics that their goal is to answer to specific constraints, usually in experimental implementations or in theoretical conceptions around this functionality that is a key distribution. You also see in this graph that there is fundamental limits in range and in rate. Okay, so in range, you see that because of the losses in an optical fiber, whatever you do at the end, when there is a big distance, you are going to lose photons. Okay, and the way for single photon protocols, the way to get around it is to use more and more cryogenic detectors. Because as you see here, like for example, at the end of the line, the record implementations in distance have used the cryogenic superconducting nanowire detectors, and this is because in that case, there is very few dark counts in your detectors, so you can go further away without your signal photons being completely the ones that are used for the key, being completely submerged by the noise. There is also something that is less visible, is that there is actually fundamental rates in the rate as well, fundamental limits in the rate as well. So this is the limits for repeaterless, they are called bounds. That tell you, theoretical bounds that tell you how much key you can extract from out of a noisy quantum channel. And we're actually not where 1 or 2 orders of magnitude away from what is possible according to these bounds, but not more than that. And there is even some protocols nowadays, like the one that is called twin field, that has actually, because of some nice trick with a relay in the middle, it has beaten this repeaterless bound and has led to very long implementations. So you see here, so I would like to make this distinction between a major distinction in the encoding of quantum key distribution protocols is what is called discrete and continuous variables that I also mentioned before. So the difference here comes both at the encoding and at the detection level. In terms of encoding, contrary to the discrete variable protocols which rely on encoding in single photon or at least in simulated single photon states of light, which are weak coherent states, here we're going to encode information in the electromagnetic properties of electromagnetic field quadratures. So this is a language that is very much close to quantum optics. Okay, it has been inspired a lot by quantum optics, where we play with directly with the quadratures of the electromagnetic field. So we don't really define a qubit. We work with directly with electromagnetic field quadratures, and of course this has implication in the detection. In these protocols, we need single photon detectors, while in the continuous variable protocols, we work with coherent detectors, as I'm going to show you in a second. And again, in each one of these categories, there is quite a bit of different number of different protocols. So let's go a little bit more into the detail. So I'll show you here how it works, these protocols, and then I'm going to show you the implementation. So this protocol by default, by construction, it's not that the coherent states are used to simulate single photons. It actually works with coherent states. So this is the coherent state continuous variable QKD protocol. So what we do is that we create the coherent states that are described like this in the phase space with a certain amplitude and phase. We also see here, because this is crucial, the shot noise, which is the fundamental noise that is associated with any quantum state of light, and particularly with coherent states. And what we do is that we pick these states using a quantum random number generator that drives our modulation. We pick these states following a bivariate modulation scheme, constellation. And so typically in the past we have used Gaussian modulation, but in the last couple of years we've also used other discrete constellations that come much closer to what is happening in classical coherent optical telecommunications. So then these states, there is a power adjustment that shows you how much, what is the modulation variance. Then they are sent over the quantum channel that is characterized by a transmission efficiency and by an excess noise, where the excess noise is any noise that goes beyond the short noise of the coherent states. And then there is the detection technique. So normally, ideally, you would like to mix your signal, your quadrature, with a local oscillator, which is essentially a phase reference. So you mix this in a coherent detector, which you can measure only a single or a double quadrature, and this completes the quantum transmission part of the experiment. And very often in the security proofs, we consider that the noise is trusted here. Okay, it's calibrated. We can come back to this point if you're interested a bit later. Once this is done, then there is the classical post-processing. I'm not going to go into much detail on this. You need to estimate your parameters, perform the error correction, and what is called private simplification, which essentially allows you to extract the secret key, properly bound what the if can do, what the if's information, and then extract make hashing schemes and extract the secret key. And there is rigorous security proofs for this protocol. So they are done by my colleague here in Paris, Anthony Leverrier, which offers composable and finite size security. So all these words, they are very technical and they are equally important. Okay, composable cryptography, it means essentially that you can compose your scheme with any other cryptographic scheme. So you can use your keys in conjunction with other cryptographic primitives and keep the security. And finite size allows you to say that it doesn't matter if Alice and Bob have exchanged a finite number of quantum symbols and not an asymptotic number of ones, I can still prove my security. While previous security techniques, proof techniques, they made assumptions about infinite communication, which obviously do not correspond to reality. So this is how the system looks like. So this is a system that has been in our lab that has been developed for years now. I again emphasize that there is no single photon detection, the standard telecom components. And you see here the historic system, and then I'm going to show you how it has evolved. So the characteristics of the system that you see here, it follows totally the protocol that I just described to you. We have a laser diode, everything is at telecom wavelength. And what's happening, an important characteristic is here, the local oscillator. Remember that I showed you here that it should be normally at Bob's side, but this puts quite a bit of constraints in the two lasers that are used here because they are separated in space, and local oscillator needs to be used as a phase reference, which essentially means that these two lasers should be locked one to another, and this is complicated. So in all our first, let's say, experiments, we were splitting the local oscillator from the same laser. This is the modulation of the signal, and then we're doing polarization and time multiplexing to make sure that they are sufficiently apart. And then they go through the quantum channel, they are recombined, there is demultiplexing, and they come here to be detected by the homodyne detector. And for the system, we showed a few years ago that you can have long distance operation with optimized error correction stability. The problem is now that this type of systems don't leverage the capacity of continuous variables to be in agreement with coherent systems, with classical optical telecommunication systems. And it's important to push this compatibility so that we can actually, one of the challenges in the field is to reduce costs, to improve deployability. And by doing this would allow us to do so. So in the last 2 or 3 years, we have pushed a lot to change this paradigm for CVQKD and actually go to a system that looks a lot more like a coherent optical telecommunication system would look like, which means that we can put the local oscillator at Bob's side. Of course, as I said, this puts constraints in the laser line width, but it gives a host of other advantages. We can also use pulse shaping techniques with continuous wave light instead of using just temporal pulses like we were doing before, which essentially essentially means that you have to use pilot tones, okay? You have to use pilot signals so that you can create a phase reference for your system. And it also means you have to use digital signal processing, which are techniques that are used in telecommunications that actually allow to recover the phase and the polarization of, and also the time. There is even synchronization techniques in digital signal processing. They're extremely advanced techniques that allow you to do this. And finally, we replace our homemade, a little bit ad hoc made homodiode detectors with commercial devices for the receivers that are available in the market, but they also have to combine, they have to be short noise limited, low noise, and high bandwidth. So this is something that people are not looking for in classical communications. They don't really work at the short noise limit like us, like in the quantum regime. So this is something that has not been pushed a lot in performance. I emphasize here that the security analysis is really, really crucial. We would like to go, for, as I told you earlier, from a Gaussian modulation to discrete modulation, for example, because again, it's easier to do it in practice, and because Gaussian modulation can never be exact, okay, because you would need an infinite amount of information in your modulator. So there is always an approximation when we talk about Gaussian modulation. So it's better to talk about discrete modulation, and we have worked on this a lot, and we have developed security proofs for constellations of any cardinality, which is not straightforward. So these are the results that I wanted to show to you. To give you an example of how it looks, to do a system that is closer to classical systems. So this is in collaboration with Nokia Bell Labs here in Paris, and in the context of a European quantum technology flagship project, which is called CIVIC. So what you see here is now the system. So we're generating using an IQ modulator. IQ modulator is some sort of clever version of putting together an amplitude and a phase modulator. It is driven by an arbitrary waveform generator. It's very fast. We are at 600 megasymbols per second, while before, as you saw, maybe you didn't notice in the previous experiment, we were at 1 megahertz. So this is 2 orders of magnitude improvement in speed. So we generate this, as you see, big constellation with probabilistic shaping, which is the specialty of our colleagues at Nokia. And we send these states, as we said, at box, where they use this amplified balance photodiodes with an oscilloscope. So this is a heterodyne detector. It measures both quadratures, and there is a microprocessor synchronization. So, but it looks a lot like a coherent system would look like. And these are all the techniques. We're not going to go through all these details. These are all the digital signal processing techniques that are necessary for recovering the message. So if you do an initial security analysis, you will see that what the interested us here is how big this constellation should be so that you can maximize your security. And you notice that if your modulation variance is in this range here, they are actually not very far. The performance is actually not very far between a smaller constellation and a bigger one. So what we did is we performed the experiment, and you see that actually for our kilometers, which is about 10 kilometers, the implementation, the 64 QAM modulation was actually gave slightly higher secret rates. So on the order of, this is record high secret rate with respect to what can be done both in discrete and continuous variable TDD, on the order of 65 megabits per second. And this is because the excess noise is actually smaller in this implementation. So although in theory the 256 one could have given bigger secret fraction, in practice, because the excess noise was a bit higher in this case, we got better results for this smaller constellation. So we see that we get that this system is adapted to high secret key rates at relatively moderate distances. So what are the next steps? So the next step is to do further optimization, to work with more pilots, to optimize the pilots, digital signal processing, the stability, to increase the distance and make the excess noise more and smaller, and also combine this with all the necessary steps for data reconciliation and combine the security proof for finite size effects. So this is where this field is going in the sense of integration into classical network infrastructure. Let me talk a little bit about other challenges as well. An interesting problem is that of photonic integration, and this is not only in quantum cryptography. It's a more general challenge in the whole field of quantum technologies, especially photonic, of course. So photonic, but also for quantum computing and for any quantum communication applications. And why is it interesting? Well, for many reasons. Photonic integration not only reduces the cost and pushes to scalable solutions, it also it reduces obviously the footprint, and it provides adaptability, reconfigurability, flexibility in the distribution at a much faster pace. So what we're working on in this field, we have in particular silicon photonic chips from my foundry here in Grenoble in France. And so you see here an example of a photonic integrated silicon homodyne detector and heterodyne detector, and you see some results we have here. This is the linearity curve. It shows that the variance of the homodyne detector as a function of the power of the local oscillator when there is no signal is linear, and so this is very important. It needs to remain linear for sufficiently long, for sufficiently time that is above the electronic noise. So this is called clearance, so that it becomes possible to actually perform with these detectors efficiently quantum key distribution. So in this particular results that you see here, we have shown short noise limited silicon integrated homodyne detection with a very good clearance. So this depends on the chip, on the order of 10 to 18 dB, and our latest results are about 13 dB at a bandwidth of around 7 megahertz, which allows us to properly perform these experiments. And we're now working with operating with a non-chip transmitter, where the transmitter with the modulators and everything, but not with the laser. The laser is outside the chip, is based on the indium phosphide technology. Let's move on now to losses and how you get away. We have focused a lot on point-to-point implementations. So let me move on to how we conceive networks and the way to go around this inherent range limitation due to optical fiber losses to go towards networks and satellite communications. And there is a huge trend globally in the field to go towards practical test-bed deployment. And why is this important? Because you can work with interoperability, maturity, network integration, and topology. It allows you to benchmark the use case and standardize the interfaces. So there is a huge effort. You may have heard, of course, of the biggest network that is available in China. In Europe as well, we have a very big project that's called OpenQKD that brings together about 40 academics, telecom operators, equipment providers, and users. There is a range of use cases for quantum QKD, and other cryptographic schemes that go from data centers to governmental communication and critical infrastructure or medical file transfer. And for that one, the system that you just saw before, we're working with this photonics company that is called XBlue here in France to make our system more look like a prototype. So you saw in this experiment that I showed you here that you need to work with arbitrary waveform generators and oscilloscopes, digital oscilloscopes. Obviously, this is not suitable for going outside the lab. So it's important to perform these operations working with, for example, FPGA cards, last generation FPGA cards. So you see here these systems that we're developing in our laboratory in this direction. This takes a lot of engineering to be able to do this properly. So hopefully we'll have this in a couple of years. On the satellite communication front, so obviously it's harder to perform experiments with satellite. It takes a lot more preparation and also a lot more money. So what we have done some feasibility studies for our technology, and this gives you a general idea of how this would work. So feasibility study in this case means that we have considered the downlink where you would put Alice, the transmitter, on board the satellite, and the light is going downwards towards the optical ground station. And what we consider is our model. Why is it downlink? Because actually the effect of atmospheric effects is less dramatic when you do it downlink than when you do uplink, because when you do uplink, obviously if you put the transmitter on the ground and the receiver on the satellite, then you have a divergence of the beam at the beginning of the communication. It makes it tougher afterwards to actually reach. It makes it even tougher to do pointing towards the satellite. So we have considered atmospheric effects with this channel model. Given the divergence and the pointing errors, we have taken state-of-the-art and a little bit higher than state-of-the-art technology for our simulations. The advantage, of course, that it could be compatible with space-certified telecom components that are becoming more and more popular. There is more and more companies and satellite providers that are actually working at telecom wavelength and with optical links. So they're moving from RF links. Obviously, optical links have the disadvantage that when there is cloud, for example, then you do not have communication. But there is quite a few other advantages. There is more bandwidth and possibility as well to work at daylight. So here the challenge was to do a security analysis for a fluctuating channel, because this is not the same. When you have fading and when what you receive in the receiver is not constant, you cannot apply the same security proof that we had applied in the previous experiment with a fixed transmission efficiency. So what we have done is to have modeled this fading as introducing an additional noise source. And this, of course, depends on the variance of the transmissivity. And so to reduce this variance, you need to divide your data. So you have done some binning of the data according to the transmission efficiency. And so for the groups that have the same transmission efficiency, you are allowed to apply your security proof. Of course, if you divide too closely, and if you have small bins with small variance in transmission efficiency, it means you will also have smaller amount of data, which makes the finite size effect explode, the uncertainty into the parameter estimation. So there is a trade-off between the two, between how you divide your data according to transmission efficiency and the finite size effects. And so this is something that we have worked on in this feasibility study. And then a follow-up of this work is that we have considered a much more refined model for adaptive optics correction. So the adaptive optics is used for the correction of the wavefront distortion due to fading, and we have analyzed a lot of this, how the secret key rate depends on that for both continuous variable and discrete variable properties. I'm going to finish. I understand I have maybe a few more minutes, so I'm going to talk to you a little bit about extending the distance beyond this trusted repeater model. So you see that if the distance between Alice and Bob exceeds the range of the system, so if you have seen the satellite will still stayed with point-to-point links, then what you do the easy thing to do is that you consider the intermediate node repeater trusted. And so in that case, you can exchange a secret key between Alice and the node, then another secret key between the node and Bob. Then the node who has both keys performs the XOR, sends it as a secret message, for example, by one-time padding to Bob, who based on this information can extract the key of Alice, and in that case you have shared a secret key between two distant parties, and this is the basis of all the test beds, in particular the Chinese one, the one in China that you see here, which is the biggest metropolitan and nation almost wide network in the world that covers a 2,000-kilometer backbone, and all of these the intermediate nodes are trusted repeaters. This is also the beginning point of this big European quantum communication infrastructure program that contains both terrestrial and space segments, and that also focuses, but this is the initial step that will then lead towards higher stages of the quantum networks. So how do you go to higher stages of the quantum network? How do you go from trusted nodes to end-to-end security? You distribute entanglement. Essentially, this is what you do. You need to get away from these prepare and measure protocols that we just talked about. You distribute entanglement, and this alleviates the need for trusting the nodes, okay? But it means also that because quantum channels are lossy in noise, you also have to have some way of repeating the information, and this is what is done by the quantum repeaters and the quantum memories. And I want to show here a couple of results that have been very nice in the field. In the field recently, you see here these two elementary quantum repeater links that have been developed just a few months ago at Delft and at TICFA in Barcelona, both based on solid state type of memory qubits and memories. And of course, the challenges in this particular case is that there is a big trade-off between storage time and efficiency. The fidelity is usually okay. There is, for example, here in Paris, a group that works on not on solid state memories, but memories based on cold atomic clouds. And has the record high efficiency, but the storage time is limited. Okay, and so you typically cannot get both at the same time, and you also have relatively low entanglement generation rate and a limited range. Both these experiments were on the few meter of the few meter scale. So while this technology is moving, what we are doing in our group is that we're working. Yeah.
Sorry to interrupt you.
Yes.
Can you
I will try to conclude
so that we can take up the questions? Okay.
Sure. Yeah. I will conclude. I just have a couple more slides of information. I'm not going to explain it all. So what we are doing in our group is we're working on many applications that are a bit at the intermediate step. So basically, instead of waiting for quantum repeaters, our idea is that we want to show quantum applications, that the power of quantum applications, while quantum repeater technology being developed. So we have worked on a number of protocols, from entanglement-based QKD that you see here, based on broadband entangled photon sources, to primitives beyond QKD, like coin flipping, quantum money, anonymous transmission, and communication complexity. So I'm not going to have the time to talk about it today. This is, for example, a quantum money implementation where we have shown it looks a lot like a discrete variable quantum key distribution system, and where we have shown that you can prove with this polarization encoded system that you can have unforgeability of your quantum money. And we're working actually with my colleague who develops quantum memories to implement these states in the lab as well, based also on quantum storage. And finally, we have done some entanglement verification experiments as well. These are difficult experiments where you have to use multipartite entangled states, and you, in the presence of dishonest parties, you want to prove that you still get security guarantees for the honest parties. And for the moment, theoretically, we have applied this to protocols for anonymous message transmission in electronic voting, where this verification phase guarantees the anonymity in the first protocol and the privacy in the second one. And all of this, we are now developing, trying to implement it in the lab to show that these are near-term proof of principle applications of quantum communication networks beyond key distribution. So you see, we're moving up the stages that I showed you of the quantum networks that I showed you before. So with this, I'm going to conclude. So I hope I have shown to you that quantum communication networks will be part of the future quantum safe communication infrastructure, which is going to be secure against attacks by quantum computing and other computing advantage. There's lots of use cases in all sorts of different configurations, fiber satellite links. There is a big application toolbox, and I think it's super crucial to understand that we need to integrate quantum technologies in classical network and cryptographic practices to materialize this vision. So with this, and this quantum network vision going from local to national wide and then worldwide, I would like to thank very much my collaborators, my students and collaborators, and thank you very much for your attention.
Thank you, Dr. Eleni, for this talk. We have some questions. I'll try to cover as much as I can. So here's the first one. Is there any factor except the phase noise that reduces the key rate of CVQKD protocol at longer distances?
So, I'm sorry, Tanya, I cannot hear you very well. So what I'm going to do, I'm going to stop the thing and I'm going to start looking as well myself in questions as well. So while...
Okay, so am I audible now?
That's better, yes.
So I'll read the questions out for you if possible. So the first question is there any factor except the phase noise that reduces the key rate of CVQKD protocol at longer distances?
Yes, one of them, actually it's interesting because it's a bit different than discrete variable QKD, where one of the big reasons why distance is limited is star count. In earlier implementations of CVQKD, the actual reason why it was limited was reconciliation efficiency, the beta factor. For those of you who know, I didn't show it today to don't go into the details of the security proofs, but the fact, the fact that there is some presentation that is showing up. Yes. So the fact that we're limited by the post-processing, in fact. So when we actually managed to do the long distance results is that we also improve the post-processing in addition to the stability of the experiment. So it's actually a new thing with respect to discrete variable protocols.
Right. Even in CVQKD, we use weak coherent signals. What makes it different from DVQKD except the homodyne detection scheme?
This is the security proofs are completely different. I understand why there can be a little bit of confusion in this because in DVQKD, you actually you have qubits, okay? So you have some sort of discrete information that you encode, and your weak coherent state is that is just a tool for simulating true qubits. In CVQKD, as I tried to say in the beginning, the encoding is actually happening in the properties of the weak coherent states themselves. It's not, you couldn't do it with single photon. So it's like the encoding is different, and also this makes it the security proofs completely different. So even the reason for the security is different. While in qubit protocols, we have these bases that are non-orthogonal, for example, for BB84. In CVQKD, you rely on the Heisenberg uncertainty relations in this in the fact that non-orthogonal states are when they are very small. That's why we still keep the modulation variance low. You need to keep them close to each other so they are not completely orthogonal. So so this this brings the security and all the uncertainty relations that are the basis of the security. So it's fundamental. The difference is really, really fundamental. It's not at all the same thing.
So actually, there are many questions I don't think we'll be able to cover because the lack of the time. But what I can do is I'll put the questions in Q&A section, and there you can answer to the
I can do that. I can do that. Okay.
And thank you so much
for a bit longer and do that. Thank you very much. Thank you.
Thank you so much for coming here and delivering your talk. It was a very nice talk. So
thank you.
One second. It's time for our next speaker. Today, we are very happy to have Professor Olga Smirnov with us. Currently, Professor Olga is a group leader in Max Born Institute and Professor of Physics in Technical University Berlin, Germany. She received her PhD in 2000 in Moscow State University. In 2009, she received the SAW Award for Leibniz Society and established her own research group at Max Born Institute in Berlin, Germany. Since 2016, she has been a professor at Berlin Technical University. In 2020, she received Ahmed Zewail Award in Ultrafast Science and Technology. Her research interests are strong field and attosecond physics, high harmonic spectroscopy, ultrafast spectroscopy of chiral molecules, and nonlinear dynamics. So we are very happy to have such a distinguished speaker with us today to talk about ultrafast chirality, twisting light to twist electrons. Thank you, Professor Olga, for being here with us. I leave the stage to you.
Thank you very much for this introduction, and I'm very honored to be here. I will talk about geometric magnetism and new enantiosensitive observables in photoionization. What I have to remind you is that chirality is a property of symmetry of our hands, for example. So my left hand and my right hand, they look different, and no matter how I rotate my left hand, it will never be superimposable with my right hand. So the molecules can also be chiral, and distinguishing left and right molecules, left and right enantiomers of the same molecule, which means left and right copy of the same molecule, is very difficult. So I will tell you today about new techniques which allow you to make measurements of distinguish these molecules on ultra-fast time scale. So first of all, I would like to thank my co-authors, my outstanding PhD student Andres Ardanes, who now moved to ICFO group in Barcelona, my outstanding postdoc David Ayuso, who moved to London with his very prestigious UK fellowship of Royal Society, Piero Di Clevo from Trieste, and Mish Ivanov from Berlin. I would also like to thank my colleagues with whom I discussed the subjects that I will present today, and we had a lot of exchange of ideas. So this is a Bordeaux team, Paris team, and Kassel team, and I highly recommend the papers which are relevant for the subject that I will talk about today. So the questions that I want to ask are following. In solids, nuclear configuration or lattice determine fundamental geometric properties such as the Berry curvature, topology, and anomalous observables such as the Hall current. The question is, are there geometry-induced anomalous phenomena in molecules? And is there a common source of this phenomena such as a geometric field? So naively, one could think that chiral molecules, these two unsuperposable mirror images, they have an additional and purely geometric degree of freedom, which is called Hednerness. Stereo arrangements of the nuclei of the molecule, they define potentials in which electrons move. I can say they define tracks for electrons. And tracks, as you see here, can have very complicated topology. So electrons moving along these tracks, they generate currents and fields encode the geometry of tracks. So what I will tell you today, that this naive perspective on geometric fields in chiral molecules is actually not so wrong. And the answer to both of my questions is affirmative. There is a anomalous phenomena in molecules and chiral molecules, and some of them are known but not recognized as such, and some have never been looked at, but they are spectacular, and I will discuss them today, present them today. So I will be dealing with molecular photoionization, and the key non-sensitive effect in molecular photoionization is so-called photoelectron circular dichroism. In this effect, circularly polarized light removes electron from the molecule, and the electron has final momentum k, with which it flies to the detector. Now, if we place two detectors along the propagation axis of the light source, of the light that ionized the molecule, then what we will find out that from the randomly oriented ensemble of molecules illuminated by circularly polarized light, more in right molecules, for example, more electrons will go to forward detector than to backward detector. And if we change the Hednerness of molecules from right to left, then more electrons will go in backward detector than in forward detector. It means that we have an enantiosensitive photoelectron current. And what's important about this current, that it is a very strong, it's a very strong signal with respect to the total signal. So the enantiosensitive signal that we have here is of the order of the total signal, which means it's easy to detect, it's very efficient, and that is what makes photoelectron circular dichroism a key enantiosensitive phenomena in photoionization, and also a very important phenomena that people study to develop these techniques to discriminate left and right molecules. Okay, but what I'll tell you so far about what I have told you so far about PCD is well-known things. So what is new and what I will tell you today is that PECD, photoelectron circular dichroism, is a manifestation of geometric magnetism. And PECD is generated by the flux of the geometric field. And this is not the only news that I have for you today. The other news is that photoelectron circular dichroism is only a tip of the iceberg. And iceberg is the geometric field and the new class of enantiosensitive observables that it underlies. So one can show that PECD current can be written in the following form, where this quantity is conductivity, and conductivity can be written as a flux of a certain field through the sphere in the momentum space. So this is the sphere, this is the momentum space, which means that this is the space of K of photoelectron momentum. And the sphere corresponds to a specific fixed energy of the electron. We also call it energy shell. And the field B, so the flux over a certain field B through this surface defines the conductivity. Now, what this field is? This field is given by the vector product of photoionization dipole. This is a dipole which connects the ground state and the continuum state of the molecule, and its complex conjugate. This field is independent of light properties. It is defined in a molecular frame, and it's unique to a molecule. Its flux quantifies a chiral response in photoelectron circular dichroism. So now I would like to compare this field to another geometric field, which is very well known in solids, and this is the so-called Berry curvature. So what is the basis for comparison of photoionization and interband transitions in solids? So if you look at these two cartoons, on the right, you see a cartoon which shows you two surfaces in the momentum space. So lower surface is a valence band, and the upper surface is a conduction band. And circularly polarized light can induce transition between the valence band and conduction band. The figure, the cartoon on the left shows two another surfaces in K space. The lower surface is degenerate in K space because this is the ground state of the molecule. It does not depend on photoelectron momentum, of course. But the continuum is a parabolic band in a sense that in the continuum, electron has energy which is K squared divided by 2. Now, the geometric field in molecular photoionization that I have just presented to you is given here. And it can be also, and this is written in the length gauge, it can also be written in the velocity gauge, and then it has this form. Now, if you look at Berry curvature in a two-band solid, it has a very, very similar form. The difference between these two expressions is that here we have matrix element which connects the valence and conduction band, and here we have matrix element, exact same matrix element that connects the ground state and the continuum state. So these two objects, they look very similar, and both have the geometric nature and reflect curly twisted polarizations or currents, and the parallel between them runs deep. So it turns out that in solids there is a phenomenon which is very similar to PECD, and it's called circular photogalvanic effect. What happens in this effect is that the circularly polarized field injects electrons into the conduction band, and the conduction band we have a current which is exactly orthogonal to the plane of polarization, just like a PECD, and it can be written via this expression where sigma is a conductivity. A conductivity is a flux of the Berry curvature through the surface of the Brillouin zone. Now, this quantity and this quantity are extremely similar, and that's what makes the analogy between the geometric field and molecules and very curvature in a solid, in a two-band solid, very strong. Now, the geometric field in molecular photoionization can originate purely from the electronic structure. And that happens when we have a photoionization from a real state, for example, ground state, which is time even. In one photoionization, indeed, that's what happens, that this field emerges due to Curly electronic structure. So this is the picture of this field. The sphere corresponds to the energy shell, so certain energy of the electron that we have detected. Now, the errors on the sphere shows this vector field B. So for each specific K, you find a vector which shows you what is the magnitude and what is the direction of this vector B. So the color and also the size of the errors on this figure shows you the magnitude of the field. And what you can see is that it has very interesting structure. Now, what we already know is that only a radial component of this field integrates to non-zero value, which is flux. And this flux quantifies PCD. It means that if I take each of these vectors and project on the radial direction and sum over all sphere, I will get non-zero value, and this is flux. But if I add all these vectors together, I will get zero. Okay, but what we could think of, apart from electronic structure, we could think of exciting dynamics in the molecule. Suppose we have a linearly polarized pump pulse which excite the dynamics in the molecule. And what happens is that chiral currents evolve, and then after a certain delay between pump pulse and probe pulse, we probe this molecule again via photoionization by circularly polarized pulse. So what you will see that geometric field can also be generated by ultra-fast twisted electronic or vibronic currents. And what is also important is that dynamics offers control over the geometric field and the phenomena that it induces. In case of dynamics and, for example, excitation of a superposition of two states, the geometric field has the following form. It encodes coherence between the two states, which is simply the energy difference times the delay between the pump and the probe, and photoionization dipoles from both of these states, from state 1 to the continuum and state 2 to the continuum. Now, in this pump probe setup, the geometric field emerges both due to Curly electronic structure and twisted currents. And thanks to currents, not only a radial component of the geometric magnetic field survives, but also the whole field integrates to non-zero value. And this integral leads to new class of enantiosensitive observables. Now, it is very convenient to represent this field in terms of its quadratures. So we introduce coordinate quadrature and momentum quadrature. Coordinate quadrature reflects the asymmetry, rotational asymmetry in electron density, and P quadrature, current quadrature, quantifies the rotational asymmetry of the current. Now, it's also useful to present these quantities, these quadratures in specific combinations. If I can take symmetric and antisymmetric combinations with respect to K and minus K, and symmetric and antisymmetric contributions with respect to left and right species. So which means that these quadratures which are plus, they are completely inversion symmetric, and quadratures which are minus, they are inversion asymmetric. Now, the field that I have described so far, it exists in the molecular system, in the molecular frame. And the photoelectron momentum that we discussed so far is also in the molecular frame. What I would measure in my experiment would be, of course, in the laboratory frame. And to transfer this information from the laboratory frame to molecular frame means that we actually have to average over all directions of photoelectron momentum. And this leads, so the quantities which result from averaging of the field or its component over all directions of photoelectron momentum for a given energy, they are invariants of the field. So let us look at the first global invariant of the field, and this is the quantity which is shown here. This is what I told you. This is if I take the field and simply sum all vectors of this field for a given energy. So in other words, I integrate over all directions of the vector. And I have these four terms, which I have already introduced. And it's obvious that these two terms, because they are asymmetric with respect to k, obviously they will be zero. But what is particularly interesting that this term, which is symmetric with respect to k, so it's a k even term, actually also vanishes upon this integration. And the reason is that time symmetry of the bound state is also an important factor for the existence of this global invariant. It turns out that this quadrature is also integrates to zero in real bound states if we consider photonization from a real state. But this quadrature, momentum quadrature, is non-zero, and it's non-zero because it arises due to currents, and in this case, we don't have time even state. And this particular quadrature, net quadrature, leads to new dynamical and anti-sensitive observables. So both the geometric field and its global invariant have been overlooked until now, and this is completely new concepts that I told you today. So what is the observable which is related to this invariant that I described? So the observable, new observable, we call it molecular orientation circular dichroism. And new effect is enantiosensitive orientation by ionization. So what you would need to, the setup that you would need to consider to see this effect is photonization by the linearly polarized pump, then evolution of the currents, delay between pump and probe, and then photonization by circularly polarized probe. And during this process, this P plus quadrature is formed, and then you can see it, you can see that it exists via the observables that I will describe now. So the observable is molecular orientation. It means that ions, after ionization, you create ions and they will be preferentially oriented. So why they will be preferentially oriented? Let's look into this. Let's consider two molecules, propylene oxide molecules of the same Hedman mass, but exactly oppositely oriented. Now, what happens is that linear polarized pulse excites a superposition of states in this molecule, and it excites the current. Now, the current will have exact same direction for this molecule and their molecular frame, of course. So it will be the same direction of current in the molecular frame. But for molecules oppositely oriented, this current will have opposite direction in the lab frame. Now, because chiral molecule is kind of a corkscrew, the current, linear current, which is excited, say, along this direction, couples into circular current, which goes in a particular fixed direction of rotation. And this fixed direction of rotation is determined by the molecular Hedman mass. So that's what you see on this figure. This current, which molecule, basically the response of the molecule, the circular current, will be in different directions in enantiomer oriented this way and oppositely oriented enantiomer. And it will be in different direction because the current in laboratory frames, linear current, was in different direction, and because the circular current has fixed direction of rotation here and here, which means in laboratory frame, it rotates in opposite direction. So now the probe pulse also has a rotation, a circularly polarized probe, and due to propensity rules in photoionization, it preferentially ionizes the molecule in which it has co-rotating current with the circularly polarized light. But the counter-rotating current will be less preferred. Therefore, we'll have more ions in this orientation than in this orientation. So in simple terms, the linearly polarized pulse excite bound electron current and geometric field. Molecules where this geometric field, you see it here, P+, is oriented along the propagation axis of the circular probe, will be preferentially ionized. Now, how strong is the effect? We excited two superposition of two orbitals in the propylene oxide molecule, LUMO and LUMO +1, and calculated the average angle between the propagation axis of light and the angle which characterizes the orientation of the molecule. And this is this vector. It's along this field. So the cosine, average cosine of this angle is 0.12 minus 0.12. And what it means that out of 10 ions produced, approximately 60 of them will have the vector in the lower hemisphere, and 40 of them will have this vector in upper hemisphere. This corresponds to quite significant orientation, and what is very exciting is that axis along which the molecule will be oriented, they are defined by the orbitals that you excite, which means you have a lot of control over orientation direction that you can induce. So this is my last slide. And what I would like to conclude, with the observation that geometric field that we have introduced allows one to establish new classes of enantiosensitive observables. What I have shown you today are the chiral one of the members of the first class of observables that rely on the net geometric field. So this is this observable, and it requires excitation of the current. Class 2 observables, they rely on the net radial component of the geometric field, and this is PCD effect that I described to you, a time-dependent PCD, which can also rely on the current. And finally, third class of enantiosensitive observables include the entire array ad infinitum, and that relies on the multipolar expansion of components of the B field. So you can consider that this field has three components. One is radial and two tangential components. And because components are the scalar fields, each of these scalar fields you can expand into the series of spherical harmonics. And that's what is written here. And of course, it gives you a lot of different tensorial enantiosensitive observables or tensorial anomalous observables. And this is, so far, one of them was observed, but the rest remain unknown and still to be uncovered. So I will come to the conclusion that I have introduced to you new enantiosensitive observables of class 1, and they are messengers of charge-directed photoreactivity in chiral molecules. X-ray can generate site-selective core excitation, and this may allow one to control direction of excited currents, orienting molecular ions along a desired direction, and the required setup is linear pump and circular probe Geometric magnetism underlies, I wouldn't say all, but many new and anti-sensitive observables in photonization and enables new phenomena. New questions and directions. What is connection between topology of the geometric field and photonization and topological properties of molecular states? And finally, quantized chiral observables. Is it possible to use laser field to create topological phase transitions in chiral molecules, similar to Flaky engineering and solids? Thank you very much for your attention.
Thank you, Dr. Olga, for a wonderful presentation. Now we have some questions. Like one question is there from Madhusudan. Madhu, you can unmute yourself and ask the question.
Hello, ma'am. Am I audible?
Yes, yes.
Yeah, it was a wonderful talk because until now we have looked at chiral molecules like the orientation or the alignment of the molecules would not matter for any circular polarization or any right circular or left circular that you put on the molecules. But according to your talk, if I understand right, you are trying to say that the alignment or the orientation of the molecule matter, or they show a significant difference when you study the PECD of those molecules. Isn't this a little counterintuitive for what we already know? I know that you started off your talk like this, saying that it is very new, but
yeah. So basically, I read quickly. I read quickly your question. You are asking if PECD includes PICD, right?
Right.
So, it's a very interesting question. Thank you very much, and I can show you a very curious slide, which I actually not wrong direction, which I actually skipped. So we can compare two observables. One is time-dependent PECD, so you have linear pump, excites dynamics on the states, and then circular probe photoionizes these states.
Right.
And at the same time, so we will measure electrons and resolve them on angles like a PECD, and we also measure fragments, ions, and also find their orientation. So this would be PECD, and that would be PICD, as you call it. I call it MOCD, but it doesn't matter. Now, what is the message is that these quantities are completely independent. They are described by completely different quadratures of the field. So this is described by Q minus and P minus quadratures, and this is described by P plus quadratures. And here they are plotted on this graph. So the interesting thing is that this observable is very much complementary to those two observables, and it exposes different chiral property of the molecule, the chiral property of the molecule that we could not catch in here. So that is what I think is interesting. And what I think is also interesting is that you can basically have, you can have this classification, which allows you to see that these observables are independent. Each of them exposes a different chiral property of the molecule. So I hope I answered. If not, please ask further question.
No, you did answer the question, but my further question would be, like you showed, there is a 60 ion will follow the PECD and 40 ions might not follow the PECD, right?
No, it's not that much. It's basically, it's a degree of orientation. So right. you can estimate this degree that, 60 here and 40 here. So
So are you talking about the experimental difficulty or the theoretical difficulty?
No, there is no theoretical difficulty. This is basically calculated analytically. There is no problem. Only the input that we have is from the basically specific method, which is static exchange DFT photoionization dipoles, which are very accurate, and they have been compared with the experiment. Anyway, so there is no difficulty. The effect can be larger. This is the first combination that we used, and that gave us this effect. Effect can be larger because it very much depends on the value of this quadrature. So if you excite a different superposition of orbitals, you can get a better response, or you can get worse response. So basically, first of all, I would like to say that this is already a pretty large effect. And second, you can optimize it by optimizing the excitation step.
Right. So I wanted to ask you, how can this be realized experimentally?
Experimentally, to be honest, relatively easy, because similar experimental setup has been already implemented to time-dependent PECD, and this is exactly what I showed here, linear pump circular probe, so you can study in this publication. But in this publication, as I told you, they looked at the photoelectrons, and now you would need to look at the ions. So you would need to detect angular distribution of fragments.
Right. Okay.
Thank you, Professor Olga, for answering the questions. There is one comment in the question and answer. Thanks a lot for this very informative session. Your talk ignited my lost interest in enantiomers and chiral molecules. And there is one more question there. I would request you to answer it in the question and answer sessions.
Very
thank you so
good
much for being here with
questions.
us today.
Thank you. Bye.
Okay, thank you. So I hope I'm audible, and this brings us to the last talk today, but we are very happy to have you, Professor Xiangfeng Ma, who is an associate professor at Institute of Interdisciplinary Information Sciences at Tsinghua University. Xiangfeng Ma received his PhD in 2008 from Department of Physics, University of Toronto, Canada. From 2008 to 2012, he was a postdoctoral researcher in the Institute for Quantum Computing at University of Waterloo, with the University of Toronto, and also visiting scholar with the University of Leeds, UK. In 2012, he joined Tsinghua University, China. He received Tsinghua Distinguished Teaching Award in 2018, OSC Outstanding Reviewer Award in 2018, and IOP Outstanding Reviewer Award in 2019. We are looking forward to hearing about phase matching measurement device independent quantum key distribution. So we are very happy to have you today with us, Professor Ma, and thank you so much for accepting our invitation. We are ready to start, and the floor is all yours.
Thanks all for the nice introduction, and thank you again for the invitation. And let me just change it a little bit. Can you see my slides?
Yes, they're visible.
Okay. My name is Xiangfeng Ma, so I'm from Tsinghua University. So today I'd like to talk about the phase matching quantum key distribution. So this is a joint work with some of my students. First, I will give a brief introduction. The good thing is that the Eleni, she already introduced the QKD in the previous lectures. And then I will talk about the security analysis. I will introduce some problems in realistic systems. Finally, I will introduce our work on the phase matching quantum key distribution. Introduction. So we know that the problem of the conventional cryptography is that the foundation is normally based on some unproven computation assumptions. When we have development in the future, when we have development on the hardware and the software on computation powers, then this foundation might not be valid. So this is the major problem for the current cryptography. Good thing is that the quantum cryptography provides information theoretical security based on quantum mechanics. But here I want to emphasize that the quantum cryptography cannot replace all the classical cryptography. Actually, currently what we can provide is the one is the key distribution, the other one is the random number generation. Okay, I don't want to overclaim the quantum cryptography. And so in the theory, so we know that the quantum cryptography, like a quantum key distribution, is proven to be unconditionally secure or absolutely secure or information theoretically secure. They basically mean the same thing. It means that we do not put any computational assumption on if. So we don't really assume that if's computational capability. But sometimes in the news or from the literature papers, we hear that the crypto system has been breached or attacked. So what's the problem? The problem is that the difference between the theoretical security and the practical security. So we know that with certain mathematical model, we can rigorously prove the security of a crypto system or quantum crypto system. But in practice, when you build up the system, you might have some device imperfections. So we have lots of engineering problems. So this is evolved with the practical security. So in this case, so I would need to emphasize that even with the quantum crypto system, in practice, we cannot reach the absolute security. Okay, so it's only if you think about that from the practical point of view, it's only a better security level than the current crypto systems. Here I give a quick overview. She already gave a very good review on this. So we know that in the beginning we have the BBA4 6 states, and then we also have the security proofs. Meanwhile, I skipped lots of the other protocols such as the continuous variable QPDs. Okay, so here I will introduce a protocol we call the BBM92. It's proposed by Benjamin Bossard and Momin in 1992. Nowadays, we sometimes view this protocol as we call the entanglement-based BBA4. So the protocol runs as let me find the pointer. Okay, so there's a source, integral source. We suppose this is the EPL pairs. EPL pair source 00 plus 1 1. So 2 particles. And then send 1 particle to Alice, send 1 particle to Bob. Okay, so this is the source is in the middle. We can either think of Alice owns the source or Eve owns the source. And then once Alice Bob gets half of the qubit, so Alice Bob will randomly perform the measurements of the Z-basis measurement and the X-basis measurements. Z-basis measurement will tell us, let's focus on the Alice side, because in this protocol, Alice Bob, they are symmetric. From Alice side, so Alice measure her half of the EPL pair and in the Z basis, and then she will get 0 or 1. She can also measure in the X basis. She can distinguish whether the phase is plus or minus. So whether this is a plus sign or minus sign. So in this case, it's like if Alice Bob both measure Z basis, if the system is idealized, then if everything is perfect, then if they both measure, Alice and Bob both measure Z basis, they will simultaneously get get 0 or they get 1. It's random. It's with probably the 1/2. Of course, in the channel there might be noise, so that's a key point of the security proof of the Rho-Chart. So the proof runs as follows. So the idea is quite straightforward. So they employ the entanglement distillation protocol. So in the beginning, the source sends out the EPL pairs, but in the channel it's noisy. So if the channel is good, then the state become still the Alice Bob will reach the state of 00 plus 1 1. But there might be some say a bit flip. Okay, the 0011 plus 11 becomes 01 plus 10 state, or there might be a phase flip. 00 plus 11 becomes a 00 minus 11 state, and sometimes there also could be both a bit flip and a phase flip, and then it becomes a 01 minus 10. And we know that once Alice gets a qubit, Bob gets a qubit. For 2 qubit state, we can write the 2 qubit state in a Bell basis. Okay, so in this basis, okay, so we can express the any arbitrary 2 qubit state in this basis. Okay, so that's the beginning. That's the starting point for this security proof. So okay, let me go through it again. So Alice Bob has Alice Bob. Originally, there's an EPL pair distributed to Alice Bob, but it's noisy. But it's still 2 qubits. So it's if you perform the Bell measurement, if you perform the joint Bell measurement, you will get the either of one of these 4 states, Bell states. Okay. So the idea is that you just perform, if Alice Bob, they have quantum memory and the quantum computers, they can just perform bit error correction and phase error correction. So for bit error correction, they just focus on the Z basis, and then they correct all the Z bit flip errors. So these 2 states, they have bit errors. After the bit error correction, you will correct all these kind of states. Then after bit error correction, you only have these 2 states left. Okay, 0, 0, plus minus 1, 1. These states left. And the phase error correction is similar, but it's in the phase space. Phase errors, we know that as long as it's a minus sign, there's a phase error. Then after phase error correction, Alice Bob will share states either 0, 0 plus 1, 1 or 0, 1 minus 0, 1 plus 1, 0. Okay, if you can design, actually it's proven that in another paper that you can do bit error correction and the phase error correction simultaneously, such that eventually you can reach the state of 0, 0 plus 1. Okay. So this is called entanglement distillation with the quantum error correction. Okay. So after this error correction, so Alice Bob will share this n copies of 0, 0 plus 1, 1 perfectly EPL pairs. So given this state, if Alice Bob perform the Z measurement, Z measurement, both Alice Bob perform Z measurement, then they will reach this state. Okay. So when I put this Z measurement, it really means that in the defacing operation, then you reach this state, and this state is the definition for the secure key. That's definition for secure key. So the key point, one of the key points is that it's tensor with any other system if. Why it's a tensor? Because the original to be measured state is pure. We know that a pure state is if you put for any pure state, it's a tensor form with any other system, right? So pure state is always it's complete. Okay. So the one-time pad encryption can be think of as a quantum teleportation. Okay. So that's a proof of the Rothschild secure proof, and of course the one main drawback of in the Rothschild proof is that Alice Bob, they need quantum computers to do quantum error correction. So they want to do this very complicated operations. And the next step is by Shaw and Pascal. They say that, okay, we can smartly design quantum error correcting code. In that paper, they use CSS code. And then so that these 2, with error correction, phase error correction, they commute. And also they commute with the final Z measurement, key measurement. We know that after they get an EPL pair, they will measure Z to get final key. If you can design this all these boxes well, then with error correction, phase error correction, they all commute with this final Z measurement. Then you can move this key measurement before bit and the phase error correction, and then bit and the phase error correction becomes classical post-processing. Bit error correction becomes regular error correction, or we call it information reconciliation. Phase error correction becomes a private application, and the final key rate will be 1 minus of bit error correction cost and the phase error correction cost. Okay, so that's a basics for the security of QKD. And then, okay, that's very nice. That's done in 2000. Okay, what do we have done? What do we have done in the last 20 years? Okay, what's our focus? Okay, it's again, it's the problem of the side information. So we know that in the secure proof, what we just discussed is the in the secure proof is we talk about qubit. Alice has a qubit, Bob has a qubit. Okay, and then all the operations are acts on this qubit. But information might be contained in other degrees of freedom, like timing of the pulse or frequency of the pulse. So even for, let's say, single photon, you might have lots of freedoms. Okay. For example, Joe Bossard, one of the godfathers of the quantum information science. So he comments on their own first experimental demonstration of the QKD, say that it was unconditionally secure against any eavesdropper who happened to be deaf. The quote is it's because he had such quote because for the first experimental demonstration, so they used 2 single photon detectors to detect 0 and 1. So basically, when you perform the measurement, you get the finally perform Z measurement, let's say, and then you get 0 or 1. And then these 2 single photon detectors, they use cooling devices, water cooling devices. And then these 2 single photon detectors, they will provide different sound. Okay, so if this detector click, then it will provide one sound. Okay, let's say dong, 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 dong. And then this another detector clicks, and then it will provide another sound. Let's say then if do not need to perform any attack, she can just sit around, hear the voice of the single photon detector. She can tell whether the detection is 1 or 0. Okay, so that's one example of the science information. So your key information is revealed through the sound of the single photon detector. Okay, I see a question. Okay, let me quickly check. Okay, let me go back to the previous slides. Okay, the question reads for a pure state with if in Rothschild secure proof, is there any limit on the dimensionality of if? Okay, there's no limit. So the point is, think about that. If Alice Bob has a qubit. Okay. So basically, in this case, so if Alice has a qubit, Bob has a qubit. If together is a pure state, it's already pure state. So no matter what if system is, it's always a tensor product form. So that's a key point. So we need to make sure that the state is pure, and which is guaranteed by error correction. Okay, we can eventually after error correction, the state is almost pure. So when I use the word almost, it's secure parameter details. Okay, let me see. Okay, does that answer your question? Okay, I'll continue, and then if you have question, keep pop up in the Q&A session.
Thank you. If you
okay,
want,
so yes.
Okay, if you want, I can ask the questions in between. Otherwise, we can take the questions in the end, as
Okay.
you'd prefer.
Okay. So let's look at the system in details. So there are 2 parts of the system. One is source, one is detection. Okay, let's look at the source first. What's the problem with the source? One of the problems is the multiphotons. So here in the secure proof, we assume there's an Alice. So basically, so in the Alice really okay. So this is a little bit confusing because here I switch to another. Another protocol. So this I go back to the original BB84 protocol. So here I will try to show you another example of the site information. So when you send out in the BB84, when Alice send out some qubit, so normally in the communication we use the photons as an information carrier. So Alice send out a qubit to Bob. So for single photons, it's nice with the single photon polarization. So Eve can also just copy this photon and then send the copy to Bob. So she cannot do that. So this is guaranteed by no Coulombian theorem. But what if Alice, when Alice sent out the qubit, it's already a copy of 2. So basically, we have 2 photons. Each photon contains a copy of the state. Then Bob, Eve can, in principle, can split these 2 photons, gets 1 photon, and then send another photon to Bob. So from here, we can, this is another example of the device imperfection. So if we do not have a very good single qubit source, in practice, normally you can use single photon source for the qubit carrier. And then if you send out multiple photons, it might get information. Okay, so we have lots of problems. So in the QKD system, we have lots of site informations. So the good thing is that there's a very nice framework provided by Gauss-Monroe, Lukinghaus, and Preskill. So they come up with this idea, say that, okay, suppose you can characterize your system. Suppose some parts of the source, let's say single photon source is good, multi-photon source is bad. And then eventually your key. So, but you in the experiment, you cannot really distinguish whether it's come from a single photon or multiphotons. Otherwise, you can just remove all the multiphotons. And then so Alice Bob gets some key, raw key. And then the idea that we know that some part of the raw key come from the good, let's say, single photon source. Some part of the raw key come from the better ones, like multiphoton state. And how can we get a final secure key? The main idea is to use the so-called tagging idea. The idea that if we XOR a good key and a bad key, the result is a good key. Okay. Let me picture this with the Eve's point of view. So think about that. Alice has two bits. Okay, we can focus on Alice's side. Okay, has two bits. Okay, Eve from Eve's point of view, from attacker point of view, she knows one bit, but she does not know another bit. And then if you do the XOR of these two bits, the result Eve does not know. Right? Okay, so that's the idea. So a good key and a better key, if you XOR together, it becomes a good key. It means that Eve does not know the final key. So then the idea is to just use linear hashing, randomly XOR all the key bits, and then you can get the final secure key. But the key point of this framework is that you need to know how much of the secure key you get, how much of the secure key you can have for the good ones, how much of the final raw key is better ones. Okay, you need to know the ratio so that you can perform this hashing private application. Okay, so in the on the source side, we propose this decoy state idea to enhance this performance. Originally, key is in the order of the O eta square. Eta is the transmittance. So basically, when Alice send us one photon, and then what's the probability for this photon to go through the channel and detected by Bob? Normally, eta is a very small number. A typical number will be less than 1%. Okay, so eta square is much less than eta. So we improve from eta square to eta. Okay, so that's a big improvement. Okay, so we can compare the performance. So in the y-axis is the key generation rate. You can think of it as the bits per second. Okay, it's a kind of speed. Okay, so this is a really what's really written here is a secure bit per pulse. Okay. Y-axis is the x-axis is the distance. Okay, we know that when the distance is further and further away, the transmittance is exponentially decreased. Okay, exponentially decreased. Okay. So that's a picture we are talking about. Okay, after that, so with the decoy state, we can reach the key rates of the O eta. Okay, in the order of O eta, and then after that, people prove that the O eta is the best key rate you can reach with a point-to-point link. Okay, if Alice sends some state to Bob, so in this scenario, O eta, that's the maximum key rate capacity you can reach. Okay, so it's also true for continuous variable QPD. Okay, so this is a very big limit on this one. Okay, so of course we know that the distance so this is pretty much at that time people feel like that's already the best we can reach. Okay, let's talk about another problem. So previously we talked about the source problem. Okay, single photon source, multi-photon source. Okay, what about detection? Okay, let's go back to the original, this BBM92, this protocol. In the secure proof, when I say that originally the state is 00 plus 11, go through a channel, go to Alice Bob. But the channel is arbitrary. So the channel or Eve will change this state to arbitrary 2-qubit state. So in this case, we don't really trust the source. So the secure proof does not rely on the realization of the source. Okay. So this we call a source independent QPD. Okay. Okay. So that means that you can use arbitrary source. Okay. You can use arbitrary source. And then if you get the security, you still, the system is secure. Okay. What's the observation? So the security does not rely on the specific implementation of the source. Okay. And so it's a source device independent. If the source from 00 plus 11, this source is scrambled, Alice Bob they are able to detect it. Okay, in the Z-based X and the Z-based measurement. Okay, and in this protocol, as we introduced, Alice and Bob's position, they are symmetric, they're interchangeable. Of course, in this case, Alice has a detection system, Bob has a detection system. They are trusted. Those detection devices, they are trusted. So the problem is that in reality, especially with the decoy state method, source is simple. It's we can more or less make it already secure. But detection device, single photon detection device, is quite complicated. Actually, if you check, if you do QKD experiment, you will see that the detection device is that's the major cost for your experimental device. Okay, so it's much more complicated. And now the question is can we reverse the trust part of the system? So the point is the source is simple, detection complicated. So it's better we don't trust the detection, but we trust the source. It's easier for us to calibrate a source than the detection device. So can we basically trust the source but not the measurement? We can reverse it, call it a measurement device independent QKD, so MDI QKD. Okay, the answer is yes. Okay, it's proposed by Hong Low and his colleagues. Okay, so the idea is that it's just a time reverse point of view of this BBM92. So BBM92 is the source in the middle, sent to Alice Bob perform the measurement. So once Alice Bob perform the measurement, they will get, let's say Alice will get 4 outcomes, 0, 1, plus, minus. Okay, Bob is the same. Okay, but the idea is that can we reverse this process? Alice prepares 0, 1, plus, minus. Bob prepares 0, 1, plus, minus, this qubit, and send to the middle. Perform in the middle of this site, untrusted measurement site. Let's say Eve. Okay, she will perform the Bell state measurement, project these 2 qubits into Bell state, and then from a time reverse point of view, it's the security is the same as you prepare this EPL pair, send to Alice Bob, gets the measurement outcome. Of course, this is just intuition. We can have a very strict secure proof on this one. Okay, so again, think about that. So Alice prepare this the BB84 state 0, 1, plus, minus. Bob is the same. Send the state in the middle. In the middle, Eve perform the BSM measurement. Normally we call it Charlie because but it's untrusted. So basically, this measurement site you can think of Eve owns the measurement site. And then we can also make it a phase encoding. So I will introduce phase encoding MDI QKD. So Alice use think about that. Alice use single photon source, send out one single photon, and then go to the PBS and then send separate into 2 modes. For one mode, she apply a phase modulation on that one, and then the other one is reference, and then send 2 in the middle. Bob does the same. And then in the middle, the BSM is very simple, just by interference, single photon interference. When Alice Bob gets 1 click here, 1 click here, they will claim that this BSM is successful. Okay, so that's the measurement. Okay, the qubit information is encoded in the relative phase between this pulse R and the pulse S. So so normally we encode the 4 phases like 0, 0 pi, and the half pi, 3 pi over half. Okay, and then we can do perform the QKD, MDI QKD. Okay, so the experimental challenge for this MDI QKD is that in order to do this Bell measurement for this single photon interference, we have to make sure that these two photons. So this 1 photon come from Alice, 1 photon come from Bob. So these 2 photons, these 2 optical pulse, they have to have the almost exactly same frequency and arrive at exactly time. And you cannot have anything else to distinguish these 2 pulses like a polarization. So you have to make it indistinguishable so that they can do this single photon interference. Okay. So that's a challenge, but so this can be done. Actually, it has been done like almost 10 years ago, 8 years ago. Throughout there are quite a few groups in the world. 70 demonstrates this MDI QKD. Okay, so you put the device source on two Edison bulb, and then in the two sides. Let's take this one example. So we have Alice here, we have a bulb here, and then Alice will send one single photon in the middle. Bob will send another single photon in the middle, and then in the middle measurement site, they will do the interference. Okay, what's the features of the? Let me check out the time. Okay, what's the feature of the MDIQD? So first of all, it's immune to all detection attacks. Okay, because we already assume the measurement device is already entrusted. And also you have two quantum channels. But so in total, from Alice to Bob, the transmittance is eta. If we have two channels, for each channel, it's square root of eta, right? Square root of eta. So because it's decay is exponential. Okay. So square root of eta here, square root of eta of this channel. But we need the coincident detection. So that's why square root of eta times square root of eta is still eta. So the key ratio is still O eta. So it's the same as the coincident QED. Now the question is that can we go beyond this linear bulb? Because if we think about this, this linear bulb is only point to point. But for MDIQD, we already have a third site in the middle. Can we go beyond this O eta? The answer is yes. So here I want to introduce this phase matching MDIQD. So the idea that's if we go back to this phase encoding, this picture. So the idea that's if we only consider half parts of this system. So if we think about that, if we look at this picture, pulse R doesn't really contain any information from Alice because this is just a beam splitter, and then this is a pulse. The information is here in the phase modulation. Information is all the Alice information is in the signal pulse. Okay. So strictly speaking, from this picture, we can see that Alice does not really need to send out pulse R at all because there's no information encoded on R. If Charlie, this measurement has some local oscillator, then she can prepare this R herself. Okay, same for Bob. So basically, it's like if we look at this phase encoding MDIQD, half of the setting is kind of redundant. Okay, the better half of the circuit is redundant. So only the bottom half of the circuit is sufficient. So that's the key idea of the phase matching and the MDIQD. Okay. Then Alice will encode this information on this pulse centered in the middle. Bob will encode the pulse in the middle. Okay. So in this case, the advantage is that we don't really need a coincident detection. Okay. Now we only need one detection. So we can increase the detection efficiency. Okay. But of course, the security proof will be very different. Okay. So now so this is Alice, send some pulse, some states to Bob, to Eve. Bob will send some states to Eve. Okay, I will change this figure a little bit. I will move it together. Okay. So this is Alice, send out some states to Bob, to Eve. Bob will send some states to Eve for the measurement. Okay. So let's look at this picture. Okay, so let's assume that this Alice encoding, let's say this phase encoding, she will apply some phases. Okay, let's say unitary operation U. Okay, now let's assume that this U has a property of the U squared equals to I. Okay, Bob is the same. Okay, so think about that. Alice encrypts at 0 pi. Bob encrypts at 0 pi. Okay, 0 pi phase. Okay. Okay, in this case. So then, if you look at the states of low AB together, so we can separate. So for this low AB, so because U squared equals to I, so for the operator, unitary operator, U cancel U has two eigenvalues, +1 and -1. So this space of the low AB can be, so this helper space of AB can be separated into two. One is the even, we call the even subspace. It's when the state is has a +1 eigenvalue. Or the subspace is a -1 eigenvalue. So we know that if low AB is in this subspace, then the whole protocol is secure. Why? Because Alice Bob will both perform U or both perform I. And then the state is the same, but that's one is the key equals to 0, key equals to 1. So basically, when the key equals to 0 or key equals to 1, the channel, the state if received is exactly the same. Okay. When the two states, when the state key equals 0 state and key equals to 1 state are exactly the same, if cannot get any information out of this state. So there's no information leakage at all. Okay. Same as the other state. For the other states, if Alice sends out this state, Bob sends out this state, again, this overall phase doesn't matter if cannot distinguish the overall phase. So in this case, for the other subspace, it's also secure. Unfortunately, if you mix in these two subspaces together, the state might not be secure. Now, what we need to know is that we need to say that, okay, the original encoding state, rho AB, is almost in one subspace, just it has a little in another subspace. So that's the key point of the security proof. It's shown in this paper. Okay, it's a little bit complicated, so I will skip lots of details. I just give you I just sketched the proof. Okay. So then, what we need to prove, what we need to do the privacy application is that we just look at, let's say, that if we say that the states mostly in the odd subspace, just a little bit in the even subspace, then we can treat the even subspace that ratio as the phase error. If we can correct all those phase errors, we can get to reach the secure key. Okay. So in this secure proof, it's like we decouple the bit error and the phase error. So they are decoupled. So this is really come from the whether you are in the even space or subspace. So this is the regular quantum-based error rate. And then we have this Q-race formula. So this is very similar to the short plus skill Q-race formula. Okay, if we ignore Q mu. Q mu is the okay, if Alice Bob send out signals, what's the detection? What's the valid detection rate on the measurement side? Okay, so think about the Q mu is the number of the raw key. Okay, think about the Q mu is the number of the raw key. Okay, so this key rate is proportional to square root of eta because we only need one detection for one key bit, raw key bit. Okay, so the key rate is in the order of O squared root of eta. Okay, so the secure proof is also proven in the another paper.
Sorry to interrupt you in between. Can you wind up in like 2-3 minutes if possible?
Okay, sure. So it's already in the end. Okay, so
yeah,
then
we have a yes. Okay.
Okay, so already it's already the last almost last slide. Okay, so then we can perform the do the simulation. We can see that it can outperform the previous protocols. Okay. So we also have the experimental realization. I will skip the experimental realization. I will jump to the conclusion directly. Okay. So this is just experimental realization. So how to implement this experiment. Okay. So the conclusion is that we can reach the key rate of the O squared root of eta, and then it also has a measurement device independence property. In the future, we want to work on the even faster, higher key rate, and then also can we make even the source side less trustful. Okay, so that's pretty much all for this talk. All right, thank you. Any questions? Okay, we have do we have some questions in the Q&A? Okay, let me check it.
So the first question is, how can one detect single photons from multi-photons for click detectors?
Okay, very good. Okay, let me go back to the original question. So actually, we cannot. Okay, let me go to the cost data slide. Okay, let me go to GLP. Okay, this one. So in reality, we cannot really distinguish that a click comes from a single photon or multi-photon. How can we do it? That we use a decoy state method. So we know that when we send out the signals, we know that the probability to get single photon and the probability to get two photons follows a Poisson distribution. So we know how many states, how many single photons we send out, and then we can calculate what's the ratio of single photons get detected. Okay, so this is the key point of the decoy state. So if we attenuate the intensity, then we can have different Poisson distributions. We can have this kind of linear equations. We can have this kind of linear equation. If we have a bunch of these linear equations, we can solve this linear equation to get how much single photon detections. Okay, so that's the key idea. Okay.
Key
Right.
idea is that theoretically we can, but experimentally using single photon detectors, we cannot, right?
So in experimentally, instead of using single photons, we use a coherent state. So whose photon numbers follows Poisson distribution. So basically, it's like if you only use one single photon, then it's one Poisson distribution. If you use one coherent state, it's one Poisson distribution. If you use another coherent state with different intensity, that's another Poisson distribution. You have different these kind of linear equations. You can solve the linear equation to get how many single photon, what's the single photon portion. Okay, so that's the key idea of the decoy state. So we don't really need to distinguish on the detection side. It's only the source side is sufficient.
We have one more question. Can Eve use entanglement swapping to gain some information in phase encoded MDI QKD?
Okay, so so entanglement swapping. So basically, it's like so when we talk about the MDI QKD, so the detection device is it's untrusted. Detection device is untrusted. So if Eve can use this entanglement swapping, so basically once Alice Bob do not receive any signal, so once Alice send out a signal, then it's done. So it's blocked. So the channel is blocked. So once Eve gets the signal, Alice signal and the Bob signal, she can do whatever she wants. So she can do entanglement swapping. She can do anything she wants. But that won't change the fact that she need to correlate Alice Bob signal in a Bell state measurement, that kind of case. Then if she eventually does that, then Alice Bob's signal becomes a kind of Bell state. Then with the Rothschild secure proof is secure. Okay, so that's the key idea.
Okay. Do the decoy pulses need a different mean photon number from single photon pulses in decoy state protocol?
Oh, okay. So here we only have the coherent state pulse. We don't have the single photon pulses. So basically, yes, for the decoy states, for decoy state pulses, normally the intensity is different from the signal pulses. Okay, the intensity is different, so that we can have these linear equations.
Right. Okay. Is there a chance that after privacy amplification, any bad photon can be left in the secret key, as we are unable to measure the exact photon state for the given pulse? I think it is a follow-up question from the previous one.
Okay.
A single photon.
Okay. Yeah. That's a good question. The answer is yes. But you ask that question about is there a chance? Yes, there is a chance. But the chance is very, very small. We can mathematically calculate upper bound of this chance. We can make it exponentially small in practice so that it can be negligible. Okay. Normally in the practical systems, we use the number, let's say 2 to the 1 minus 100. So it's a very small number. We don't need to worry about.
Right. So if there is no Eve, can we use this protocol to QKD between Alice and Bob? This is another question.
Which protocol?
Decoy state.
Oh.
MDI.
Oh.
I think
Okay,
Gautam sir can tell which protocol are you talking about, sir? I think if Eve is not there, we can use any protocol. Right. But Gautam sir, are you there? The current protocol. He's talking about the current protocol.
Current protocol. So basically, it's like you mean phase matching protocol.
Phase matching, yes.
Okay, phase matching. Oh, so what's the question again? Sorry.
If there is no Eve, can we use this protocol to QKD between Alice and Bob?
Okay, so if there's no Eve, then actually in practice, okay, in the real experiment, normally there's no Eve. Normally there's no Eve. So so the measurement device is we really need to build up this measurement device ourselves very, very carefully. Okay, normally that's a hard part. That's a very hard part. So if Eve come over, try to learn something, she will inevitably introduce some disturbance, and Bob will figure it out. So that's the idea of the activity.
Right. So thank you, Professor, for answering all the questions. And thank you for being here with us today.
No problem.
I thank
you.
the audience also for their attendance. There is Pyaril Amrit Vyakyan at 4, I think it is 4 right now. So at 4, there is Pyaril Amrit Vyakyan. It happens every Wednesday. So I invite everyone to join us there at Pyaril's official YouTube website. Thank you, everyone.